Well, let's jump right in then. Just a few things to observe, some of which I think are obvious. The government is about to shut down. That seems pretty almost inevitable at this point. I've spent a bunch of time on the Hill and talking to OSTP since our last meeting. I mean, it's all tied up. Research funding is obviously all tied up with the budget mess, and I'm sure others will talk about that from the perspective of DOE later today. A couple things I did want to share. One is that OSTP, as mandated by the CHIPS and Science Act, is conducting a quadrennial review to produce broad science and technology recommendations. Those of you familiar with DOE doing quadrennial reviews, this is the national one. The first one is due by the end of the year, so it's a quick sprint, but will be interesting to see what comes out of that. I know several groups have been talking to OSTP as they seek input, and I certainly have been as well. Last couple things, just quickly, is at our last meeting, we heard the outbrief from Jack's committee about the state of global competitiveness in HPC. We also talked some about the National Academy study that looked at the state of computing for the weapons labs. And obviously, those two reports largely overlap and say the same thing, so no surprise there. The issues are the same on both sides, and as are the challenges around those. And so some of those are tied up with what the broad national strategy around advanced computing should be going forward, and how we sort that out. Obviously, a lot of things happening on both the government side and the DOE side. I am hoping that we can stretch the meeting a little bit at the end and allow a little bit of time for the committee to sort of talk about where we think we all are. And what some ideas might be going forward. And I expect we'll have some input from DOE during the day that could provide some input for that process. But we're currently at a big fork in the road about what the future of advanced computing looks like in just about every way that one could imagine. And it's important that we collectively choose wisely and thoughtfully, because the technology base in which we depended is shifting rapidly, and there are some dead ends as well as some forks in the road. So with that kind of setup, I know, let me try to not make us any more late than we already are, and hand the floor over to Esmeret to give the view from DC. And I'm sure she will perhaps correct or elaborate some of the things I just said. So over to you.
Morning, all.
Good morning.
It's always a pleasure to join you all. And first and foremost, let me start by thanking everybody for your participation and presence in this committee. I can't understate, obviously, how important the work you do is to the Department of Energy's Office of Science and the computing community at large, and the American public that we are so fortunate to have entrusted us with so much public resources to guide the direction of the science enterprise in the nation. I also wanted to take a moment to recognize and congratulate Jaren in her new role as the Permanent Associate Director for Science for ASCAC. We're thrilled to have you and very much appreciate your hard work and expertise over the years in pushing forward computing science. So thank you all. I think you all know me at this point, so this is the third time I'm speaking to ASCAC, so I don't think I need to introduce myself, but I'm excited to join you all today. So jumping into the topics of the day, this community is working on some incredibly important topics. Obviously, it seems like the work you all do has yet again captivated the public's attention. It's in the news constantly and of great interest, of course, to not just scientists as well as the public and our stakeholders. From quantum information sciences to artificial intelligence and digital twin technologies and groundbreaking news at the forefront of microelectronics. It's a wide swath of science that's really of great interest to an incredibly wide segment of society. The direction and future research of this committee are then, of course, means that they're very critical. I'm looking forward to hearing more on your research priorities, updates from the Exascale Computing project in the home stretch, if you will, and so much more following your meeting today. I know you're all excited about the results starting to flow in this new AI-enabled exascale era, and I appreciate that you're creating a bold vision for AI. The ASCAC community has been thinking about AI, of course, for a long time and came together first for the AI for Science workshop series and more recently for the AI for Science, Energy, and Security workshops, which are incredibly important and really timely. This community's efforts present DOE with a unique opportunity to take a lead role in this critical area. So you all played and continue to play a really important role. Of course, our leadership computing facilities also continue to provide a valuable resource for this research and so much more, including new allocation program enabled by a 1-year extension of the Summit system. This can now remain a pretty stable and significant resource for the community with over 1 exaflop of mixed precision performance that, of course, the AI applications desperately need. And there's, of course, a lot more exciting and a lot more exciting opportunities about Frontier that are the fore these days with its nearly 10 exaflops for similar performance, and the fact that Aurora at Argonne National Laboratory is expected to have even greater capacity and capabilities for AI researchers, all just incredibly exciting time. And as amazing as the results continue to be, the ones that are coming in to the new exascale science era, I also understand that a few congratulations are in order. I was so happy to hear we have a finalist in the new special category of the Gordon Bell Prizes for high performance computing in an area that's very dear to my heart in the climate space, climate under the Exascale Computing Initiative, which is on the agenda, including for today's meeting. This work is, of course, advancing the goals of the Biden-Harris administration to address climate change and is a major step forward in serving the public as well as researchers across the country. And congratulations to all who contributed to make this the success that it is. I also understand that Oscar facilities and ECP have also enabled 3 traditional finalists as well, including another ECP application team. These efforts are, of course, leveraging exascale and AI to accelerate progress in small modular reactors, novel materials, and HIV research, to name a few, and all of that is just demonstrating the wide range of research that will benefit from the AI-driven exascale era that we have enabled. Just so much important work and amazing research. Again, congratulations to all. Coming to the topic that I assume Dan was referring to earlier, I want to assure you all that, of course, all of us here are closely monitoring the budget events that are happening right now and developments as they happen in real time. Please be assured that I'm personally committed to doing everything in my power to not just help us weather this situation right now, but also secure a top-line budget that will allow us to meet our budget expectations with continued full funding. Like you, of course, I am concerned about a possible government shutdown, but know that there's a lot of hard work happening right now to come to an agreement and to think about if there were going to be a shutdown, how the Office of Science and Labs would continue to work through these times as we have in the past. And we're grateful, of course, for the budget flexibilities and careful management of our program direction funds that will allow us to continue to operate to the extent that we are. But we all kind of, at this point, we're awaiting what will happen, of course, in the news and direction from DOE leadership on the path forward if it does happen. Okay, we'll probably pause talking about budget there for a minute, and I want to just highlight a couple of things related to equity and inclusion before I conclude. And this is especially important because, of course, we all are eagerly working to support a building out and growing of the computing workforce for the future. I know you have concerns about continued support for the Exascale Computing project workforce, as well as continued development of the ECP software ecosystems. I guarantee you, we hear you. We are also thinking about this and continuing our efforts to secure more resources for Office of Science overall, so that we can address all the areas that need continued support. For instance, today, you will hear more about DOE's Earthshots initiative, how the applications and software technologies developed by ECP will be leveraged to advance our goals. We also recognize that we are at a pivotal moment to launch a new science era by combining the power of the exascale with the potential of AI, and we're thinking of innovative ways to transition the world's leading ecosystem that ECP created to lead in this new science era. And as you're working to retain and continue your efforts to recruit more people into the computational science workforce, I want to urge you all to focus on broadening participation of people from all walks of life. Broadening participation in STEM is, of course, very important, first and foremost, because it's the right thing to do. And specifically in the case of your community, we've already seen some very concerning signs of what can happen when algorithms, models, and devices are developed and trained with data and information that only consider a limited segment of society, without taking into serious consideration, I should say, the diversity of the public, and not to mention the needs of the diverse and vibrant population that pays their precious tax dollars to allow us to provide public support for this area of STEM and so much more. I challenge all of us in everything that we do, that we must do all we can to attract people from all walks of life to the computing workforce and make sure that we're creating healthy workplaces and exciting professional opportunities that would make the people we recruit want to stay. We must continue this work and continue to offer imaginative and innovative programs to ensure that this field becomes more diverse and more inclusive going forward. And this has to continue, of course, until everyone is included in all the science that we do and support. Again, allow me to say thank you for your participation and hard work and leadership in this committee as we move forward to the future. And I'm looking forward to taking your questions now. I believe we have like maybe 10 minutes, if I'm not mistaken.
Yeah, we'll absolutely make time. So questions from the committee. Valerie.
Thank you. And thank you, Dr. Berhe, for the opening remarks. Really appreciate it. I was wondering, I guess I have two questions, if you don't mind. And I was wondering if you can comment on where you see things going in the microelectronics area. I know later on today, we'll hear more about the CHIPS Act, but welcome your insights in the microelectronics as well.
Yeah, I mean, of course, as you've seen in the news and in the CHIPS Act, we're asked to create the microelectronics research centers and expand our efforts in the space. But of course, all of that will depend on how to what degree and what size that, new programs can be will obviously depend on the budget reality that we all have to contend with, and when we do get the numbers, basically, right? So we wait and see exactly how big that can be. But we also have the co-design activities that I'm sure Sharon and others can speak of that have already been part of our programs that will continue. Again, I can't say at what level, because obviously that all remains in flux until the budget is decided. But the plan is to continue to support it and continue to make sure that the DOE supported community and national labs remain an integral component of this and so central. I think we're doing a good job as a whole, as a department, I mean, in terms of making sure that DOE remains central to these activities. But of course, ultimately, we'll just have to wait for the numbers.
Understand. Thank you. can I ask one more question, Dan, or?
Absolutely.
Oh, okay. Also, I was wondering, you mentioned about AI, and was wondering if you can comment also on activity in the space around NAIR with the National AI Research Resources. I know there's a lot of discussion among different federal agencies in that space, and would welcome your insights also with respect to NAIR.
Yeah, so I mean, as you know, I assume you know that folks, from ASCAC and DOE in general have been active participants in this conversation from the beginning. There's still a lot of conversations that remain about the governance structure and what that might mean for resource allocation, of course, of NAIR that are still being discussed. I don't know that I can say a whole lot more about that, but there's been a lot of conversations, and again, a similar effort to make sure that DOE, our people, our resources remain central to major efforts like NAIR when they're going forward. And we've been actively engaging in this conversation.
Thank you. Thanks, Dan.
Sure, Valerie. Any other questions? All right, well, I know your time is valuable. You have lots of things going on, so appreciate you being willing to drop in and chat with us for a few minutes. Obviously, welcome to stay as long as you'd like.
Oh, good. Thank you.
All right, we'll move on to the next item in the agenda, which is ASCAC research priorities, and Hal Finkel is going to give us an update. So Hal, over to you.
Okay, Dan, thank you very much. And I'm going to try and share my screen here. Slides. So please let me know if you can see the
we can
cover slide.
Yep.
Very good. Okay, awesome. Okay. Good. So thank you very much, everyone. So I'm Hal Finkel. I'm currently the acting division director for research in ASCAC, and I'm going to be providing a presentation on ASCAC research priorities. And I'm going to try to structure this presentation in a somewhat novel way. The idea is to try and give everyone a feel for the portfolio, kind of the way that I see it. So I'm not just going to talk about things that we did this year, but there's going to be a little bit of retrospective to it so that everything hopefully fits together and people can see more of the puzzle and how the pieces complement each other as we go forward. So let me start. If PowerPoint will let me, good. On this slide, which many of you have probably seen before, but this slide, it really represents this categorization of the trends, the technology trends that are motivating our research program. And what I'm going to do is I'm going to go through each of these trends. I'm going to talk about ways in which we've engaged with the research community to gather input, to set priorities. Then we're going to touch briefly on sort of what we've done in these areas over the past couple of years. And then we're going to talk about what we did this year. And then I'll have some announcements at the end. So that's how I'm going to structure things for this presentation. And then let me say, I'm also going to go through these categories in no particular order. So all of these trends are really important and heavily influence the way that we think about the research priorities that are important for the missions of the Office of Science and for DOE more broadly. So first, this, as we all know, is a challenging time for the computing technology industry because the trends that we relied on for so long, Moore's Law and Dennard scaling and the rest have changed. They've slowed, perhaps. I mean, some people have said that Moore's Law has ended. I think the situation, of course, is complicated. And there are a lot of advancements that are happening all the time in terms of microelectronics technologies and packaging and algorithms and architectures and everything else. But regardless, there are a lot of really interesting research challenges that we need to tackle. And so we have engaged with the research community, in the past couple of years. There was a workshop back in 2021, which I had the privilege of telling this committee about some time ago. We did a couple of things this year in this space as well, focused in the quantum computing area. There is a workshop that happened just in this past July on basic research needs for quantum computing and networking. That was a really successful workshop from our perspective. It really engaged the community. The program committee, the organizing committee for that workshop is now hard at work, kind of consolidating input and drafting priority research directions and the report and so on. So I expect that we'll be back here with a presentation at a future meeting about that. And then also we had a roundtable that I'll mention just briefly that was joint with NIH on quantum computing for biomedical, computational, and data sciences in March, which was also quite informative on our thinking, and I think NIH's thinking in that space. And so, over the past, couple of years, this has certainly been an area that we've been looking at quite closely, as one might imagine. We've had a number of targeted solicitations, focused on new advanced computing technologies and paradigms. This included work in quantum networking. It includes, of course, our microelectronics co-design portfolio that we also started in 2021. There were a number of topics in the past year's Express calls that did focus in this area as well, specifically looking at quantum computing and algorithms and at quantum edge computing, which is a really exciting area that we had the opportunity to make some seed investments in. And so, as you can see, I mean, this is something that we've been obviously thinking about for quite some time, and is something that really must continue. So, so this year, okay. And so this year, we had the opportunity to have a number of solicitations and those awards that are in this space that are relevant. So first, we have a program that we call Accelerate. And Accelerate is a really interesting program. It focuses on basic research that really helps accelerate the transition of innovative new technology innovations into a kind of more commercially relevant or scaled up space. And these are larger awards, and we had an opportunity to make two of them, and they're kind of in two different categories. So I've listed one here, and then you'll see later this is listed again with the other. This award that I'm calling out here is led by TJ Lab, and it's a project that develops a novel kind of superconducting microelectronics that will achieve ultra-high energy efficiency computing. Nuclear physics is also providing some funding for this award. So we're really excited about that. And then also in Express, so Express is our solicitation vehicle for funding high-risk, high-reward, shorter-term projects. And we had two topic areas, I should say, in this space in Express this year. One is on modeling future supercomputing systems. And we funded 4 projects in this area. And it includes projects that are also focused on modeling advanced cryogenic and photonic systems for beyond exascale, kind of beyond more computing. We're really excited about those. And also, we had a topic on programming techniques for computational physical systems. So in this area, we also funded 4 projects. And they focus on exploring the fundamentals of analog computation, the computer science of analog computation, which is an underexplored area, and for microelectronic and chemical systems, which will enable, hopefully, a next generation of computing and storage technologies. So this is a very active area for us, and we're making a lot of investments that are seed investments so that we can hopefully grow this area in the future. We have in addition, under Express, there was a topic on quantum algorithms. And there we funded 7 projects, which includes projects that look at fundamental techniques for converting between kind of different quantum computing paradigms, including between quantum circuits and dynamic quantum walks, and then mapping those things onto different kinds of quantum computers. That's a very interesting area. We had the Quantum Testbed Pathfinder program. Under that solicitation, we funded 6 projects. These explore the limitations of noisy intermediate scale quantum processors that are available today, and then develop tools to assess whether particular kinds of quantum processors can advance the forefront of computational science, even in the absence of formal error correction capabilities. And then finally, we also had a solicitation on scientific enablers of scalable quantum communications. So this is a quantum networking investment. We funded here 3 teams. There's one led by Argonne National Laboratory. There's a team led by Oak Ridge National Laboratory, and then a team led by Fermilab. And all of these teams are exploring different aspects of quantum networking, quantum entanglement, and how you can kind of scale up these systems to be useful for various kinds of scientific uses. Okay. So the next theme I'll talk about is data. Of course, science doesn't happen without data. So this is a really essential part of our overall strategy, realizing that modern scientific simulations and experiments now routinely generate petabytes of data. So this is obviously a key challenge. Not only managing all of that data, making it fair, findable, accessible, reusable, and then understanding how you can analyze it and process it on the other end. So, in the recent past, we had 2 workshops. One was on the management and storage of scientific data. Another one on basic research needs for visualization, scientific discovery, and decision-making. So between visualization and data management, we were able to have solicitations last year in this area. And in addition, we had a solicitation on data reduction for science. So, as you're likely aware, it's really, really hard to deal with many, many petabytes of data or more, to transmit it, to analyze it, and the like. And so we really have to make fundamental advancements in the way that we represent data. We were able to start projects in that area last year, as well as in data management and storage, and as well in data visualization. And all of these things, of course, are important for science broadly, but very essential to our ability as well to advance artificial intelligence-based technologies for science. And I will draw everyone's attention to the testimony that our Deputy Secretary gave to the US Senate quite recently, where he made this particular point about the how essential data is to enabling AI and AI for science. And he points out that the advantages of AI and machine learning can only be unlocked through powerful computing capabilities and commensurate amounts of good data. And so our ability to generate that data, to store that data, to make use of that data for simulations and for analysis, to visualize that data, all of those things are absolutely essential as we move forward. And one other thing I'll point out is as I go through these slides, I've tagged a lot of these slides for areas where our new investments here are leveraging and building on investments that happened under the Exascale Computing project, which really laid a critical foundation for enabling work in almost all of these spaces. Okay, so the next theme here is exploding software complexity, which really is one facet of the challenges that need to be addressed in order to enhance scientific programming. We have to, we realize, of course, that scientific programming has become increasingly complicated, as has all programming in a sense, as computing technology has become complicated. But it's particularly poignant for scientists working on high performance computing because they're so concerned about performance, because the systems have heterogeneous properties, distributed properties, which make them quite difficult to deal with. Plus, as we all know, dealing with numerics is not easy. And so, understanding how all of these things come together is really key. I'm going to call out just sort of two community activities that we've had in this space relatively recently. So one is we had a workshop on the science of scientific software development and use. That was back in December of 2021. The report is now available. And also, we had a joint NSF-DOE workshop on correctness in scientific computing just this past June at FCRC. The report for that should be forthcoming. And this is a really good opportunity to bring together the DOE and NSF communities working on correctness in scientific computing. And I'm really excited to see what happens as a result of that community convergence. Okay. So, in the past couple of years, we have had a couple of solicitations that really speak to this area. So our kind of flagship program in this space is Exascale. We had a solicitation for that back in 2021, covering portability, performance portability for scientific computation, and also testing and correctness. So those two areas were represented in the 2021 solicitation. In 2022, last year, in Express, we had a topic on differentiable programming. And we realized that these areas are also quite essential, not only for scientific programming broadly, but also, again, when we look at how we are going to innovate in the artificial intelligence space, realizing that as we leverage artificial intelligence, well, we need to be able to couple AI training with modeling and simulation. And differential programming is a really key technique that enables that coupling. And B, of course, as we look at artificial intelligence-based tools to generate source code to help with programmer and scientific productivity, being able to test and verify what's coming out of the artificial intelligence-based systems is going to be critical. So all of those things are really critical to this overall space. All right. Good. All right. So our next theme is scientific computing and networking from exascale to the edge. So I've grouped a bunch of things into here. So obviously exascale is extremely important. We've talked about themes around the integrated research infrastructure, how scientific computing happens at the exascale, it happens in data centers, it happens at the edge, it happens everywhere in between. And taking advantage of that, launching the exascale era, now that we have exascale computers and really taking advantage of them is absolutely critical to our scientific enterprise. And so I'll call it just a couple of things, some of which, of course, you've seen. There's an integrated research infrastructure architecture blueprint now that has been published. There was a biopreparedness and response roundtable in March of 2022. The report for that is also available. And then we had the roundtable on parallel discrete event simulation. Again, looking at ways that a wide variety of different kinds of use cases can take advantage of large-scale computing. And all of these things really speak to these themes of the integrated research infrastructure of edge to HPC, of edge to exascale computing. And so, we've been, of course, focused on this quite a bit over the past couple of years. We had a number of past solicitations in this area that are relevant. And this spans the space from research in advanced wireless for science. Of course, we had CIDAC partnerships with Basic Energy Sciences. We had the ICDI, the Integrated Computational and Data Infrastructure portfolio that was launched in 2021, looking at how you take advantage of large-scale computing and advancing algorithms in that space. There was a solicitation on randomized algorithms for extreme scale science, CIDAC partnerships on Earth system modeling with nuclear energy. with high energy physics. We had a call last year on advanced computer modeling for epidemiology and biopreparedness and response. SIDAC programs in partnership with nuclear physics. We had a MIMICS center, a mathematical multifaceted integrated capability center call last year, and also randomized algorithms for combinatorial scientific computing as well last year. And we had in last year's Express solicitation this parallel discrete event simulation topic, which explored a number of different really interesting areas. I don't really have time to discuss all of the past things, so I'll talk about what we did this year. And but I will first start by saying that a huge portion of what we did this year, and really speaking to this theme, speaking to how we're going to leverage investments that we made through the Exascale Computing project in the future, is captured within the Earthshots portfolio. We have Earthshots centers and also the Science Foundations for Energy Earthshots, which is a solicitation that had university leads or other organizations, but not lab leads. And unfortunately, the announcements for those are not out yet, but they are expected this fiscal year, so hang tight. And then we'll be able to say more about that. But I can tell you that there are many projects within this overall portfolio space that build on ECP investments in a really, really key way. And in addition, we did have a solicitation this year on biopreparedness. And if it's under what we're calling the BRAVE initiative. And there were 4 Oscar-funded projects that came out of this effort, which includes awards to Lawrence Berkeley National Laboratory and Oak Ridge National Laboratory to examine diverse data streams using DOE computational capabilities and AI tools to accurately detect the onset of emerging pandemics and help enable decision makers, in both healthcare and policymaking in those spaces. And this portfolio also includes co-funding from BES and BER. All right. We had a solicitation called Advanced Scientific Computing Research for DOE User Facilities. This resulted in 2 projects that Oscar is funding. There's a Center for Advanced Mathematics for Energy Research Applications, which is led by Lawrence Berkeley National Laboratory to develop algorithm software and autonomous workflows, real-time analysis for next-generation scientific user facilities, and also a research project led by Argonne National Laboratory that addresses technical challenges and tools needed to enhance optimization, prediction, and experimentation. This is a space where I'll call it the other award that came out of the Accelerate portfolio. This is an award led by Argonne National Laboratory that leads a project to develop an innovative edge robotics visualization capability using digital twins to really advance the way that isotope production can be used and other similar activities. And this is co-funded with DOE's isotope program. All right. And finally, we had a solicitation in distributed resilient systems. So this is a kind of core computer science investment in enabling the kinds of workflows and systems that you need for the integrated research infrastructure. We funded 5 projects. These include a collaboration led by the University of Southern California for novel methods in swarm intelligence for distributed resource allocation, very interesting algorithmic project. And then also a collaboration led by the University of California, Merced, improving our understanding of scalable federated privacy-preserving machine learning. And we also had a SIDAC partnership call with the Fusion Energy Sciences program, which led to 12 projects co-funded by FES, which will use computational modeling and resources to look at plasmas, study turbulence, and use AI. All right, the last theme I want to call out is artificial intelligence. And this, of course, is an extremely important area, which has a lot of focus and attention, which is well-deserved at this stage. And so I'll just call out a couple of things that we did in the recent past. So one is there was a solicitation 2021 that specifically focused on privacy-preserving artificial intelligence research as part of an aligned investment with NIH. There was a call for data-intensive scientific machine learning and analysis, federated machine learning as part of Express in 2022, and also explainable AI is expressed in 2022. Near the end of this presentation, I'll show you some research highlights that came out of some of these investments. For this year, we did have a call that had a very robust response on scientific machine learning for complex systems. We funded 4 projects. Here I've highlighted 3 of them. There's a collaboration led by PNNL, partnering with Spelman College for quantifying uncertainties and improving predictions for atmospheric simulations and measurements in similar systems. There's a project led by Johns Hopkins University, looking at the properties and behavior of systems that are relevant to additive manufacturing. And then a project led by Lawrence Berkeley National Laboratory to develop a new generation of uncertainty quantification tools to ensure optimal operation and accurate predictions for accelerators and reactors and many other systems. And this is really building on ECP investments as well. There is, of course, a number of sets of initiatives and solicitations which cross all of these themes and are really applicable to everything. So I'll talk very briefly about some here. We have, of course, a huge emphasis on growing and diversifying our research community. We've had a number of really interesting awards here as part of our early career research program, as part of our FAIR set of projects. We funded, I should say, we funded 10 projects as part of the early career research program. I won't read the topics here, but you can look at them on the slide. Under FAIR, we funded 5 projects, which focus on everything from machine learning and surrogates to performance modeling to computational storage and asynchronous I/O and quantum computing. And then 2 really exciting awards from a workforce development standpoint under Renew, which focus on innovative workforce development methods. One project for QIS and another one for artificial intelligence. And both of these projects involve many different institutions. They're very large collaborations. We're really excited to see what happens there. We have, of course, our small business investments, which are a really important part of our overall strategy of enabling technology transfer and building capability within the overall ecosystem, but of course is also relevant to our community. And I'm not going to really highlight any particular investments here, but I will say that I've listed here the phase 1s and the phase 2s on the next slide. And you can see even from the titles of these projects that many of them leverage ECP investments, and many more of them leverage ECP investments, even though that's not obvious from the titles, because they are incorporating technologies developed by ECP into their commercial products and services. And this is a really important way that we can help support the small business community. These are the phase 1 awards. And here I have the list of phase 2 awards. Again, from E4S to all of the other sort of specific technologies that are mentioned, there are lots of ways in which these projects are leveraging the investments that we made under the Exascale Computing project. Okay. Just quickly, just a couple of logistical and other announcements. So first, I did give a brief summary of the different awards that were made under the different solicitations. People have asked us, how do I find the full list? In part because on our website, the place where they are posted has changed. So here you go. If you're trying to find the award list now for our research targeted solicitations, you have to go to the website, and then you have to go to funding and click on where it says topical funding opportunity awards. And there you'll be able to find the award list for all of the Office of Science solicitations. That's different from where it was in previous years. So if you're looking for them, that's where they are. And also, of course, I encourage everyone, if you're not already, to subscribe to our GovDelivery email service. There's a link on the website that will allow you to do that. Okay. For next year, I want to say a couple of things about anticipated solicitations. We first, as you well know, we had a lot of targeted solicitations that came out this year. I think we had more independent targeted solicitations this year than we've had at any year in the past decade. So this was a huge effort from the entire team. And I'd like to thank everyone on our team and also in the external community for bearing with us as we work through this effort and we're able to get out all of these awards, get all of the reviews done and everything else that was needed in order to make all of this happen. So, thank you very much from me to everyone for that. Compared to this year, for next year, we are expecting to issue a smaller number of larger, more broadly scoped solicitations to drive innovation across the entire research community. In appropriate areas, we are going to expand our strategy of soliciting longer-term projects, and in most areas, encouraging partnerships between DOE national laboratories, academic institutions, and industry. We will continue to seek opportunities to expand the set of institutions represented by our portfolio. But this is not only our responsibility, it really is a responsibility for the entire community. And so we really encourage the entire community to kind of walk with us in this hand in hand and assist us in this process by actively exploring potential collaborations with a diverse set of potential partners when you're considering responding to solicitations. And finally, with the caveat that, of course, we don't know what our budget looks like yet, and also with the caveat that it's impossible to call out every area of interest that is going to appear in a solicitation, especially as we look at broader focus for solicitations. I do, however, want to list some areas, especially to reassure researchers working in these areas right now that we do value the work that they're doing. We value the work of the research community in these areas and do intend to continue supporting work in these important areas. So with that having been said, areas of interest include, but are not limited to, applied mathematics and computer science basic research in quantum computing, covering the full stack. The same for AI for science, which includes everything from foundation models and decision support for complex systems, privacy-preserving federated AI systems, digital twins, and scientific programming. It includes microelectronics, co-design efforts from devices, systems, architectures, algorithms, and software. It includes correctness for scientific computing, data reduction, visualization, the parallel discrete event simulation, neuromorphic computing, and advanced wireless. And it includes all of the absolutely essential work that goes into making the scientific software ecosystem, to enabling community participation in exascale innovation, to enable the adoption of AI technologies, and accelerate research productivity. I have the pleasure of making a personnel announcement as well, which is that ASCAC has welcomed. It welcomes and has welcomed Todd Munson. Todd is now on part-time detail from Argonne National Laboratory. Todd is a well-respected researcher within our community. He received his PhD from the University of Wisconsin-Madison in 2000. And he's a senior computational scientist at Argonne National Laboratory. He's a deputy director for the ECP CODAR Co-Design Center and a lead developer of Tau. And if you want to know more about Todd, you can see his Argonne profile. But he's been very, very valuable in contributing thoughts and ideas in helping us organize internally in ASCAC as he joined us some months ago. And so it's with my pleasure that we welcome him. Okay. In my last remaining few minutes, I'm going to give you highlights. I chose in this particular context to focus highlights on a theme. So I'm going to give you some spectrum of work that sits in the space of trustworthy and efficient AI. And this is obviously a really strategically important theme for us right now. And so I want to give everyone an idea of the kind of investments that we are already making, the work that's already going on within Oscar's research community, looking at trustworthy and efficient artificial intelligence. So first, there is, so this highlight is on scalable transformers on frontier for real-time experimental steering. So really there are two reasons why this is key. So first, this is an example of great work on looking at innovative AI techniques, advancing the forefront of AI, of deep learning, of transformer models in a scalable way. They're running on frontier. They're scaling up to very large numbers of GPUs. They demonstrated scaling up to 4,608 GPUs, and also are doing so in a way that is trusted by the scientists, and really is going to enable, you know, advanced and enhanced scientific capabilities in this space by coupling AI and the kind of cross-cutting themes of the integrated research infrastructure. Next, I also will congratulate this team from Oak Ridge. They won an R&D 100 award this year for Super Neuro, which is a GPU-enabled simulation framework for neuromorphic computing. And of course, neuromorphic computing is a really exciting area because it's a very promising way of getting very energy efficient artificial intelligence. But of course, in order to design such a system for doing energy efficient artificial intelligence, you have to be able to iterate, you have to be able to co-design, you have to be able to do all those things. And these kind of simulators are really essential in that work. Next, I want to call out this work at Argonne National Laboratory. It's led by Argonne National Laboratory on privacy preserving federated machine learning. They have a framework, the APPFL framework, and they've packaged all of this up as a service. And this is really an important aspect of how we see the future enabling, as we see AI enabling the future scientific capabilities. And really, I see this on a spectrum. So, you know, we have integrated research infrastructure. We have, in many cases, the need to move data around between facilities. We also recognize that there are some times when you have to model using data that you might not be able to move, that needs to stay federated, that you might not be able to have access to universally because it has privacy, there are privacy concerns with that. Maybe it's health data that has human health privacy considerations that are attached to it. But maybe it's proprietary data from a company who's working on some kind of microelectronics technology or the energy grid or nuclear energy. And you need to be able to enable science using that pristine data, but not everyone can have access to it. And so having these privacy preserving and federated machine learning technologies is an essential part of helping to enable those kinds of workflows. All right. There's also, you know, in enabling trustworthy AI, a lot of fundamental work that's going on to understand when you can and can't trust these systems and precisely what they do. And so here I'll call out work that's being led by SLAC in collaboration with Stanford University. They did some really interesting fundamental work to understand where and for what kinds of models the automated differentiation technique that's very commonly used by all of the big machine learning toolkits actually works from a numerical stability standpoint. And are there kinds of models that tend to be more stable than others when you apply these kinds of important techniques? And interestingly, I discovered that the answer is yes. There are certain kinds of AI architectures that tend to give you more numerical stability when you apply automated differentiation. So this kind of work is really important when we start doing artificial intelligence for high consequence systems and need to understand how things work. I also would like to call out this work from Aditya at the University of California, Davis. Again, this is work that is enabling kind of deep interrogation of deep neural networks and understanding exactly how you can understand what they will do, not just on a small sample of points, but in a larger, more comprehensive way understanding their behavior, and then understanding how you can modify that behavior if the behavior of the network is not precisely what you would like. And finally, I know everyone is very excited about the possibility of using large language models. We see what they do in general use cases now, and there's a lot of interest in using them for science. And so here I'm going to call out some very recent work that is part of our portfolio on explainable AI from University of Central Florida and Florida International University, where they're looking at the use of large language models and looking at how you can take their output, understanding that sometimes the models produce output that just isn't plausible or isn't right, and then combining that output with logic solvers, with symbolic techniques about which we can reason about correctness, and then integrating these things together so that it's possible to provide feedback to the AI systems and thus enable, in this case, this large language model-based system in order to generate plans that have physical plausibility to them. And this kind of capability is going to be very important as we look toward the future of AI-enabled infrastructure, of automated laboratories, and accelerating science more generally. All right, so I think that's the end of my presentation. So I may have a time for some questions.
Thanks, Hal. Yeah, there's a whole queue of folks. So first in order, and these are not all, but we'll start with these three in order: Gil, then Susan, and then Jill.
And Dan, they wanted me to let the members of the public know that they can type their questions into the Q&A.
Okay.
Thank you.
Great. Nice talk, Hal. I really resonated with the Exascale to Edge. There's a great synergy between the two, and I often use the SANDAC computer as a really, really early pioneer for multiprocessor architectures. But you said something early on that confused me a bit, where you talked about quantum at the edge, and what you said that language, but what I heard was quantum as a coprocessor. So could you kind of fill me in a little bit more detail on what you meant when you said quantum at the edge? Because like I say, I heard quantum as a coprocessor, which I don't consider that to really be edge computing. Over.
Oh, sure. So the portfolio about quantum computing at the edge is looking at how you have quantum computational properties in edge quantum systems. So, I mean, that's, starting with quantum data coming from quantum sensors, how you might embed kind of quantum computation directly as part of that sensing and kind of processing process. Obviously, there are all sorts of trade-offs there, right? Because, at the real quantum edge, things are noisy, right? So, because that's where you're interacting with the world. And so as you kind of back away from that and figure out how you're going to integrate quantum data and quantum processing, there's a lot of interesting overlaps there, not only with computation, but also with quantum networking and quantum sensing. So it's really something that kind of sits at the boundary of all of those topics.
Yeah, thanks a lot. That clarifies my confusion.
Sure.
Hi, Dan, I think I'm next. And Gilbert, you pretty much asked my question, which was exactly that. As you know, NIH is interested in quantum computing, both in quantum calculations, but also in the integration of quantum and sensing. So I don't know if you want to add anything else. I know that you're aware of our interest. So I was also interested in what you had meant by quantum at the edge and where you saw the role of quantum in DOE and where it was going. You may not have anything additional to add at this time.
Yeah, I don't have much additional to add, but I will say that, between, computing and networking and sensing, all of these areas are important broadly to the mission of the Office of Science. And I think to NIH and to other agencies that are really, looking at this opportunity space. And as you know, Susan, we also had this roundtable between NIH and DOE, which I think was useful in kind of elaborating use cases and understanding where opportunities are as well. So
absolutely, we absolutely look forward to following up in our next fiscal year on pushing that roundtable and some of those ideas forward. So really appreciate your time and effort on that roundtable.
Yeah, great, thank you.
All right, as soon as that fiscal year starts, whenever that may be. Jill?
I actually don't have any additional questions, Dan, but thanks for giving me the opportunity.
Oh, I thought you did. Okay.
No, mine was a technical question to you.
Oh, I'm sorry. Okay.
That's
All right.
okay.
Vivek?
Yes. So Hal, thank you so much for the overview. I know that our research community is really excited by all the vitality that we now have again in OSCAR in the research programs that you mentioned. One topic that I saw that came up in a few different programs, including Extract, Express, related to programming of scientific applications and new directions. So a lot of exciting opportunities there. I was wondering about your thoughts on how to transition those research ideas or decide which research ideas are amenable to transition after the research is done. And I know in our community, we have a long history of doing that kind of thing, whether or not in the scope of programs. I mean, a lot of the programming techniques we use came out of research ideas. And so I was just wondering your thoughts, whether there's opportunities to collaborate with facilities over there or any other approaches for transition.
Yeah, I think that, two things. So one is, of course, this kind of decision making is not completely top down. In fact, in some cases, it really has to be bottom up driven, right? People are going to adopt technologies and tools that best suit their needs, and of course, needs evolve, and so that has to be an essential part of the process. We have, of course, folks at the facilities who look at this carefully. We have, our small business community that we provide opportunities to, and this is really kind of this as I transition here. Part of this, right, is that it is bottom up, but also we try to provide opportunities to help enable and facilitate that process. And so we have, as I noted, we have, for instance, our small business awards in this space, which provide some opportunities. We also have a broader set of opportunities looking at our next generation software stack, looking at how we're going to steward the investments that we've made. I didn't say too much about this. Sharon addressed this during her last presentation at ASCAC. We have a set of seed collaborations around software stewardship, around next generation software stack technologies. They're right in this process now of transitioning, so there's not too much I can say at this time, but I think by the time we have the next meeting, there'll be a lot more that we can say in this regard.
Okay, thank you.
Okay, Valerie, did you have a question?
Yes, I do. So
Okay.
thanks, Al, for the valuable presentation. Enjoyed it. So my question relates to the discussion about the anticipated solicitations for 24. And so it's really good to see, looking at solicitations that would be longer term projects. So, want to applaud you for that. My question has to do with you mentioning that some would be more broadly scoped. And so just trying to get an idea of what that means. Is that broadly scoped within OSCAR, in terms of broadly scoped, let's say in applied math or computer science, or broadly scoped going across the Office of Science in that sense? So try to get that understanding of the scope for the broadness.
Yes, thank you. That's a great question. Thanks for asking. So I intended to convey broadly scoped across OSCAR's purview. Now, that having been said, of course, we have a number of very important initiatives across the Office of Science. And OSCAR, may certainly participate, in some of those going forward. But I think, it is important that we have an inclusive posture for our portfolio, and we want to make sure we provide opportunities. And so, across the purview of OSCAR's scope, we'd like to make sure that that's represented to the extent that we can, as we have important, core investment areas to maintain.
Okay, thank you.
Teresa?
Yeah, mine is a little bit related as well, thinking about the cross Office of Science kind of activities. you'd mentioned SIDAC as one of the opportunities that was done in fiscal year 21, I think it was, or 22. And I was just wondering if you had any other thoughts on what's coming up for SIDAC and how that's going to progress and what areas.
Yeah, and it's a really interesting question. So, and I'll say a couple of things. So one is, we have had both in 21 and in 22, and previous to that as well, a number of calls for SIDAC partnerships with different offices. So each of those portfolios is on its schedule, and so we look forward, of course, to what's coming out of those projects. We will continue to explore the opportunities for new partnerships with other offices, with applied energy offices, with other parts of the Office of Science. Obviously, it's constrained by budget, so that's the reality. And then also, of course, the SIDAC institutes, play a really important part in this portfolio, and so when their current award period ends, then that would certainly be something that would likely appear on a list of solicitations. I think there wasn't anything that we had particular to call out for next fiscal year in this regard, just because of the amount of ongoing work and what we anticipate for the budget. But we could be surprised. I'll be happy to be pleasantly surprised, and then we can explore other things to do.
All right, Ed.
Thanks, Dan. Yeah, hi. I have a question, kind of picking up just discussions I hear in the community. There's some concern that with all the rush to AI, which I mean, we all find tremendously exciting, that some traditional simulation and modeling kinds of activities and all the applied math that goes with that and so on is not getting the kind of support that it needs, or you have to do AI in order to get the kind of support. And I just wonder, can you comment a little bit about that a little more broadly?
Yeah, I mean, this is obviously a balance that we all have to strike, because the core areas that we invest in across applied mathematics and computer science, of course, many of these areas apply to AI, right? I mean, optimization and uncertainty quantification and all these things are really essential for AI, but they're essential for other things too. I think one thing that we have to realize is, AI is becoming quite ubiquitous. It's also a very broad topic area. And so we need to make sure that we support it appropriately. We also need to make sure that we do not support it to the detriment of other important core areas. And so this is one of the specific reasons why I tried to caveat this list of areas of interest for next year, because in some sense I could have added a lot more to that list. As I mentioned, we're going to try to have solicitations that are broadly scoped, so to make sure that we're not overly focusing on particular areas to the detriment of others. That having been said, our authorizers and appropriators, also express their interest in us investing heavily in AI, and so this is something that we have to balance. We have to do both.
All right, well, I might ask, we're behind, but I want to try to sweep some of these things together as a theme. Maybe I hope the committee can come back to at the end of the day. So how this is not directly solely at you, it's more of a philosophical question, which is, when there is a period of transition, you need to invest in a lot of areas to surface winning strategies. And so I think we all appreciate the importance of that. The flip side is we are at a major inflection point in computing, and we can all debate about where it's going to go, but it's clear that the past is not going to be the future. So the related sort of strategic question is, how is DOE thinking about that at a strategic level in terms of how it's going to prioritize programs and investments?
Well, I mean, I'll say something very briefly, and then of course, we can, come back to this. One thing I think is really important is that when we think about structuring our portfolios, we think about having a spectrum of risk tolerances, a spectrum of kind of timescale outlooks for impact. And, when we look at the needs for energy efficiency and computing, for computing capabilities, what we see is that there are tremendous opportunities that could be enabled if there were transformative increases in energy efficiency, in computing capabilities, both algorithmic, hardware and software. And so we want to invest to enable those things. When we want to do that without starving the essential investment that's needed in the technologies that are more mature, because the whole research enterprise depends on those technologies today. And so, and it depends, moreover, on innovation that's directly tied to those existing methods and techniques. And so, you know, I think as we look at this, you know, it seems cliche, and I understand, but we really do try to keep a spectrum of investments, and we make sure that we are both looking at high risk, high reward, transformative opportunities, and we are also investing in really innovative work that is advancing the kind of core techniques that we've come to know and love, you know, and in doing that, I hope that we can serve the research enterprise in the best way we can.
All right, like I said, it wasn't just directed at you, it was a philosophical theme I hope we can come back to. So Hal, thanks very much for that thoughtful presentation and for the questions.
Thanks,
We're gonna move on to our next presentation, which is about the Energy Earthshots initiative. And Devin, you've got the floor.
There we go. Double mute. You guys can hear me now and see my screen. Is that right?
Yes, we can.
Fantastic. All right. Well, good morning. And I appreciate the opportunity to share more about the Energy Earthshots. It's a crucial part of our domestic climate agenda. And want to express as well our appreciation for the close partnership we have with the Office of Science. They have been a key player in designing the Energy Earthshot initiative, program staff dedicating time to that, in crafting the individual Energy Earthshots and their targets, as well as conducting the work of implementing the Energy Earthshot initiative. And of course, want to express thank you to the PIs that have been applying to the work that will make up the innovations we need to achieve our ambitious plans. So I work in the Office of the Undersecretary for Science, Innovation. It's our mission to spur innovation and accelerate progress towards our 2030, 2035, and 2050 climate and energy goals through fully integrated science and applied energy research, development, and demonstration within and across key technology domains at the department. And so today I'm speaking of one initiative within our office, which is the Energy Earthshot Initiative. This was spurred at the Climate Summit 2 years ago, where President Biden directed the DOE to speed the development of critical technologies to solve the climate crisis. And Secretary Granholm noted this initiative to being akin to our generation's moonshot. And so the Energy Earthshots were born as an all-hands-on-deck effort to target the remaining major RD&D breakthroughs we know we will need to have ready for commercialization in the next decade to solve the climate crisis and reach our 2050 net zero carbon goals. All hands on deck means a all of DOE initiative, from fundamental basic science to applied work to development and to deployment. And we certainly have to acknowledge that the bipartisan Infrastructure Law and Inflation Reduction Act have since directed and significantly funded the department to add to its traditional mission spaces for that demonstration deployment work. It's a key area for commercialization of these clean energy technologies, and bill alone is the largest investment in DOE history. And yet with that acknowledgement, we know that basic and use-inspired science will always be the seed corn for any commercial technology. And certainly the ambitious energy earthshots that we have today rest on the fundamental and basic research and of the previous decades, and will rely on that continued discovery moving forward. So what the energy earthshots are, they are performance targets in key technology areas. They're technology focused. They establish this cost or performance target in a specific technology space. It is ambitious on a level of a order of a moonshot. It's something that can't be done with business as usual. It's singularly focused on reducing emissions at scale, and it needs to position the U.S. as a central leader of global clean energy trajectory. And this initiative is based off of DOE's successful Sunshot program. It launched in 2011 and helped slash the price of solar energy within the decade. And so the DOE used the Sunshot program as well as expertise within the department, including from the Office of Science, to design what this initiative would be. This is one of the outputs of the designing of the initiative. It's what we call the Energy Earthshot Framework. And it's an expression of the ambition of the initiative, as well as a guide for implementation. I'm not going to go through each of the columns that you see on this slide, but in particular, I would like to draw your attention to the center column, the strategic alignment column, because I'll be referencing that shortly again. So this will speak to how we are aligning our resources, informing our efforts in an all-hands way, and engaging stakeholders for the Energy Earthshot. So I've spoken a bit about the Energy Earthshot initiative, and that each Energy Earthshot is a singular performance target. Can you guys all hear me still? Is my audio still connected? Can I get a thumbs up?
We can hear you.
Okay, sorry, I had an odd sound come through my computer. Okay, so this is the Energy Earthshot portfolio. There have been 7 Energy Earthshots announced so far. We've always said we would have 6 to 8. 3 were announced in 2021, 3 in 2022, and 1 so far in 2023. The Earthshots together span a broad swath of sectors required to decarbonize the economy, and independent analysis has shown that achieving the Energy Earthshots collectively and cumulatively to 2050 can save $850 billion and avoid 3.9 gigatons of emitted CO2. Again, what's kind of critical to share here is that by announcing these Energy Earthshots targets, we're calling for basic research and the applied research communities to become more aware of the challenges that are faced and working together. And we hope by doing this that we can catalyze faster than ever the big science breakthroughs that DOE has been known for. So that was the full portfolio. The Energy Earthshots individually are performance targets that guide the direction of the full department. And so I'll spend a moment stating what the Energy Earthshot target is for these different areas, and then what that means in terms of achieving it. The hydrogen shot, and these are listed in orders that they were announced. So these 3 on the screen are the most mature, the first ones released. So the hydrogen shot has a goal of $1 per kilogram of clean hydrogen within a decade. And we know that cheap, clean hydrogen is a pivotal asset that will enable decarbonization of multiple sectors, such as manufacturing, transportation, and even long duration energy storage. The second Energy Earthshot, long duration storage shot, aims for a 90% cost reduction from a 2020 lithium ion battery baseline for at least 10 hours of storage within a decade. In the upcoming years, we'll see a massive increase of renewable capacity on the grid. And so ubiquitous long duration energy storage will enable clean power anytime, anywhere, as well as create resiliency for people and communities. The third Energy Earthshot announced is carbon negative shot. This Earthshot calls for less than $100 per metric ton of stored CO2 equivalent, with costs measured for the monitoring, reporting, and verification of that removal for at least 100 years and achieving this work again within a decade. These are decadal focused targets. As the IPCC has made abundantly clear, there is no path to 1.5 degrees C that does not feature gigaton scaled carbon dioxide removal as a deployed capacity. And we know that we need to enable progress here to keep that 1.5 alive. Carbon negative shot is, along with all of the Earthshots, are meant to be enabling of multiple pathways. So direct air capture is well known as a solution, but it is also embracing, carbon negative shot is embracing of nature-based pathways, ocean-based carbon dioxide removal. And so these targets are driving for a solution, not prescribing the path to get there. These are the next 4 energy Earthshots. The first 3, geothermal, floating offshore wind, and industrial heat, were announced in 2022, and clean fuels and products was announced this past May. So the enhanced geothermal system shot aims for a 90% cost reduction in geothermal energy from man-made reservoirs to achieving that $45 per megawatt hour by 2050. What achieving this energy Earthshot means is unlocking firm and clean base load power for the grid. This power can supplement the grid at peak times in the evening when the demand spikes and other distributed energy resources are no longer producing power. Floating offshore wind complements enhanced geothermal in terms of opening the capacity of renewable power throughout the country in terms of its geographic distribution. It has a similar goal. This is a 70% cost reduction from a 2022 baseline, but getting to that $45 per megawatt hour objective, hitting that timescale of 2035. That's in line with some of our Clean Power Administration goals. And this Earthshot is focused on creating that capacity to generate power in deep water sites far from shore. The potential here is that currently 2/3 of our area space within our exclusive economic zone for energy production is currently unfeasible. So by driving this, achieving this energy Earthshot opens 2/3 more space for us to generate clean power. The third energy Earthshot goes to our hard to decarbonize sectors. And so it's industrial heat shot. It has an ambitious goal, moonshot level goal of an 85% emissions reduction from industrial processes relative to cost competitive technologies. Industrial heating refers to many methods by which the heat is used to transform materials into useful products. Heat is used to remove moisture, separate chemicals, create steam, treat metals, melt plastics, and much, much more. Industrial heating accounts for about 9% of the entire US emissions footprint. And so what we're talking about with this energy Earthshot, along with the others, but in particular, is a massive change in terms of what we'd be capable of doing. And so industrial heat is where we start going to a space where I like to think we can touch and feel the work. And Clean Fuels and Product Shot helps round that out. So this Earthshot was launched to reduce the negative impacts of GHGs from carbon-based fuels and products that are really critical to our way of life. This shot is focusing on decarbonizing the fuel and chemical industry through alternative sources of carbon to develop cost-effective technologies with a minimum of, again, 85% lower greenhouse gas emissions by that 2035 timescale. And so that is each of the individual energy Earthshots that together makes the portfolio of the initiative. Now, I said when I was on the framework slide that guides the ambition and the profile of the mission, as well assists with implementation. So what does that mean? We focused on that center column that was that strategic alignment column. And we call the Energy Earthshot Initiative an all hands on deck effort. So how do these performance targets drive that? What an individual target does is it focuses all hands of the DOE on that target. And so the individual offices will execute their actions in alignment with it, or at least, yeah. So with resources being aligned, funding opportunities dedicated specifically to the Energy Earthshot, or with awareness to some of the needs of the Energy Earthshot, informed with strategic planning, conducting strategic learning exercises like roundtables to guide the strategy, identify the barriers and the next set of opportunities that are primed for action. And then engage stakeholders, working with the scientific expert community, industry, national labs to learn what the most pressing challenges are there and folding those learnings quickly into the initiative. And that's what that feedback loop is. So that's the feedback loop. What does that look like from the street? A lot of our work in the department, it is a bit like an iceberg. The coordination that we're doing across the department, most folks will not see, but in terms of the tip of the iceberg, what you guys can see, that's what's expressed on this slide right here. So each of the individual Earthshots, so this is specifically for hydrogen shots, and it captures some of the work that has happened, some of the work from June 21 to September 2023. And so you can see for aligning of resources, the Office of Science has announced the Energy Earthshot Research Centers and Science Foundations funding opportunity, and we are all very eager to hear the selections. For the Applied Energy Offices, the Hydrogen and Fuel Cells Technology Office released the Clean Hydrogen Electrolysis, Manufacturing and Recycling funding opportunity announcement. And of course, the other major hydrogen announcement, the United States at the Clean Energy Twitter community is waiting to hear, is the announcements of the regional clean hydrogen hubs. So you can see as an example there how the department, through all different offices in charge of spectrums across the RD&D supply chain, are taking coordinated action to address barriers. The same goes with informed strategic planning, roundtables related to this topic, developing national clean hydrogen strategy and roadmap, and working on what we call these commercial liftoff reports, which is meant to inform the investor community and large-scale operators on what are the challenges and metrics for driving faster deployment. And then, of course, conducting these workshops and doing other creative and innovative work to, again, increase the pace that we're pursuing and achieving breakthroughs. And so what's Oscar's role? What hands do they have in the Energy Earthshot initiative? So you've heard a bit, and I will say as well later, some of the existing projects and fundamental research related to the space. Oscar, you can look in the FY23 and the FY24 budget requests are going to highlight where they're playing a role in the different cross-cutting initiatives across the department, which these Energy Earthshots are currently reported within some cross-cuts. And I just mentioned on the last slide, the Energy Earthshot Research Center lab call, as well as the Science Foundation for Energy Earthshot's funding opportunity announcement. I'll spend a little bit just speaking about them. So the Energy Earthshot Research Centers are going to bring together multi-investigator, multidisciplinary teams to address key basic research challenges for the Earthshots, with an application award focused on one of the Earthshots. And of course, this is going to be very pivotal to advancing the Energy Earthshot initiative. The applications were open to the DOE national laboratories, and they encourage partnerships with other institutions, including academia, other national labs, non-for-profits, industry. The total combined funding for these were up to $200 million for over 4 years, with $50 million in FY23 dollars and funding contingent on congressional appropriations in out years. And the size of each of these individual awards will be between $3 million to $5 million a year. The Science Foundations for Energy Earthshot's funding opportunity is focused on small teams on cross-cutting scientific challenges that address multiple Earthshots. So these awards are small teams, but hitting topics relevant to multiple Earthshots. The applications were open to U.S. colleges and universities, nonprofits, and private sector companies, and of course, encouraging partnerships as well. The planned funding for this was $150 million over 3 years, again with $50 million in fiscal year 23 and out-year funding contingent on congressional appropriations. The funding anticipated for these awards are $50K to $200 million. I'm sorry, $2 million. And so we're looking forward to hearing the announcement of awards for both of these funding opportunities. I will say that part of the portion of the iceberg underwater that I'll share a glimpse with is that the Office of Science has been fantastic at coordinating reviews, input from the applied energy offices through the design of these funding opportunities, the review and selection of these awards. And so it is something that is very valuable to see at what really drives innovation in this space, this close collaboration happening at this high strategic level, all the way down to the nitty-gritty mechanisms of the true innovation work. Okay, and so to round out my presentation, I wanted to highlight some examples of active projects that are relevant to specific energy Earthshots. The first I will highlight is enhanced geothermal. On the resources aligned slide, I mentioned that the offices across the department report their budgets to Crosscuts, and the enhanced geothermal shot is supported by the Subsurface Energy Innovations Crosscut, that budget mechanism. And so the Crosscut budget mechanism, as well as the team, they coordinate on deep subsurface work to advance solutions to common challenges across multiple technology domains. So the group comes together across the department, and they're focused on fundamental work or the work relevant to their offices, but the clean energy applications that are enabled by the coordination are carbon dioxide sequestration, geologic hydrogen storage, critical mineral and material sourcing, and geothermal energy. The common challenges that this group has identified are that new subsurface energy projects are hard to develop due to the limited capacity to assess, monitor, and access the subsurface. Now, exascale computing, artificial intelligence, and machine learning can and are being leveraged to better characterize the subsurface so that exploration projects can become less risky, so that drilling the subsurface can be done faster and more economically, so that we can observe and modify operations below the subsurface in real time to ensure safe economic operation. And with all of these things, increasing the success in modifying the subsurface environments to meet our clean energy demands. Now, one active project in this space is led by Carl Steffel at Lawrence Berkeley National Laboratory, and it has collaborations with Lawrence Livermore National Lab and National Energy Technology Laboratory. The project is titled Subsurface, an Exascale Subsurface Simulator of Coupled Flow, Transport Reactions, and Mechanics. This project focuses on the scientific challenge of overcoming a failure of a well bore for CO2 sequestration in saline reservoirs with consideration of wellbore segments of up to 100 meters in length and times up to 1 year. Now, to put that in comparison for current modeling efforts, it's modeled at much larger scales, on the order of 100 meters to 1 kilometer and at 10 years time. So what this project does is it increases the accuracy of prediction of fracture evolution through microscale resolution of the fractures. That thereby enhances the control of the chemical reactivity and permeability of the space. This capability, there's been a lot of interest recently from the Hill on subsurface work, particularly for critical mineral extraction, for enhanced geothermal. And I cannot express enough the enthusiasm and being able to achieve this higher scale of resolution and what that can enable in terms of live operations from both the Hill and from industry members that we've heard from in terms of the need for work. Many of the Energy Earthshots benefit from ASCA's capabilities. The next one that I will highlight is floating offshore wind. For this Energy Earthshot, the areas of emphasis for the initiative are on cost reductions through improved siting, improved turbine performance, and improved installation, operation, and maintenance. Another area of work includes expanding deployment, which involves sharing data and tools to support the delineation of additional deep water lease areas and transmission development with an eye on ensuring a cybersecure, reliable, and resilient grid. Projects within the Exascale Computing project are developing capabilities that will advance floating offshore wind shot, as well as wind energy writ large. So Exascale Computing provides researchers and engineers with the computing power to model operational control, optimal siting, and reliable integration within the power grid for wind energy at scales that are simply intractable at pre-exascale era. To give more color to that challenge, wind turbines are the largest rotating machines in the world. Offshore wind turbines can have blades that are more than 100 meters long with a 240-yard rotor emitting 12 megawatts of power. That's enough power for a small town. The airflow boundary layer around the blades is extremely thin at only a few microns wide. So the wind farms themselves can span, and in addition to that, a wind farm itself can span over 10 miles. So the dynamics range of scale we're speaking at is huge. Predicting the fluid dynamics within this operation, it requires resolving the giant difference at scale. And so supercomputing is essential to this extreme simulation. To put another example on it, simulating a wind farm with 15 turbines that produce 5 megawatts each would require a model with at least 20 billion grid points. And so this is the type of challenge that's fit for frontier. So for a project that's in this space, there we go. Got that. Michael Sprague is the Chief Wind Computational Scientist at the National Renewable Energy Laboratory, and he's Principal Investigator for ECP's ExaWind subproject. One thing that is very impressive, maybe this is common across your awards, I'm from the Applied Energy Office space originally, but just reading that the project has more than 50 collaborators, and again, bringing multiple national labs together is something that to me feels noteworthy. And so the ExaWind team established a new suite of software for Frontier, and they're working with the Wind Energy Technologies Office, a DOE office, to validate ExaWind by simulating a real 2 megawatt turbine with an 80-meter rotor. And so this is going to allow the researchers to compare the data from their model against real field measurements, to the point of needing to drive increased deployment. Being able to have these models be verified by real data then can create one, knowledge to drive innovation on how we can have improvements there, but two, help quantify risk for project developers, which is an absolute certainty we need to have to drive deployment at a faster rate. So I want to applaud the work that's happening here as a critical enabler. And why this is really front of mind for me, this week I was attending a conference called Deploy 23. It was the inaugural conference. It was organized by the Clean Tech Leaders Climate Forum with a significant partnership from the DOE Loans Program Office. The central message of this conference was that the clean energy transition must be industry-led and government-enabled. And a quote I took down in my notebook from the forum chair, the Clean Tech Leaders Climate Forum chair, was with AI-inspired research, change will accelerate faster than ever before. AI is a buzzword, right? But supercomputing, the capabilities that rest within ASCAC are going to help drive change faster than ever before, and we need it. We need it. We're counting down the years to our energy Earthshots being completed. We're 12 years from our clean energy, clean electricity goals, and we're 27 years from 2050. It took about, I think, a little over 25 years to get solar deployed to the space that it is. We need to move faster. And so the last Earthshot that I will highlight is the Clean Fuels and Products shot, and was so inspired reading up on this achievement. So bridging the gap again between breakthroughs in the lab and commercial scale operation, it's critical to the establishment, in this case for biorefineries, that can replace the production of fossil-based petrochemicals and help decarbonize the US economy. So a recent achievement was startup firm Pyran scaling their technology 1,000 times over in a single step. And so this was achieved through working with the Consortium for Computational Physics and Chemistry, the CPP. It's led by Oak Ridge and the Department of DOE's Office of Energy Efficiency and Renewable Energy, so one of the applied energy offices, and their sub-office, the Bioenergy Technologies Office. I share this because this is a capability enabled by the Office of Science, and so what others are doing, building off of what you guys are leading. So this consortium leverages modeling and simulation capabilities at the national labs to help bioenergy companies resolve technical roadblocks to deployment. So this program paired Pyran with modelers from the chemical process scale-up group at Oak Ridge to suggest improvements to Pyran's process for creating biomass-based 1,5-pentanediol, chemical that's specifically used to make paints, adhesives, and other products. And so Oak Ridge scientists took data from the lab scale reactor using approximately 60 grams of catalyst and analyzed aspects of the process and suggested modifications to the scale up. The resulting pilot scale reactor used 62 kilograms of catalyst to create multi-ton quantities of the immediate precursor to pentanediol. And the end product will go to companies for testing in the manufacture and consumer goods. This is remarkable. And it's something that I hope to read more and more for other companies, just taking advantage of the capabilities that have been developed through the fundamental sciences and at the national labs. And so brings me hope for what we must do for a better future for all. And so I just want to kind of conclude my presentation to say that the challenge that we face is great. And we know from our long-term strategy that it is achievable, that the challenge requires all hands on deck from fearless innovators. And I appreciate the opportunity of speaking with you all and ask what are the opportunity spaces for ASCAC and the Energy Earthshots and this all hands on deck effort. Thank you.
All right, thank you. Questions? Well, I'll ask one just quickly. As you think about how much computing is shifting, and obviously the enormous pressures on trying to move forward with renewables, how do you think that combination of things will play out, given that we're uncertain about exactly where computing is going to go in a time frame that many of these objectives need to be met?
I have a few different thoughts. In terms of the direction of computing alone, as we all pivot to greater software capabilities, we're requiring more GHGs from our compute power. So the need for increasing efficiency in computing alone is going to be a critical space. I think in its interaction with the grid, one of our crosscuts in our office is the Grid Modernization Initiative, which is thinking about this interplay. One thing that they were focused on was introducing quantum computing into their most recent lab call so that they could start developing capabilities again on making computing more efficient. I think that thinking about grid integration is very critical. Some of the in industry conversations, several leading tech companies have stated publicly that they have 24/7 clean power objectives. So to have that, you will either need to have long duration energy storage enable or clean firm power. Both of these things pointing to importance and innovations in these spaces, but also a willingness to purchase clean power at a higher price. And so it's that community that might actually be some of the early movers for the deployment of next generation geothermal or alternative long duration energy storage capabilities. And so as a user of energy, you guys are right in the center of the mix, I guess, of both solutions as well as solutions and innovation and solutions in terms of the need for early deployment.
All right, great. Any other questions? Well, I very much appreciate you coming to talk to us about these critical problems, and as you said, the interplay of both the modeling, but also as high performance computing being a semi-insatiable demand for energy as well. So thank you. Next up is a different take on applications computing, opportunities and challenges for digital twins. And Michelle is joining us to represent the National Academies.
Hello, thank you all so much for inviting me. Just to kick off, I'm here to give a bit of a teaser for an upcoming study or for an upcoming report that the National Academies will be issuing that's partially funded by ASCAC. So first off, hello everyone, I'm Michelle Schwalbe. I run our board on mathematical sciences and analytics and also oversee all the manufacturing and material science work at the academies. So starting off, because the National Academies is a chronically confusing organization. So we are a nonprofit, nonpartisan, non-governmental organization that largely works to help provide some high quality and objective advice to the federal government and to research communities. So we play a bit of a translational role between research communities and policymakers who should be engaging more with them. And because everybody loves a good org chart right around lunchtime, I did just want to give a little bit of an overview of how we're structured, because I am going to be referring to some of the different parts as if you all know them. So within the National Academies umbrella, we have 3 honorary societies. We have the National Academy of Sciences, National Academy of Engineering, and National Academy of Medicine. And then we have a larger policy-oriented wing that used to be referred to as the National Research Council, if that sounds at all familiar. But basically, we're structured kind of like an academic institution where we have divisions that roughly correlate with colleges within a university, and then boards or committees that are similar to like a department within a university. So I'm with our board on mathematical sciences and analytics, which lives within our engineering and physical sciences division. None of this is particularly relevant, except to say that a lot of the groups around the National Academies are involved in this digital twin study. So just to pop into the chat box, I'm going to put the link to our project page in case anybody wants to look through some of the materials as we go. But basically, as we start, we're conducting the study on the foundational research gaps of digital twins. One of the first questions that I usually get asked is, well, what the heck is a digital twin and what do we mean by this? And one of the things that's been particularly striking through the course of the study is that there are so many different definitions and interpretations of what a digital twin means. I tend to think of them, or I like this particular definition by the American Institute of Aeronautics and Astronautics that calls for a digital twin, refers to a digital twin as a set of virtual information constructs that mimics the structure, context, and behavior of an individual or unique physical asset or a group of physical assets, and is dynamically updated with data from its physical twin throughout its life cycle and informs decisions that realize value. So what does that actually mean? So I interpret this as we have a physical entity, we have a set of models, we need them to talk to each other. So there's a continuous or a continued feedback cycle, and both continue to get updated, and then that information is used to inform decision making. In practice, what this looks like is very, very different by communities. So some of the early examples of digital twins were in the aviation space, where a digital twin was being created of a physical airplane. And then that airplane was creating data, which was being fed back into the models. The models were helping to recommend when particular maintenance or other activities were happening with a particular airplane. That maintenance happened, more data was created, it goes back into the model, that type of cycle. Where things get really interesting is when we go into these different communities, we're seeing a lot of great examples and opportunities for digital twins outside of some of these more traditional engineering spaces. So one example that we've heard a lot of through the course of the study is in biomedical applications. So using digital twins as a way of tailoring and helping inform patient care. So using some of the biomedical models that the communities have, using those to help predict a particular treatment path or provide options for an individual. And similarly, we see some of these applications in virtual clinical trials and in a number of other domains as well. So I'll talk a little bit more about what those domains are and what we mean by them. But maybe then going back to the specific study that we are doing. So in thinking about all of the different ways that we are hearing digital twins talked about across industry and academia and through these different communities, we wanted to take a more foundational research perspective towards digital twins and pull together a group of experts who could help us really think through how are some of the digital twins defined across communities. Is there a single definition that we could be leaning on so that things aren't so community specific? We also wanted some guidance on some of the foundational gaps or opportunities for digital twins and how those vary across some of our different application spaces. And then also looking for promising practices. So some communities are much further along in their digital twin journey, and some have a lot of enthusiasm, but are still trying to figure out really where to go from it or with it. And so we're looking to pull together some of these best or promising practices across domains and really provide some guidance that can cut across communities. And similarly, we're looking for opportunities for translation of best practices. We're also looking for use cases that can advance the awareness of and confidence in digital twins. And then looking at some of the key challenges and opportunities in the research and development space to advance digital twins. So I had mentioned in the beginning that OSCAR is partially funding this study. We are very fortunate to have a cross-agency funding base for this. So we have DOE, NIH, NSF, and DoD all engaged. This is pretty unusual for the national academies. For those of you who've seen our projects or been involved with our activities before, most of our work is geared towards a particular agency or a particular community. So having a cross-cutting, cross-agency working group that is helping to guide and really shepherd this activity along has been immensely helpful in making sure that we're engaging with folks across a set of applications. And then going back to that org chart that I made you all look at, similar to how it's unusual for projects in the National Academies to be so collaboratively funded, it's also a little unusual for us to have such a diverse group of stakeholders internally. So I mentioned I'm with the Board on Mathematical Sciences and Analytics, which is the lead for the project. We also have our Computer Science and Telecommunications Board, which lives within our same division. And then we have our division on Earth and Life Sciences involved through their board on Atmospheric Science and Climate and their board on Life Sciences. And then we also have our honorary society, the National Academy of Engineering, engaged as well. So a lot of folks with a lot of different takes on what digital twins are or could be, both from the funding side and the staffing within the National Academy side. And that brings us to our study committee, which is equally broad and eclectic. So you'll just, for those of you who haven't seen a National Academy's consensus study up close, what we do is we pull together a set of experts from a wide range of whatever the stakeholder communities are. So in this case, we have folks from the engineering, from computing, from maths, from statistics, from biomedical applications, from industry. Particularly want to flag a couple of the lab folks for the like Ruby Lung at PNNL and Irene Walters at Los Alamos, who have been just amazing to work with for the committee. But what we ask for these folks is that they commit to a significant amount of time over, in the case of this project, we've been meeting for a bit over a year now, or coming up on a year now. And we lean on them and their expertise to make sure that we are answering those questions that I laid out before in our statement of task. And ultimately providing a report that's going to be helpful to both the research community and to federal stakeholders. So as I'd mentioned, we had been meeting weekly since October 2022. We've also organized 3 large public workshops that I'll talk about in a few moments. Those are geared at getting more of the domain specific constraints. And then the focus of the report really is, in spite of the fact that I've talked about all of the different domains and communities that are engaged and all of their unique challenges, our consensus study is really focused on these foundational research gaps. So it's looking at where can we make the most difference to turn the vision of digital twins to a reality. And we anticipate this report to be pretty broadly accessible, but the primary audiences for the report are the scientific community and federal funding organizations who support digital twins. And so the report is on the final stages of development. It's gone through our peer review. We're just finalizing some of our changes. If all goes well, we will be able to release the report in about a month or 2. So stay tuned. But I did want to talk a little bit about some of the workshop reports or workshops and some of the information that we came across along the way. All of the recordings and summaries for these workshops are available on our webpage, and that's the one I put into the chat box. And there is a lot of information in all of these if you are interested in diving a little bit deeper into any particular application space. All right, so the first workshop that we had organized was on digital twins in biomedical sciences. And this workshop, actually for all 3 of the workshops, perhaps indicative of some of the varied approaches across the communities, we tasked a subset of the study committee with helping to organize each workshop. And the folks who were in charge of organizing each workshop were the ones who were most closely connected with the community of interest for each workshop. So for the biomedical sciences, sort of reflecting the unique spin of the biomedical community for digital twins, we ended up with a workshop that was focused, like step number 1 is always definitions. Like what is it, how is the biomedical community or communities referring to digital twins? What do we mean by them? What are some of the use cases that are being discussed or proposed across the broader community? But then a good portion of the workshop was focused at the different physical scales that digital twins were interacting with. So we had discussions on digital twins at the cellular and molecular scale, and then digital twins of the organ, tumor, and microenvironment scale. And then lastly, across the whole human, multi-system, and population scales. And then we had quite a bit of conversations about how do you connect that information across scale? How do some of the issues of uncertainty quantification across scale, like how does that play out in practice? And there was also a real emphasis in this workshop on some of the privacy, ethics, and data issues, so particularly with some of the identifiable data. And then also the workshop really focused on some opportunities for convergence. So how do you bring some of these different communities within the biomedical umbrella together? So just in terms of some of the specific opportunities and gaps that were flagged, I had talked in the beginning about the idea that a digital twin in biomedical applications could help inform real world patient care and clinical practice. And that really is an overarching goal in many of the conversations that we heard. So how do you improve the health and well-being of the patient at the center of this? And then there was a lot of conversation about this opportunity to conduct virtual clinical trials and really expand and make the best use of available resources to gather the most information and make the most informed decisions. Some of the specific research gaps that were flagged, and I just want to note that our whole consensus study is geared at outlining some of these key research gaps. These are ones that were specifically suggested by the workshops. They are not the official consensus study version of it, but just to give you a sampling of some of the input that we have heard. So as is not surprising to anybody, some of the opportunities to improve modeling, computation, and data analysis were pretty high up on the list, particularly combining some of the data-driven and mechanistic models, and some of those, the challenges with applying those in often not well understood biological processes. So that was like issue number one that came up across a number of the conversations. And then more specifically, managing some of the data and integrating different types of data is always hard. And then accounting for and communicating uncertainties is just something that we've heard a lot across digital twins, and is something that I think is an area where OSCAR really plays an important role in terms of the broader verification, validation, and uncertainty quantification. We also discussed quite a bit the challenges of developing trust with patients and clinicians as potential new tools are being implemented for clinical use or with the potential for clinical use. Everybody, both on the patient and on the doctor side, need to understand and value and trust the input or the output that you're getting from those. And also addressing some of the ethical, privacy, and security concerns, and then also improving data sharing mechanisms, particularly with sensitive patient-specific data, making sure that that's all handled and managed appropriately, especially as for the case of a digital twin, if you might have a larger feedback cycle that can potentially share data with a number of people along the feedback loop. So that was our first workshop. The second workshop was on digital twins in atmospheric science and sustainability sciences. Again, we focused on definitions. I can't emphasize enough that across these three different workshops and I think every information gathering session that the committee did, I don't think we heard the same definition more than once across it. So a big issue across digital twins is just really, how are we defining this? What's the difference between more conventional modeling or simulation? And what is the value proposition that makes this different? And so across for atmospheric science, for atmospheric climate and sustainability science, we talked a lot about the key methods and practices, technical challenges and opportunities, translation, and then one thing that really stood out for this workshop was an emphasis on transparency, societal benefit, and equity. So some of the visions that were laid out in this workshop was really creating more, through the use of digital twins, creating more interactive simulations of Earth systems, and improving the prediction capabilities and ultimate use for decision makers and for community engagement. And through the potential of digital twins, the goal is to have more realistic and high resolution models that can incorporate these different types of data and really get and provide the potential for more community-centric metrics along the way. Some of the specific gaps that were flagged were challenges or a need for increasing observational abilities, computational capacity, and mechanisms for large-scale data handling and management. An emphasis was placed on expanding research for parametric sparsity and generalizing observational data. Another conversation was more about increasing the generation of training data and how do you provide the right types of data to help these models how do you provide the right types of data so that these models can react in a predictable or expected way. And then again, the uncertainty quantification is a huge issue. This community had more suggestions of some potential approaches that could help, but again, emphasized throughout that this was a key and important issue. And then lastly, our third workshop was digital twins on engineering. This perhaps was the most broad of the conversations that we had because engineering can mean a lot of things to a lot of different communities. So again, we start off with definitions, and then we spent a good chunk of time hearing the perspectives from stakeholders. So there were a number of industry folks engaged, some different academic research communities, but really across the board looking through what are the opportunities and what are the current methods and practices and challenges and opportunities, kind of similar to the other workshops, but with a more engineering focus. And then this workshop also paid a bit more attention to not only the R&D needs, but potential investment opportunities as well. So in laying out some of the visions and opportunities for digital twins, we talked about the potential for digital twins to really help provide actionable information for asset management. And what that asset is depends a lot on the context, obviously, but really making sure that those assets are operating reliably, that digital twins can be used to help inform maintenance, similar to the aerospace application that I talked about earlier. And then hopefully really improve efficiency of the system and the use of that asset within the system. And one thing, a conversation that was unique in this workshop was an emphasis on testing, designing, and prototyping processes and using digital twins to really exercise some of these virtual prototypes. So some of the gaps that were flagged for the engineering workshops were more along the lines of issues connecting simulations across length and physical length scales and physical phenomena, advancing experimental design, capturing sources of uncertainty within the broader engineering space was emphasized repeatedly, and managing a lot of that uncertainty and the uncertainty propagation is essential. And integrating data science and domain knowledge to enable decision-making was an important topic, and also managing, once again, like similar to the other workshops, managing the massive amounts of data and really providing an analytic structure for that. And there were several folks in the workshops who called for the development and harmonization of ontologies across the different user community to really help bring some clarity of how we're thinking about digital twins in some of these application spaces. All right, so the workshops were part of the information gathering. As I'd mentioned, for the final report, a big emphasis, like bullet number one for our study statement of task, is defining what we mean by digital twins and how that varies across some of the use cases. But then really identifying and prioritizing some of these cross-cutting foundational research challenges. So some of the ones that particularly resonated from the ASCAC space were along the modeling, simulation, uncertainty quantification, and managing multimodal data. And the final report also discusses quite a bit some of the promising practices for digital twins in use and opportunities to translate some of the best practices across communities. So with that, I would be very happy to answer any questions. I know I'm excited for you all to see the final study as it comes out. If you are interested in getting alerts on it, you can sign up for our webpage or sign up for our mailing list on our webpage. It's nas.edu/BMSA, which stands for the Board of Mathematical Sciences and Analytics, or feel free to send me an email and I will put you on our distribution list. And then lastly, I know he's not here, but I want to say a big thanks to Steve Lee and Oscar, who's been just really instrumental along this whole process and helped us think through some of the key questions for digital twins as as we're moving forward. So with that, I would love to help answer any questions or hear any of your thoughts.
Rick, and then Jill.
Hi, and thanks. Given the charter for this particular group, what are your thoughts or what you see as a trajectory for discussing a national infrastructure for hosting the actual execution of and the data surrounding digital twins that would be of a non-private nature?
Yes, so this is, I think, unfortunately, one of the areas where I'm going to punt it until the final report comes out. So the report does talk about some of the ways that some infrastructure opportunities that exist for some of this cross-cutting collaboration. But I think there's a lot of interest and a lot of enthusiasm around digital twins, and I am excited to see where that heads in practice. But I would encourage you to sign up for the mailing list so you can get the report once it's out.
Jill?
Hi, Michelle. Nice talk. Lately, I work in biomedical research. Lately, I've seen lots of proposals to review that throw in the words digital twins all over the place. And I have a hard time, even in the talk you've just given, trying to really distinguish between modeling and simulation of systems, whether they're biomedical systems or engineered systems and so on, and a digital twin. And it just struck me when you mentioned your cross-cutting issues that, to me, these cross-cutting issues, modeling, simulation, they're very actually domain specific, because when you're modeling a biological process, that's very different than modeling an airplane, and different approaches are used. So I just wonder, is digital twins really a new thing, or is it just a new name for what we've all been doing for many years in modeling and simulation? And in terms of infrastructure, I think that the infrastructure that's required, that was just brought up by Richard, I mean, that's required right now for modeling and simulation. So help me out here.
Yes, okay, so your question about the definition of digital twins and what makes it different from modeling simulation is one we have heard at almost every public session that we've had for it. So the committee is coming out with in the report, there will be an explicit definition for a digital twin that they think cuts across these different domain applications. But the gist of what, as I think of it, is really the feedback cycle. I think that is what's unique. That is what differentiates a digital twin from, say, modeling and simulation that takes real data and then provides output. You really want it to be a feedback loop where you have data, it goes to the model helps inform a decision, that decision is implemented with the patient, and then it goes back to the model. And the model then evolves over time.
But don't we do that all the time right now in modeling? I mean, when we're doing machine learning and other approaches like that, and especially with Bayesian methods, which existed even before we started calling things machine learning. I mean, we always took what we learned and how well it actually fit the real life situation we were trying to model, and use those to improve our models, the parameters that we used, and so on. So I'm still wondering what the real I don't want to put you on the spot, but I'm still wondering what that definition and why the feedback loop really adds something that many of us do in modeling and simulation already.
Yeah, then that's very fair. So I think that there are instances in modeling simulation where a feedback loop like that is implemented and is very indicative of how we're referring to digital twins. I think where some things deviate for us, like we've heard in a lot of the workshops, people are like, it's a digital twin because it looks like the entity. And we're like, no, that's not really it. In addition to the mathematical sciences board and portfolio that I run, I do a lot of manufacturing and material science stuff as well. And I can't tell you how many industry presentations we've heard under that board where it's like, look, we have a digital twin of our manufacturing floor. And it's like, no, you've just modeled your manufacturing facility. Like, that's not the same thing. So I think we're just emphasizing that the feedback cycle is an essential and critical part for digital twins, and that in the case of digital twins, like your model evolves with a particular entity. So it's not that you've updated your model and then you're using that, you've updated your model off of, say, one airplane and you're then using it across your fleet. You're updating that model for your airplane, and then that model continues to get updated. That same model is getting updated for that same airplane. And so the evolution of the evolution on a more individualized asset is, I think, really where some of the distinctions that we've called out are.
Okay, thanks.
Yeah. Oh, and then your second question, though, about the cross-cutting issues. Totally agree. Like, what's going on in biomedical sciences is fundamentally different than what's happening in some of the defense-oriented engineering spaces. And I think that's been a key challenge for the study. So our whole study is really geared at looking at what are these foundational cross-cutting challenges. So what's something that we can say, hey, this one research area, if it were to advance, can help biomedical sciences, can help atmospheric science and climate, can help diverse engineering spaces. Recognizing that some of those communities are farther along on any one of those things. So the workshops were meant to really do these deep dives into the domain communities, but the final study is intended to be a more cross-cutting look.
Got it. Thanks.
Martin?
On the same theme, isn't some of what you're saying, though, that the digital twin, because of this feedback loop, has to be rather more nimble in terms of how it can be used than a massive simulation that might take a day or a week or something like that? Isn't there this idea of feedback coming through more quickly sometimes, at least in some circumstances?
Yeah, the issue of how quickly this like real-time information or how quickly this feedback cycle has to happen. I think, as at least from what we've heard through some of the workshops and other information gathering, is like that is very domain specific. Running some of these big atmospheric science and climate models, it's gonna take a long time, and like you're pulling in a bunch of different data. Whereas, so that might be a larger or a more slowly iterated feedback loop. But if you're modeling for a particular patient, say in a biomedical space, then like potentially you would hope that that could be, you know, that would be a more nimble model than when some of these larger, more complex modeling spaces. But I think that's one of the areas where I would expect that to be pretty domain specific. But the idea of calling for some of these real time or at least continually updated modeling approaches, I think that could be identified as like more of a cross-cutting challenge.
Thank you.
I mean, these things are all evolutionary, you know, control systems, modeling. I am, just as an anecdotal aside, I remember once my DARPA program officer called me and said, Dan, I want to correct an illusion under which you've been laboring. You may think you're doing advanced high-performance computing, you're not. You've been doing nimble and embedded adaptive systems, and next week when the solicitations come out, you'll understand why. And I said, I've had an epiphany. So I do think the real-time notion of feedback is perhaps the critical enabler, but there are a lot of semantics in these. So Michelle, look forward to the Academy's report, and thank you for joining us today.
Thank you all so much.
All right, and we'll move on to the view from Germantown, and congratulations, Sharon, on your formal appointment. Look forward to that conversation as well.
Thank you, Dan, and I hope you guys can hear me. And I'm just going to go ahead and share my screen, hopefully successfully. All right. Well, again, it's my great pleasure to address this committee once again, yet again, a different role, I guess. And I want to thank you over the years for all your support and your valuable feedback as we went through, new emerging technologies and changes within the ASCAC staff, etc. So one of the first things that I learned in this job is that I don't get to talk about fun stuff anymore. I used to talk about QIS and the new research directions, and now I'm gonna talk a little bit more about budget. And let me dive right into it and give you a budget update on the FY24 outlook. As you may remember, the President's budget request came out a couple of months ago. I think we've talked about it in the last ASCAC meeting. The President's budget request for ASCAC is a little bit over 1.1 billion, which is an increase of 58 million or 5.4% above the 23 enacted budget. After that, since we last talked, the House and Senate markups came out, and I'm going to try to give you a little bit more details of relevant sections for ASCAC. For high performance computing and networking facilities, I'm going to start with the House markup that came out first. We have the committee recommends 219 million for ALCF, 255 for OLCF, 135 for NERSC, and a little bit over 90 million to support necessary infrastructure upgrades and operations for ESNet. The committee also recommends 7 million in other project costs for high performance data facility. On the research side, the committee recommends 295 million for overall research, and that includes the computational science partnerships and the advanced computing technologies divisions. And of course, there are a couple of asks from the committee. One of them is that they encourage us to support research to develop a new path to energy efficient computing with large shared memory pools. In other parts of the markup that are not necessarily specific to ASCAC, but certainly relevant to ASCAC, is a couple of recommendations here. One of them is about QIS. The recommendation provides not less than 245 million for QIS, including not less than 120 million for research and 25 million for the 5 national quantum information science centers that we stood up in FY20. At the same time, the committee supports efforts to expand quantum internet, networking, and communications testbeds. And also, they direct us to conduct research activities in support of the Quantum User Expansion for Science and Technology program, otherwise known as QUEST, as authorized in Chips and Science. The recommendation is that we allocate up to 15 million for these activities. The committee also asks not later than 90 days after enactment of this act, a report on near-term application developments that outlines the breakdown of research funding across the available quantum computing technologies, including gate model, annealing, topological, photonics, trapped ion, silicon, superconducting, and other viable quantum technologies. At the same time, we are encouraged to expand our relationship with NIH, including National Institute of Mental Health, and that includes, of course, strategic partnership projects to work together more strategically to leverage DOE's research capabilities. And that also includes, of course, instrumentation, materials, modeling and simulation, and data science. Couple of more items from the House markup that are certainly relevant to OSCAR is that the House markup does not include any funding for Renew or FAIR. For Energy Earthshots that you've heard this morning about, the recommendation provides up to 20 million for Energy Earthshots, including up to 5 million for OSCAR, and 10 million from BES and 5 million from BER. Of course, the committee is very much supportive of the facility operations. There's a recommendation for the department as a whole is that we are directed to provide a table of user facility funding levels from previous 5 fiscal years, showing optimal operations using the new determination. The recommendation includes not less than 35 million for EPSCoR. And there's also another recommendation that that involves the future year awards. And we are expected to provide information by control point and fiscal year on the total funding from active and closed funding opportunity announcements. Okay, and then came the Senate markup. Of course, the committee strongly supports OSCAR's leadership in emerging areas relevant to the department's mission, and that includes artificial intelligence and quantum information science. We are asked to continue in our pursuit of machine learning tools for scientific applications and the development of algorithms for future deployable quantum computers. Of course, it is also very well recognized that the ECP has successfully created a broad ecosystem that provides shared software packages, novel evaluation systems, and applications relevant to the science and engineering requirements of the department. So the recommendation supports efforts to maintain and improve such products in order to continuously realize the full potential of the deployed systems. When it comes to the facilities, the numbers that are actually quite close to the House markup, and I'm going to show this in the next slide as a table of how these numbers compare to the president's budget request. So maybe I'm going to skip to the research side. The Senate markup recommends not less than 280 million for research in total. Again, that includes the activities within the computational science and partnerships division and the advanced computing technologies division. This also includes 20 million for CSGF. A few more details from the Senate markup, not less than 255 million for quantum information science, including not less than 120 million for research and 125 million for the centers. There is language related to artificial intelligence and machine learning. The recommendation is to provide not less than 135 million across the Office of Science programs. But in this recommendation, OSCAR is given a lead role in the department's artificial intelligence and machine learning activities. Again, we would like to, and we are recommended to continue our focus on the development of foundational artificial intelligence and machine learning capabilities. And the committee encourages the Office of Science to apply those capabilities to the Office of Science's mission. In terms of the diversity and broader engagement activities, the Senate committee supports FAIR and Renew initiatives. Again, it recommends similar to the House markup, 35 million for EPSCoR. And of course, there's language supporting our facility operations. There is language in the Senate markup regarding the microelectronics. We are encouraged to support the microelectronics research and microelectronics science research centers. As you may remember, the microelectronics science research centers is part of the president's budget request. When it comes to Energy Earthshots, The committee recommends up to 67 million for energy Earthshots, including up to 18 million from Oscar, 31 million from BES, and 18 million from BER. So how does this all come together? I tried to put this in a table here with the, what we know from the report languages. When you compare this to FY24 request and FY23 enacted, the facilities numbers are close or similar, in some cases identical to the President's budget request for FY24. When it comes to research, I think about 28% in the House mark, 28% less than the President's budget request, which is also about, I think, 13% less than the 23 enacted budget. In the Senate mark, we have a reduction of about 32% in comparison to the President's budget request, and I think 17% in comparison to the FY23 enacted budget. For Exascale, of course, we're wrapping up our activities. You're going to hear more about that in the next talk. And the high performance data facility, the recommended budget, they remain the same. Okay, so on that note, let me shift some gears and talk a little bit more about the facilities and the exciting news that came out of the facilities since you've had a chance to hear from the research side. Perlmutter full system was accepted in July 2023. GPU nodes have been available to all NERSC users since May, and the previous system, Cori, was retired at the end of May 2023. At the same time, we are continuing to work on deploying the second Exascale system. We are on track. Aurora at Oak Ridge, the full system installation was completed on June 22nd, 2023. The system is still in the scaling test phase. There are some usual issues seen with those systems, but we are on track to on fully deploying the system. Exciting news, Frontier is open for science, and all allocation programs have been enabled since April 2023. We have 2 Gordon Bell Prize finalists and additional one, a special Gordon Bell Climate Special Prize finalist. You're going to hear a little bit more about the E3SM this afternoon. Up to date, we have over 1,500 users and 240 projects active working on the on Frontier. And really, the early science results that we get are so encouraging and really inspire us that there is a new science era in front of us that's unfolding. At the same time, Summit has been a very stable system, and we decided to extend the lifetime of Summit so that the users can take the maximum advantage of it through the calendar year of 2024. And there is a special allocation program that we created for Summit that's called Summit Plus. The system is currently accepting proposals, and if you have any questions and want to learn about how to apply for allocation on Summit, please contact OLCF. Now, going back to the 3 Gordon Bell Prize finalists in 2023, one of them is in the materials domain. This was led by University of Michigan, and it involves DFT calculations for design and discovery of new materials. The model achieved the fastest sustained performance recorded for any materials simulation, close to 0.66 exaflops using Frontier. And again, this is just the beginning of what we're going to get, that we believe that we're going to get with exascale systems. For advanced reactor design, this is the second Gordon Bell Prize finalist, and the lead is Oak Ridge National Laboratory. In this case, the work involves multi-physics simulation of nuclear reactor with a Monte Carlo neutron transport code. The problem sizes and work rates they achieved on Frontier make it feasible to simulate the conditions inside a nuclear reactor with really unprecedented accuracy. We are also very excited about the special prize that came in the atmospheric modeling. I think you're going to hear a little bit more about that this afternoon. In this case, the lead institution is Sandia, and this involves a simple cloud resolving E3SM atmosphere model. I'd like to go with the abbreviation SCREAM. This is a very exciting result, again, in the sense that it broke the long anticipated barrier of simulating more than 1 year per day of computation, with promising to help inform climate change forecasts. So I think you've heard a little bit more about the research directions that we're interested in. And we've been talking about the end of ECP and transitioning the workforce, etc. At the same time, instead of maybe focusing on the end, we really need to start celebrating the beginning of a new science era. And the early science results that we have using the exascale computers really show us that we're at a very pivotal moment, probably in once in a lifetime opportunity. The research tracks that you heard about this morning really focus on 3 themes. One of them is how do we leverage the exascale ecosystem that we created, which is really a world-leading ecosystem at the end of ECP, and combine that with the power of the AI. At the same time, both in our investments in research and facilities, we want to continue leveraging the heterogeneous architectures, and that includes, of course, the AI, but also quantum information science and anything else that are emerging. But another thing that we want to do in our programs is to find the balance between agility and the long-term sustained funding. And you've heard a little bit more about that in the morning. We have programs that we revived in 2021, like Express, where we're really exploring exciting breakthroughs in certain areas and fund high-risk, high-reward research for small teams, and going from there to bigger teams and center scale activities that involve multiple institutions and more sustained, bigger funding. So in a way, given the budget realities and there is no denying it, of course, the Senate and House markups, they're lower than the president's budget request. We are working very hard to figure out if we can consolidate certain research areas within the research division so that we're making the maximum impact in terms of advancing a new science era. I think with that, I'm going to stop, but the day is not over. So a couple of remaining ASCAC agenda items. We have the ECP update, and this is really the home stretch that you're going to hear from Lori, and more about the how climate scientists are using our exascale ecosystem. And Tony is going to talk about the DOE and NCI collaborations that we've been very proud of and following very closely. And you're going to hear from Eric Lin, who's going to talk about Chips for America. This is it, and thank you very much. And I'm happy to take questions. I know that Martin has a question.
All right, Martin, we'll start with you.
I can't
You're
hear
muted, Martin.
Yeah.
First of all, congratulations, very well deserved. I'm very pleased to see you there. I'm just thinking, first of all, I thought you covered many good things, and this looks like a great path forward. I'm kind of curious as to sort of one other aspect of this, and maybe some of that, it's slightly related to chips, but it's more than that. I mean, I heard the rather shocking news that 7 out of the 10 fastest machines in the world are not in the US. I mean, you can guess where they are. And these are machines that are not on the top 500, and they're slower, older technology, but the things are moving pretty quickly with regard to the technology. Let's not mess around in China, with phones and everything else. Now, it may be that gets slowed down with the way things are going. But at the same time, we see new generations of photolithography equipment. We see new sort of energy saving architectures such as processor and memory. And I don't get a sense that these are sort of on the priority, queue for the present activities that we're hearing about. And I feel that there's a danger that we may be sort of left behind if we don't think strategically about moving in these directions. It gets worse when I hear that these machines in some of these other places are being used for what you might loosely call hypersonic science, in which is an area that we seem to be behind, looking across all the agencies. And so there seems to be a kind of national interest in kind of moving us forward into sort of more advanced architectures and thinking more about, energy efficiency architectures and so on. And it looks like the path to down to 1 nanometer is reasonably clear at this point in terms of what's happening. So what's your view on what the strategy should be in terms of going in this direction to try and retain our traditional advantage in this space and to move forward in terms of some of these applications in areas that might even require sort of multi-agency collaborations and things like that?
Well, I think some of it is really in the microelectronics, and we've been, a very active partner in the interagency setting in terms of how we're going to advance that field. And as I mentioned, and you know very well that we do have a big request for the Microelectronics Research Center. Some of these things, they need to be done in partnership with the other Office of Science programs, and we do actually have these ongoing collaborations. The question is that can we expand them, and we hope to. And even if we don't get the budget, we would like to pivot in certain cases to make sure that we are following these very fast-moving fields. I think Dr. Berhe talked about the the microelectronics co-design program that's ongoing. And of course, the centers is in the request, and whether or not that's going to happen, it remains to be seen. But certainly, the recompetition of the co-design program is coming up, and I think these are the fields that we're following very closely and working with the interagency partners too. At the same time, I think the Express program gives us the flexibility to include some of these topics. And we're constantly actually trying to get input from the community, and this is very good input, frankly.
I mean, I think that's great, but I also think there's a more urgent need to think about what the machines will be beyond exascale. And I think the technology is becoming clearer, and the steps that you indicate are all good ones in that direction, but there might be something that's a larger, more clear sort of initiative in this space to try and make sure that the advantages that we've gained with architectures like Aurora and Frontier and will be the case with El Capitan are not lost over the next 5 years. And that's probably going to require more than the focus that's present right now. But that's not to decry those activities. It's just that we cannot afford to lose that.
Agreed.
Other questions or comments? I mean, that's kind of, my high level concern as well. I mean, to be sure, Path Forward accelerated some of what the vendors were going to do, but it was still a small tweak of their roadmap. And our influence is, in terms of financial leverage, is increasingly small, which is kind of what the National Academy Study for the Weapons Program pointed out. to how we kind of think about this as not just an Office of Science challenge, but to Barton's point, not just as a DOE challenge, but this is probably $1 trillion question. It's a national strategy question. And how we marshal that conversation in this political divide seems to me to be the really big question. Any other thoughts? Yeah, go ahead.
Well, I was just going to say, yes, I appreciate that any input that this committee has, of course. And at the same time, you know, we are well prepared to work with the partners, with the industry partners. I think ECP, not only the outcome of ECP created a big ecosystem, but also the history that led to ECP gives us a lot of experience in terms of, you know, advancing different fields and working with the industry partners. Now, the budget question is something that I cannot necessarily answer, but certainly we plan to leverage that experience with the budget realities that we have.
Fair enough. All right, thank you. Picking up on your last slide, we'll jump into the ECP home stretch. And so Lori, Mike, and Andrew, I'm not sure which one of you or which combination is going to present, but please go ahead.
Great, thank you. It is all of us. And let me just go ahead and bring up the slides. Okay, I'm assuming everybody can see the slides that I'm showing.
You're good.
Okay, great. So yeah, this talk is going to happen in 3 parts. I'll start out and give a broad overview of where we are and where we're going over the next 3 to 6 months. And then Andrew will speak a little bit about some of the details of what we have found in our KPP verification process. And then Mike will bring us home with some observations on the software technology side. So we are in the home stretch. So just a reminder for those who aren't familiar with ECP, you know, this is a very large project, about $1.8 billion that was started in 2016. And it involves most of the DOE laboratories along with dozens of universities and industrial partners. Over the years, we've funded more than 1,000 participants, and we're organized into 3 technical focus areas: application development, software technology, and then hardware and integration. And then those are further subdivided into about 81 different research projects. So because we're a formal 413 project, we had specific measures of success that we needed to define and meet in order to be considered successful. Those are called key performance parameters. And I'll give you, our most exciting news for the day. We have met our key performance parameters, our KPPs. So we have about 3 months of technical work, and we're increasingly focusing our energy on the project closeout, our communications and outreach. And so I'm going to talk about some of that today. One of the things that we're working very hard on is capturing and documenting our impact and what we believe the legacy of the Exascale Computing project will be, and then writing that in a way that it's broadly accessible to a wide audience, so not too technical. And so these are, just as a starting point, some of the things that I believe ECP will be remembered for, right? The suite of applications that impact problems of national importance for decades to come. And Andrew will speak to that. We have had the opportunity to develop an integrated software stack for GPU accelerated computing that's going to be widely available and useful from laptops all the way up to Exascale. And so again, Mike will speak to that later. We have de-risked folks moving to accelerator-based computing. When we interact with our industry and agency council, this is one of the things that they talk to us about, what we have done for them. We have shown them the kinds of best practices that are needed in order to take advantage of accelerator-based computing in a wide variety of areas. And we've provided the software and tools to help them get there. And that's been really critical for moving not just the DOE forward, but a lot of other agencies and our industry partners as well. So I think we've also had a lot of experience now in running a large scale software development, our research development and deployment project, research development and deployment project in a 413 formal way. And there are a number of lessons that we have learned along the way that we are capturing and documenting and passing it along in case it's useful in the future. So yeah, our big news, our KPPs are complete. So the key performance parameters that we had were divided into 4 areas. There were 2 that were focused on applications. The first, KPP 1, was focused on applications that were already running well on petascale class machines when the project started. So they were able to run to, full scale run on the, order 15, 16 petaflop machines that were available at the time. And our success here is that half of those applications, and there were 11 of them, need to demonstrate a performance improvement of at least 50x on a base challenge problem. And one of the keys here that Andrew will comment on is that these are not benchmark problems. These are real multi-physics integrated applications. And so this is a hard goal. Where we are is we have 9 that have completed their KPP runs. 5 have gone all the way through the review process to our federal project director, and 4 are still under review. The second set of applications are those that were not running at petascale levels when the project started. So this is about broadening the impact of exascale computing to additional application areas. So we had 10 Office of Science and 4 NNSA applications that are in this KPP2 category. And they were required to demonstrate a base challenge problem that they couldn't even have dreamed of doing back in 2016 and show good utilization of the machine. So since they didn't have a baseline, we couldn't say do 50x better, but they have to show good utilization of the machine. And where we are now is that 6 of the 10 Office of Science apps and 3 out of the 4 NNSA apps are complete. And then finally, the other one that we're active on is KPP3. So this is for software technology in our co-design centers, and it's really focused on creating those integrated, sustainable contributions to the overall software ecosystem. So each one of our products, and we had 76 software products that we're considering, was required to demonstrate about 4 or 8 integrations with a client. And that client could be an application code, it could be another software technology library or product, could be the facilities, it could be the community standards. So we created a rubric by which those integration points were collected and scored, and we had a possible maximum of 68 points that we could achieve for these integrations. And our threshold was to meet 34 of those. Where we are today is that we have achieved 40 of those integration points. A little over half of those are complete and all the way through the review, and the rest are under review. And then one that we achieved many years ago was KPP4, which was about the path forward milestones and impacting the exascale architectures that are on the floor today. So I do want to say that our KPPs would have been impossible to meet without really close collaborations with the OSCAR facilities. And so, just a reminder of, we're working very closely with both Frontier and Aurora for Exascale, and we've also worked very closely with NERSC as we were getting ready to get onto the Exascale systems. So the full system of Frontier was made available to us in April of this last year. We did have an opportunity to put select teams on in a rolling 10-day window, starting, I think it was around last October, where we could get some initial experiences on Frontier before April. So all of our KPPs to date have been run on Frontier, and they're seeing excellent performance. And many of our ST and co-design KPP3s have also been achieved on Frontier. So in terms of what we're seeing now, we're still seeing some stability issues with large scale jobs, but there are many workarounds in place, particularly leveraging the fast storage capabilities for checkpoint restart. And so that has made it able for us to do lots of great science on the system. So it's been a really great collaboration with the OLCF. So to get to to our KPPs, we've used about 5 million node hours in order to demonstrate our KPPs. 6 of our teams have insight allocations, which have been used for a mix of KPP and insight science, and those have used about 3.6 million node hours. So a lot of time used, a lot of great science done. On Aurora, you saw in Jaren's slides that the installation was completed in June, and they're still seeing some issues. So we do not yet have access to Aurora as a full team. We are expecting that access. We're hoping later in October, but we have had some limited availability starting in July through our Argonne ALCF liaisons. And so we've been able to do some sort of mid-scale type testing for some of our applications. We have achieved a little less than 10% of our KPP3 integrations have been achieved on Sunspot, which is the test and development system for Aurora. And we do believe that Aurora is going to be a major performance portability test in the final quarter of technical work once we get access. So we've used about 9,000 node hours on Sunspout and about 24,000 node hours on Aurora. So because we don't have our hardware and integration team presenting today, I wanted to present one highlight from that team. And this is work led by Bryce Videu at Argonne National Lab. And several years ago, we were looking at performance portability and looking at the fact that it was really straightforward to go from CUDA to HIP using the HIPify tools, but it was not nearly as straightforward to go onto the Intel GPUs at that time. And so we funded an effort that was all around this idea of bringing HIP to the Intel GPUs. And so the idea here was to really reduce the effort that it was going to take to move applications to the Aurora system and allow them to port and try out their applications very, very quickly on Aurora. And so Bryce and his team have been developing a new HIP implementation on top of level 0, which is the Intel GPU runtime, and on OpenCL. They've also been looking at porting math libraries and the tools that are needed and supporting many of our applications. So they've released version 1 of ChipStar, which is this implementation of the HIP on the Intel GPUs. And they're supporting several applications. The games application, this is one we'd really like to have access to Aurora in the next quarter so that we can see how well this technology works. And then one of our co-design centers. So they've also been doing some benchmarking just to make sure performance is not impacted in a really negative way. So they've been looking at the Aurora Ponte Vecchio GPUs using this HECbench version of the benchmarks. And anything that's scoring greater than 1 shows that HIP is doing a little bit better than SYCL. And you can see for most of the cases, the vast majority of them, they're very, very comparable. And in a few cases, the performance tails off compared to SYCL. So we're very excited about this, as a risk mitigator. That's why we initially put it in place. But we think there are lots of additional benefits in terms of the ecosystem improvements that can be made, better tooling, additional tools for performance portability for our teams. And then this will see some continued support from the ALCF going forward and some of the seedling stewardship projects and from Intel. So just wanted to highlight one of these examples from our hardware and integration area. You've already heard several times about the fact that advanced nuclear reactor modeling has been nominated as a Gordon Bell finalist. I'm also choosing to highlight that application. So it's our ECP ExaSMR application. And the goal of this project was really to help DOE meet its goal of an operational small modular reactor within a 10-year time frame. And so Jaren mentioned several of the performance improvements that they've seen, right? In terms of, it's the first fully coupled, fully resolved simulator of the nuclear core, with CFD and Monte Carlo neutron transport. They were able to see, over 400x on the CFD in terms of the improvements that they saw from the beginning of ECP, and 113 on the neutron transport algorithms. And so just tremendous improvements in speed, well beyond the 50x. So they're using these to model a new scale reactor core. And some of the advances that we've seen, compared to the beginning of ECP is on, on Titan, they were able to model just fresh fuels that are in the nuclear core with just 4 or 5 isotopes. With Summit, they were able to look at depleted fuels, but only at a snapshot in time. And now with Frontier, they're actually able to model that evolution from fresh through depleted into depleted fuels. And so that's a tremendous improvement in the accuracy of the simulations and the fidelity that they can get. And so this, as you've heard once or twice or 3 times already, is one of the Gordon Bell finalists. And because we had a number of Gordon Bell finalists and other things that were coming to our attention, we thought, we really should go back and look, what were the awards that ECP technologies and people have garnered? And one of the things that we've discovered is that not only are we working on leadership class computing facilities, we have a leadership class computing technology and participant list. You can see the R&D award, R&D 100 awards that have been given. This is just from 2016. We have technologies in our portfolio that have R&D 100 awards from previous to when ECP started. We've had Gordon Bell finalists, both last year and this year. Our E3SM team is part of the E3SM Gordon Bell finalists, but not specifically for the ECP work. So we don't list that here. And of course, Jack's AM, the Turing Award from last year, the ACM Fellows, the Ken Kennedy Award that Ian won. It's just a star-studded cast. So lots of awards, some very notable. So the Sundials team, for example, was awarded the ACM Prize in Computational Science and Engineering earlier this year. So just want to acknowledge how tremendous the have been and the technologies that they have developed. Also want to give you an update on our broadening participation activities. So we've had a significant focus on training the next generation as a pipeline into the DOE workforce. For the last 2 years, we have been funding sustainable research pathways for high performance computing. So this is a outgrowth of a program that was started at Berkeley Lab several years ago. In the summer of 2022, we looked at, had 61 participants in the program. In the summer of 2023, we expanded it significantly. We funded 120 participants through ECP, and then an additional 69 participants were funded through the labs. And so we had almost 200 participants go through the program this year. So next summer will be beyond the end of ECP. We're not going to be able to fund a program next summer, but we are funding the matching workshop, which is happening basically next week. We're targeting 100 participants and looking to the labs to fund those participants, similar to how the 670 or so were done this year. One thing that is new that just happened in August was our Intro to HPC Bootcamp. And this was a really nice activity. And if you have questions, Lois is on the line and can speak to this. We hosted it at NERSC. There were 60 students who came in from 22 different states. About 50% of them were first-time scholars. And the way the program was organized was that it was focused around group projects that looked at problems of real impact to society. So what was chosen here were energy justice projects. And so they worked in small teams with project leaders, with mentors, and really got a good introduction to high performance computing through this program. And now many of them have applied to be part of this SRP program in the matching workshop that's coming up next week. And then finally, I just wanted to mention AppTest. This, of course, predated ECP, and it was incorporated into ECP back at project inception. It's a 2-week training program at Argonne. But we just got a really great email from Eric Nielsen, who's at NASA Langley. This is one of our agency partners, and he's been sending some of his early career staff through the program for many years. And he just had a really nice quote that, the AppTest program is truly the standard of these kinds of courses by which all others are measured. And so I just thought that was a really nice acknowledgement from one of our agency partners. We will have a significant presence at SC23. Lois has been invited to speak about the Broadening Participation Initiative that I just mentioned. So I invite you to look for her talk. I believe it's on Thursday morning. I'll be a part of the press session and we'll be speaking on exascale computing there. And we have a panel that has been organized from our Industry and Agency Council. Fran Hill from the Department of Defense will be our moderator, and it will involve several of the folks who are on our Industry Agency Council. So those are some highlights to look for, but we're also in the Gordon Bell Prize. It will be featured in the DOE booth, and just of course many talks, tutorials, posters, etc. With our Industry and Agency Council, we've been very active since the last time we talked in June. We've had a technical deep dive with NASA on software technologies. It was held on July 18th with about 70 attendees, and we really focused on an overview of what the NASA software and hardware environments are, and then what E4S technologies, software stack itself, but then individual technologies, including SPAC and IO and compression, how those are used in ECP applications, and then how those might be used in NASA applications. Had our quarterly call just a few weeks ago, 6 weeks ago or so, with update on our communications and outreach strategy and discussions about sustainability, and have been really focusing in on the collaboration points with NASA and with NOAA are the two that we've been looking a lot at. And so looking at incorporating E4S and SPAC into some of the NASA codes, exploring GPUs and performance portability tools in their codes. NOAA has been using E4S on the cloud and been working with our teams on performance portability using COCOS and OpenMP, looking at it, including adaptive mesh refinement in one of their benchmark kernels. So just a lot of activity with the Industry and Agency Council as we try to bring them along into the exascale era. So we are moving toward project closeout. So we're here basically right at the boundary of the fiscal year. We have 1 quarter left of technical work. So we will complete technical work on December 31st. And at that point, we will start preparing for our CD4 review. In fact, we're already preparing for those reviews, and project completion and the financial closeout. So as part of those 3 months, a real focus for us is going to be our communication strategy. I mentioned earlier that we're really trying to spread the word to a very broad audience. So we just finally completed the procurement process to bring some additional writers on to help us with this, where we're looking at the collaboration and integration case studies between application development and software technology, how this is being used in industry and the other agencies, articles about where we started and how far we've come and the impact of exascale computing. We're working on a book. So Andrew and Mike and I have been very involved in that, to tell our story in a way that we think will be broadly accessible. And, just working on a number of different collaborations and highlights. We are planning to hold 2 final Industry and Agency Council meetings along with a virtual workshop. So again, next week we have a virtual workshop on continuous integration and continuous deployment that they were very interested in. We already have about 70 registered participants. We'll have our fall meeting, government shutdown permitting. We'd like to hold it in person in Washington, DC. Focusing in on stewardship and computing in a post-ECP world. And then we will have a final meeting in January, late January, early February with the tech reps for our industry and agency partners. It'll be a larger meeting. We're expecting about 100 people, and we're going to hold that at the Argonne Conference Center. Leadership team will remain engaged through not only our CD4 review, but then also through the DOE sign-off, which is called the ESAB. And working on a lot of different things, talking about, project documentation that we have, the CD4 review. I will mention that a big lift for us is going to be the financial closeout of ECP. Right now, there are nearly 400 financial elements that will need to be closed out, including 150 subcontracts to universities. And so this is going to be a pretty big lift for our project management team. And so something that we're paying a lot of attention to. And then finally, we are capturing and sharing our lessons learned in technical areas, things like performance portability, increasing arithmetic intensity, refactoring codes, strategies for moving from GPU accelerated to GPU resident type algorithms, our lessons learned in collaboration and the value of software in that process, and how you build integration and collaboration into project structure and measure its success. And then of course, project management, which I mentioned earlier. And then we have been collecting statements of impact. Here are a few that we've collected, that Mike Bernhardt has collected from the community, talking about the impact of ECP and what they think that means to them. And so with that, I'm going to switch it over to Andrew. And Andrew, just tell me when to switch slides.
Okay, not yet. So my update is going to be tightly focused on the application development areas status in meeting KPP1 and KPP2. And that's both just so it's very clear where we are, but also because I think there's some very interesting lessons for the community that came out of this process, going all the way back to the beginning, that might be useful for things that we do in the future. So next slide, please. I want to start off with 3 high-level observations about AD and ECP that are going to be relevant to everything that I say subsequently. You can think of them as just misconceptions or clarifications, if not for you, maybe for me or somebody else, or things I hear commonly. And I'll start with number 1, that ECP in application development is sort of a code porting exercise. And of course, these terms all need to be defined, but by code porting, I'm thinking of things at the implementation level, data layout, loop ordering, structuring code to run on accelerators. Well, of course, that's all very important. If we move to the right, that is not what characterized ECP and what made it special. I like to think of a very holistic rethinking and restructuring, yes, of the implementation, even of the algorithms in a hardware independent sense, computational complexity, of the physical models, of the prioritization of the physical models based off of what the hardware provides. So it really touched all aspects of the computational science from the application development standpoint. Second one is we have this ecosystem with a massive amount of enabling computational technologies living side by side with application development and the hardware. And we may be tempted to think that the application development teams are consumers of the software technologies. And of course, while they are, and while this was a big surprise and a huge success of ECP, the degree of integration, I would still caution people not to think of it primarily as an over-the-fence type of collaboration. I think if we move to the right and we think of more of a software application, very tight code design loop as being more typical, where from the software technology end, the capabilities are developed, they might be deployed, integrated with the applications, and the abstractions are better understood, they are modified, capabilities are accreted into the software technology. And as this sort of cycle continues, the software technology becomes more broadly relevant, not just to ECP applications, but possibly clients, broadly in the community. And eventually, maybe there is a greater decoupling as the abstractions are better identified. But at this phase, at the very least, these are very close and tightly integrated components of the project. And I think that realization and the shared fate metrics and the way that we were structured fostered that and led to a lot of the success that I'm going to talk about. And then the third one is this idea of a kind of traditional do-it-yourself application group with a lot of domain experts and very good programmers, but minimal dependence on external software. And while that actually has value for risk mitigation and historically was popular, although not always, obviously, I think if we move to the right, it's a much more realistic depiction of what happened. So Exascale hardware is very complex, and the teams needed to rely heavily on expertise and tools provided by a very broad ecosystem. So that includes what Mike will talk about, which is the software stack and things that were developed in software technologies. Lori mentioned the critical role of the leadership computing facilities, people with expertise at the hardware algorithm interface for the particular machines that are being deployed, also with domain expertise, are probably the most critical ingredient to meeting our KPPs. Centers of excellence at industry at the vendors also provide great expertise on understanding how to use the hardware. And then the teams themselves being composed of diverse expertise, which we have experience with through CIDAC and other similar programs. But I just want to emphasize the importance of the range of different types of expertise that reside within an application group itself. Okay, so these are sort of high-level perspectives, and they inform a lot of what I'm going to talk about. So next slide, please. So I want to look specifically at the current state of the key performance parameters for application development. They are KPP 1 and 2. And you're looking now at our workflow, which starts at the left, which is a successful execution of an individual project's KPP, all the way through to the right, which is when it's formally considered successful. And I want to make this distinction so when I show our status, you understand in what sense we might be finished or near finished and what work we have to do. And I also want you to understand the latency of this process. So this was took us a long time to formulate this, but from the time that on the left, the team actually completes its challenge problem and believes they're done, there's a lot of work to collect all of the evidence and to store and document the artifacts that would convince someone that this is actually the case. And a report has to be written. This can take weeks, this process. But once this is done, this is first sent to leadership and application development for ECP, but then shortly thereafter sent out for external review. Of course, there's a latency associated with getting the reviewers to prioritize and eventually give the review, but then we often see an iteration where more evidence is requested, clarification, maybe something significant needs to be addressed, but that iterative loop can take maybe even up to a month. And when hopefully finally the external reviewer is satisfied, they give their signature saying that they certify that this particular project met their contractual obligations for their KPP. And then finally, it goes for final signature to the federal project director, who might have some issues, normally would sign off after reviewing all of the evidence, but that stage still has to be completed before we are finally considered totally complete. So you see why early in the summer, we were aggressively trying to meet as many of these as possible because of this long process that we've had to go through. Next slide, please, Lori. Now we're going to look at where each application project resides in that workflow, and we're going to start with KPP 1. So KPP 1, just to remind people, are the applications that have to meet a particular performance metric based off of a figure of merit, which I'll talk about a little bit more in a minute. Let's start from the right. We need 6 of 11 to meet our threshold. 5 of 11 are totally complete according to the workflow that I just told you about. If we move 1 to the left, 2 more have been signed off on by the reviewers. So they are just going to be passed on to our federal project director. I don't see any issues. If they're signed off on, then we will have met our threshold. So if you hear rumors that we have or haven't, it's that last little piece that makes up the difference between formal completion and where we are. If you go 1 to the left, the arrow to the right on the project called Exalt, which is long time scale molecular dynamics for materials, is a verbal consent, but we don't have the signature yet. So very close. And then we did get some feedback from the reviewer for the climate project on the bottom, but we don't have a favorable review yet. And then I'll talk about the projects that haven't yet met their KPPs in just a second. Next slide, please, Lori. We're going to do the same for KPP2, as shouldn't be a surprise that we're not as far along. I'll start from the right. We need to make 5 of 10. We have 3 of them totally complete. We have 3 others that are under review. The top one, Games, has gotten sort of a verbal sign off, but we don't have it officially yet. That would make it number 4. So we do have reviews for our power grid project at the bottom. There's going to be a little bit of work that has to get done this week. We're not quite sure how long it will take, but we need either that one and or additive manufacturing to be signed off on and then eventually get through the federal project director before we've met our threshold for KPP2. So there's a little bit of work left to be done, no question, but we're doing very, very well. Next slide, please, Lori. I want to focus on the 6 that have not met their KPPs yet. And I'm not going to read everything here. I want to make a sort of general characterization. First thing I want to really emphasize, this is in no way a statement about the progress of these projects. You could be on the leading application of ECP and just get very unlucky. You just happen to be doing something where there's a bug in the runtime system or compiler that is very difficult to resolve. So there's no real way to compare applications in this kind of way at all. We're just trying to get as many complete as possible. So I noticed that 1, I have the highest risk level on, which is, I'd say, unlikely. I talked to Paul Kent this morning. Things are improving. They have run into a lot of bugs with the OpenMP offload implementation. A lot of them have been resolved, but every time they think they've gotten over the hump, there's another thing, and they're able to run on 2250 nodes, but they're getting failure past that, and they're doing everything they can to be able to meet their KPP on time. Eventually they will. It's not certain if they will by the end of December, which is our deadline. For the others, everything is likely or possible. There are kind of two different camps. There are people who just got very unlucky and ran into bugs that are very hard to track down, and they're working with the Leadership Computing Facility and with the vendors to prioritize them and try to fix them. There are a couple of projects where there's just a lot of development that had to be done. They're very new, and the focus was on new algorithms and not so much testing and executing the codes early. And I'd say in one case, maybe Teresa would agree with me, for NWChemX, there was a loss of some expertise in the project a couple of years ago that might have slowed them down a little, but I'd say they're on track and are expected to meet their KPP. I'm not aware of any obstacles by mid-October, and certainly by the end of the project. So let's say 3 of the 6 of these will make it. And if that's true, then Lori's assessment of how many we'd make overall is probably consistent with what I'm showing here. Okay, you want next slide, please, Lori? I want to talk a little bit about how the systems are programmed. It's a question I get a lot, and it's interesting. I'll just make a few points. And it's a little harder to characterize than it might seem for number of different reasons. But we did do a study that attempted to track this and track some aspect of changes over time. I mentioned one of them here, but I'll just show on the left the programming model, or the principal programming model. The y-axis isn't exactly the same as the number of projects, because some projects have multiple codes. And it's even possible within a very large code to have multiple strategies. So there's a larger number than you might expect, but this is all described in the paper that I have referenced below. So there was a migration from Fortran to C in the process of doing everything else by 3 of the projects. I think with the recognition that all of the tools and technologies supported that are integrate with C are better supported earlier than Fortran tools. So I think as a risk mitigation, they decided to just sort of make the leap. But I think the interesting thing is on the right, we kind of bin the programming models into 4 different groups. There are the sort of native GPU models, which is HIP, CUDA, DPC++. There are loop pragma models, which is mostly OpenMP, can be OpenACC, or it can be something custom. And then there are sort of the high-level looping kind of descriptive models, mostly Cocos and Raja. We have one project that uses Oka. And then we have projects that really don't directly program to the GPU, but depend on a tightly integrated enabling computational technology that we call within the Code Design Center for doing things like adaptively refined meshes or particle and cell or whatever the particular abstraction needed is. And there's a, not an even distribution, but there's good representation in each of these groups. So you cannot just characterize very simply as a dominant approach. There's been some migration that we talk about in the paper, but people have tried very different things. And if you look at the teams that have not yet met their KPP, there's no real story about it being because they use one of these or the other, with the possible exception perhaps of bugs in OpenMP, although there have been some very successful projects with OpenMP as well. So now I want to take a little turn here and be a little philosophical. So next slide, please, Lori. So in the early years of ECP, I want to take a deeper look and go back one.
Okay, sorry.
Introduce it first, and then I'll dive into it. Otherwise, it'll be confusing. So in the early years of ECP, we spent a lot of time and effort defining and refining and getting feedback from everybody on our metrics for success, the things that I just described, what our status is with, and our sort of process for going through and defining project success. And now that we're nearing KPP threshold and have finally executed this process and gained a lot of experience, I wanted to take a look back at some of the key decisions we made in the early years. One, I think it's important to get a sense when I say we've completed this KPP, what that really means, because it could sound sort of simple and empty. And I at least want to convey the fact that there's just a lot of work and thought that went into this. And also because there are a couple of interesting lessons that I think we learned. Some things I would have done a little differently. Some things I'm happy I did the way we did, but I have a series of just a few reflections I'll try to do in just a couple of minutes and then wrap up. So next slide, please. Oh, I'll say first, there are sort of 3 generations of this. The first one is just defining our overall process. So that is the decision to define a figure of merit for each application independently. The FOM, the figure of merit is on a scientifically relevant challenge problem that has impact in the particular domain as reviewed by a subject matter expert. It is not a toy problem or benchmark. I put in red things that are decisions we made that I thought were different and were impactful. The next step was to base the FOM on a scientific work rate and not on hardware utilization. There are a lot of implications of that decision, some good, some made it more difficult. To calculate a formal baseline value based off of the existing 20 petaflop systems at the inception of the project, and then finally to require that that we exceed a value of 50. Then we realized immediately, well, what about codes that don't fit into this box? There is no baseline because they have not been developed yet, or the physics that we'd like to add to them hasn't been developed yet. And that's when I put in red, defined a second KPP, KPP2, that freed the community, I would say, to be more creative and to have science be more of the goal. But we still had to make quantitative metrics, such as they have to make efficient use of the resource, even if they're not targeting a value of 50. But the definition of a second KPP was a key decision. Just a couple more minutes and then I'll be done, Lori. Next slide, please. So I'll just say, I'll sort of accelerate and say at a high level, generation 2 was defining the individual FOM formulas. And that was a very deep question that we had to leverage a lot of expertise from the LCFs. And we also had to do it our own way. And I think one of the really deep questions was, how can you encourage algorithmic innovation and still have a fair measure of speed up? Because if the speed up was owing to the algorithmic change and not the hardware, then you haven't demonstrated you've made efficient use of the resource. So this is one. There are also other things like more optimized codes at the inception are penalized in a sense because they have a higher bar to crawl over. I put to the right my favorite quote that I ran into after we made all these decisions from Hennessy and Patterson's famous book about exactly this. And I totally agree with their conclusion, which is to err on the side of encouraging innovation broadly. We're in a computing revolution, and we want to do everything we can across all layers of computing in order to enable science. And there are a lot of sub-stories here. Maybe I'll tell them if anyone's interested in some future meeting, but I'll just leave it there for now. Next one, and then I'll be done. So generation 3, and there are a lot of lessons here, was writing the formal contracts that the project teams had to meet in order to say they passed their KPP years before they actually did it. And I won't get to say too much about it, but if I had to do it again, we wanted to put a lot of details in those contracts because we wanted to be credible. We didn't want to say, I'll do something big. We wanted to say, I'll do 200,000 MC tallies and I'll do 6 reactions per MC tally. But the more details you put in as you learn things, as you start doing the work, because we kind of code to think, not lay out requirements and then code it up. Then you realize if you can't do one of those things, you're in an awkward position. So you either have to let the reviewers know very early in the process that there is subjective leeway to not hold people to every single detail if your judgment is that they learned something new such that that detail is no longer important, versus just not putting in quite so much detail, but then looking like you're not making a strong enough statement. So very interesting lessons and decisions that we made. I think some were good, some weren't as good, but we've been able to work around them and execute this workflow. Okay, so I'll just say one thing in wrapping up. Last slide. Sorry, I know I have to be explicit. Okay, I just want to emphasize, I talked a lot about KPPs. The impact of success, from my view, in AD should be considered much more broadly. I'm obsessed with the KPPs because we have to meet them now. But I list a few other things, not the least of which is what Jaron talked a little about, which is scientific impact in the years post-ECP. But I think a lot of there was a lot of co-design that happened at every level. And I think of it as having paved the way for the next wave of applications to undertake the same inevitable transition that ECP did. And a lot of best practices like Lori talked about, and a lot about operating as a large community with diverse expertise, but common shared fate metrics. And then I'll also say, like Lori did mention, we are seeing a lot of success on Aurora, and we're not far and might still meet some of our KPPs on Aurora as well. And with that, I'm finished. Thank you.
Great. Thank you, Andrew. All right, Mike, same for you. Just let me know when to proceed.
Yeah, you can go to the next slide, please. And then the next slide. So in software technology, I've used a version of this slide many times, and it shows kind of a sketch of the activities and the kinds of products we've been working on. Where we've been able to make progress is yes, we've established next versions of established products. But I think in the space of robust emerging products, we've gotten rid of the emerging part. If you think of things like Cocos and Raja and SPAC, for example, in the beginning of ECP, those were not well-known tools and maybe a bit risky to take on. But now, at this point in the project, they are established foundational elements of what we're doing and really provide the scaffolding for how we're going to go forward in the future. Similarly, we've been able to sponsor activities for some new products and that are brand new and bootstrapping their way. And a couple of them in this past year received some R&D 100 awards. And so I was going to highlight those. Tap, go ahead, Tap. And then the legacy of all this effort will really be the stack that we are providing as we go forward. And it's for leadership platforms for sure, absolutely Exascale, but increasingly we're seeing that because of the design of the Exascale platforms and their widespread use of accelerated architectures, we're really talking about a software stack that will impact the desk side to the closet-sized rack to the leadership platforms to the other innovative device architectures that expose lots of concurrency and need a software stack that runs on it. Next slide, please. One of the products that received the R&D 100, led by Peter Lindstrom at Livermore, is ZFP, and it addresses this bandwidth to compute ratio issue that we see getting worse and worse from generation to generation. And it allows you as a developer to create arrays of compressed data, and then you manipulate those and use those in the design of your algorithms and the expression of your code. It's a very flexible library of capabilities. It's been used by lots of teams. Myself, I've experimented with it in the context of sparse solvers, and it provides a very nice set of tools with very rich algorithmic theory and development that sits behind it and makes this a practical capability. Next slide, please. The second product we want to highlight is Variorum. And this slide just motivates the purpose for the library. A lot of applications don't utilize the power that has been procured for them in the execution. For example, there's been quite a bit in literature about if you have a bandwidth limited computation, you don't need the clock speed of the processor to be super fast. You can clock it down a bit and drop your power consumption and still realize the same performance. And so this chart shows some of that kind of behavior across a bunch of codes. Next slide, please. At the same time, being able to manage power and tune the knobs that are available on our multi-device and multi-component processors is pretty challenging if all you have to do is use the vendor-provided tools. Very different architectures, very different tool sets, different in ways that are meaningful and sometimes in ways that are not so meaningful. And so it's a very challenging thing, if you move to the next slide, for the people who want to explicitly deal with power management to deal with if all they have to do is to work with vendor provided tools and do so across all of the different vendor architectures. Next slide, please. So Variarum was developed exactly to support people who want to work across various architectures. And it illustrates a common theme in a lot of our software products. People who are familiar with PAPI, for example, would recognize this pattern that you have an API, an interface that allows people to think about conceptual and terms that can then get translated into the specifics for each of the specific devices that the library sits on top of. And Variarum does this for power. Next slide, please. And so Variarum is this platform agnostic, vendor neutral API that sits on top of all of the various devices that we support, including all of the upcoming and current Exascale platforms. It's integrated with a number of libraries that can take advantage of this. And because of the success they've been able to show, they received an R&D 100 award. Next slide, please. And there's a lot more, right? I highlighted these two, but we have contributed explicitly within ECP to 70 different libraries and tools and advanced their capabilities in service of Exascale for sure, but also more broadly, accelerator-based architectures that and done it in a way that is portable today across various types of systems and adaptable in the future as we find and develop new capabilities, new device types that are highly concurrent. Next slide, please. Okay, I want to talk a little bit about E4S, not a lot. We've talked quite a bit about it in this meeting and also in the past. Next slide, please. So for those who don't know, or maybe it's not so fresh, this is a kind of eye chart of the things that we do and have within E4S. The latest release was on August 31st. We do quarterly releases, contained 115 directly supported products that are curated for correct execution and correct versioning. And then behind the scenes via SPAC dependency management, install hundreds of additional libraries and tools that are dependencies for the 115 that we support. It supports lots of different architectures, including all of the architectures that are in the leadership platforms in our 3 Exascale systems. And so it's become a wonderful ecosystem that we've been able to use to establish partnerships with other US agencies and industry, as Lori had mentioned, and others have mentioned. So it's a great vehicle, not only for delivering our software, but for creating rich and deep collaborations with our key stakeholders and partners. Next slide, please. In the latest release, which was at the end of August, lots of things listed here. This is a quarter's worth of work. So it's a small text, but it shows the amount of progress and activity that goes on from quarter to quarter. I want to highlight two things. One is through our negotiations, our business relationships with the vendors, we've been able to get access to things like the Cray PE, which is a programming environment for Cray. We've been able to get access to Intel's One API, which is the programming environment for Intel. And similarly for NVIDIA and other vendors to pre-test our software against their stack so that our users, when they get a hold of our stack, a lot of the bugs that they might encounter have already been identified and fixed. So it's a way of providing much more stability when we create a release of our product. And again, we can do this at the scale of E4S, whereas an individual product team would have a much harder time doing the same thing. And they wouldn't have the business relationship that we needed to cultivate with companies like Intel and like HPE to do that. So that's one thing I want to emphasize. Similarly, the vendors themselves can take our software and build it against their release candidate and eliminate a lot of the bugs and incompatibilities that might occur. And so we're able to share each other's pre-release software stacks and greatly improve the user experience. The second thing I want to mention is that we talked a lot about AI, scientific AI and AI tools in this meeting so far, and of course, much more broadly. But we already include within E4S a large collection of the most popular AI and ML frameworks that people want to use. And in fact, we support these for the GPUs as they become stable and available. One of the things I hear from people who are doing scientific work in the ML community is they are trying to manage a very fragile stack of their own with their own versions of, PyTorch, for example, and they're running into lots of issues with trying to upgrade to the next version because upgrading also requires them to upgrade other things, and that creates bugs, and they end up spending days trying to debug this process on their own. What we've been able to do with E4S, and we anticipate being able to do as we go forward, is to introduce and integrate industry standard AI and ML libraries and tools, but also be able to support those products that we are developing within DOE that support AI functionality for people who need to use it, and introduce those into the software stack, and also make those part of our curated offering as we go forward. And so we feel prepared. Of course, anytime you bring in something new, there may be things that you have to change, but as a general kind of set of tools and libraries and workflows and testing infrastructure capabilities, we believe that we can extend what we have in E4S to also support scientific machine learning and AI in general. Next slide, please. So E4S is really a first-of-a-kind collaboration between the facilities and libraries and tools. We've never been able to operate prior to ECP at the scale of coordination and integration as we have within ECP. And it's been a tremendous privilege to have the vision set by the project and our sponsors, to have a multi-institutional effort in this space in collaboration with the facilities and our users and our vendor partners. It's been a real privilege, and we've been able to, because of the scope and the time, to prove this concept in a way that I think is quite compelling. And we want to keep that going. I want to especially thank, because of the role that the facility staff have played in helping E4S become what it is, and actually making it possible, because without their work with us shoulder to shoulder, day to day, week to week, we couldn't have made it happen. And so I want to say thank you to the facility staff for their efforts in working with us and often educating us, because we work on these products, but then to integrate those into a real stack that the community can use requires that kind of fingers to the keyboard type approach at the facilities. And so their willingness to work with us has been exceptional and a great part of our success. Last topic I'm going to mention is, go next slide, please. So I stole these slides from Andrew. He said I could, so thank you very much. The only way I get pretty pictures in my talk. I want to just have you look at the FOM numbers, the FOM's speed ups on these, and see what kinds of degrees of improvement have occurred since the beginning of the project. Hundreds, right, in most instances. This is no accident, right? This is actually what you get when you put good resources, good people together, put them on top of a good software stack and using a good system, the kinds of things we can do. And what we'd like to do going forward is try to cultivate the ability for other people to get this kind of 100x or 2 orders of magnitude improvement. Next slide, please. So we've spent 7 years creating this ecosystem, this collection of approaches for getting 100x or more out of our new problems. We've been able to utilize accelerators from multiple vendors. We've been able to emphasize software quality, so people will want to use this software knowing that it's going to be a pleasant experience and be around for a while. We've done a lot of community engagement so people can know about our work. We've invested in portability layers. And so because of that, we can lower costs, we can increase performance for accelerated platforms. And really, outside of AI, where there's tremendous investment, industry is not caught up. If you look at the software stacks of, say, our other agency partners and broadly speaking in the high-tech industries, they run primarily on GPU or CPU-based scalable platforms. And so one of the things we can do is help the rest of the community and engaging with them and making it more possible, more feasible, less costly, more quickly they can move to GPU architectures. Next, please. So what are some of the opportunities? You can port to full use of GPUs. You can utilize SPAC You can utilize E4S. You can leverage our experiences. This includes Andrew's teams and the teams that I represent and the HI teams, to help you build a plan, de-risk the path towards making GPUs a part of your computational environment. Next slide, please. And what are the ingredients? Well, this is a notional recipe, right? 100x recipe. You need, I think, first of all, a compelling science impact story. You need to be able to have a good reason. You do need money. There's no doubt about it. You need staff, which is challenging, right? People who can do this kind of work are in high demand. You need resources and trainings. You need the deliverables and experiences from DOE and ECP. And then, for example, organizations like PESO, which is one of the teams doing the seedling project work, and the partners that we're working with. And then again, notional steps. I won't go through these in detail, but there is a notional path if for other people who want to do this work, who want to realize this 100x improvement. Next slide, please. And there's more than one way to leverage 100x. You can certainly do it to get exciting new science capabilities at the high end. This will always be an ambition of ours that we want to do that, but we can also use it to reduce costs. We can do migration to accelerated platforms, to do things like migrating from a cluster to a desk side, lower your monthly charges on AWS, and in general, things like keeping your energy costs in check while still growing computing capabilities. You may run a facility that runs at 2 megawatts. How are you going to continue to improve capabilities for your users if you can only do GPUs? It's really hard to do. And so I think our biggest impact from ECP will be accelerating this GPU transition. And specifically, migrating to GPUs is one of the really attractive ways to address energy efficiency concerns for HPC. We see this in the news, right? That HPC, in the AI space in particular, but more broadly, that it's expensive, right, to do high performance computing. And what can we do to reduce that cost while not impeding our progress? And one of the ways is to move software stacks from CPU-based scalable systems to GPU scalable systems. And you can go from having just a few % improvement from generation to generation in energy efficiency to multiple times improvement. And we would like to be a part of that process. Next slide, please. Okay, so some takeaways. Lori mentioned we achieved KPP3 officially as of September 15th. We went back and looked at our records. We believe the legacy of ECP includes this collection of portable libraries and tools, ready for today's platforms, but also because of the architecture of the software, we're ready to adapt to future systems. We've de-risked the path through all of ECP for others who want to go in this direction and have the opportunity then to assist in this 100x improvement across a lot of scientific domains. And it's also a way for us to address environmental impact concerns. And our next steps include continued engagement with the facilities on the delivery of software via E4S and cultivating the impact in collaboration with other agencies and industries. And I think we're really just getting started. My hope is that if a junior staff member joins the DOE Oscar community 5 years from now, they will wonder, haven't these software capabilities and these platforms always been around? It's always been this way, right? And we'll be able to say, no, it wasn't always this way, but it is now. And I'll stop. Thank you.
Thank you, Mike. So just in conclusion, I just want to say a big thank you to everybody who's been involved with the Exascale Computing project, all the team members, the leadership team, the project management office, our sponsors. It's been a tremendous project. And I am hoping that we'll have one more opportunity to address this fine committee when we are done. So maybe in the next meeting. And then this is just a summary of the looking ahead. And with that, we'll just open it up for questions.
All right, I see Martin and then Bruce.
Great job, guys. Fantastic project. Great presentations too. I think this is a model for how these things should be done, and you should be justifiably proud in the way that you carried this through to completion, and it's made a huge impact on the software base. Couple of questions that came up though. I was very interested to see your moves to HIP from SYCL, and I guess I understand why. And it's certainly been what I've seen, that the software stack on on Aurora, while it's firming up, has been more than usually fragile. Let's just put it like that. And that's been a problem. And we've seen some more of that with the challenges that some of your projects have faced with OpenMP and everything else. I mean, is that an impediment to sort of getting all the results that you would like to get on Aurora, or is that just half of the course, do you think?
So Susan is on, and I believe she's empowered to speak. I believe it's kind of par for the course. I mean, we saw some similar kinds of issues as Frontier was coming up. We're seeing it as Aurora is coming up. And so, you know, more fragile, less fragile, they're all kind of fragile in the beginning, from what I can tell. And we originally did this effort, again, this was 2 or 3 years ago that we started it as a risk mitigator. You know, at that time, we weren't sure Frontier was going to come up, and we had a lot of codes that were really targeting Frontier. And so at the inception of that project, it was about risk mitigation. And now we were seeing a lot of additional benefits as well.
Sorry, yeah, that sounds good. One final point is
yeah.
You know, one of the challenges of a big project or any project is making sure that the people who are in it have good outcomes coming from it. Have you taken any kind of study to try and understand what the outcomes are for the people on the project and how they are moving forward in time, you know, once a project ends? I realize within this number of people, that's a challenge, but I wonder at least if you have a perception of where you fit in terms of the work, this amazing workforce that's done fantastic work.
Yeah.
And, you know, is there other challenges to be faced there, or do people feel that they have a good future? And have you quantified that in some way?
We have been, you know, working with the project teams to just understand their current status. And so we've been collecting that information and, you know, passing that up. Of course, you know, their long-term future is a little bit outside of our, well, it's outside of our control, but we have been working hard to just make sure we understand what the opportunities were, encouraging teams to go after those opportunities, tracking when they're hitting successes. So we do have that information that we've been tracking, Martin.
Yeah, for every AD project, we have a one-page slide, which includes what programs they've applied for post-ECP, which ones have been funded, which ones they plan to apply for. And we talk to the program offices frequently to at least let them know what has been accomplished and ideas for using the tools that were developed for future scientific campaigns. And I think that, you know, the story is very mixed, but we track that information carefully.
Good, thank you.
Bruce?
Yeah, so I want to echo Martin's accolades, both on the presentations and more importantly on the overall success of the project. I mean, just phenomenal accomplishments all around. Congratulations to everyone on the team. Mike had some remarks on one of his last slides about the legacy of the project. I think he's missing something really important in that list. I think that this project and your leadership of this project has transformed the community in a profound way. So if you remember back at, you know, it seems a long time ago, but pre-ECP, we had many different competing software stacks, many different instantiations of similar overlapping competing tools. And now we emerge from this project with a community software stack that has been hardened and co-developed by many people across the community. And it will, at least in my view, be the basis for the next decade plus of developments in the field. And so you've positioned, you know, both the technology developers, but also the application scientists in a very different way than we were set up before. And I think that's a really profound legacy.
Thank you.
So that was it. Not a question, just a comment.
Thank you.
All right, Ed, I think you're next, and then Karen, and I see Roscoe.
Yeah, thanks. I guess my question was partly answered, but I guess I wanted to, well, first of all, I'd say it's really exciting to, I've been watching this for a long time and participated in some reviews a few years back, but I just wanted to drive home the concerns that Jack has been hammering, you know, about the staff and the concerns about, are we going to lose staff and so on. You kind of got to this, but I mean, how are you really feeling about where that is all going for the future? I guess that was my main concern.
Is that a question or just a comment?
It's a question. I mean, yeah, just a little more commentary on how you feel about the stability and the future of the staff that have spent a lot of years on this.
Yeah, I mean, we've been tracking it and, talking a lot with the leadership at the labs in particular, where we have a lot of insight. I think in general, things look pretty good for FY24 for the staff. Most folks have found a home. It may not be exactly in their key research area. I know a lot of the facilities, like the OLCF and ALCF, have been leaning in to help pick up some of the ECP staff that are coming off of the ECP projects. I know that Oscar has been working with opportunities on bridge funding for some. So I think in FY24, it's okay. I think a lot of concern, I hear a lot of concern still about FY25, but there's still so much that needs to be developed between now and FY25 that it's, hard to predict exactly what that will look like. But I think that's where most of the concern that I hear about is right now, is a year from now.
Let me add. So my head is completely immersed now in planning for post ECP. We're putting lots and lots of energy into what that might look like, at least within the scope of the software technologies and co-design projects. And one thing that's happening is our budgets are going to be lower, at least initially. There's no doubt about that. But it's forcing innovation and it's forcing even deeper partnerships and deeper levels of trusting across the work that we're trying to do. And we're going to be able to leverage the investments we made in ECP to look for even further opportunities to leverage and increase and integrate our activities. And so while it's very painful, I have to admit, to be frank, to be involved in some of this kind of rescoping activities, there are going to be some really valuable and even tighter collaborations that occur, because there is no other way that we can get our job done other than to further trust and collaborate with each other.
I think the part that's hard to track, Ed, are the people who leave voluntarily because they're not working where they think they can make an impact.
Yeah.
And, people talk a lot about RIFs, and I'm sure you can collect data on those things. I know nothing about it, but it's when someone doesn't contribute where they think they can contribute most effectively, it's very hard to sort of track why someone left. And I think that there is those concerns because there is no natural follow-on to something that people have been doing for 7 years, and they're deeply entrenched and expert in it. So it's just another way to look at it, I think.
Yeah.
Sure.
Thank you. Yes, I want to first echo the accolades. I mean, I've been, of course, tracking, and that was in the early days of some of the studies towards Exascale where we did not think it was even possible. And so it's just amazing to see, all that was accomplished, that this incredible initiative was happened, executed, and so well, and made so many contributions. Along those lines, I mean, we in this community, in this group here, are very familiar with these accomplishments. And some of it has been, of course, communicated externally. I wonder if we can do more. This is just such an incredible story. It really is an incredible story. And, so just want to put that out there. I wonder if we can do more in terms of external communications.
Yes.
The contributions, some of the stuff that I'm more familiar with, the hardware side of it, Mike, and some of what you talked about with the power and the APIs. I mean, those are not small things. Those are big things.
Big deals.
Yeah. And this, my second part was, the concern for the staff, and that's been addressed, and I understand that. So I'll stop here, but thank you so much.
Yeah, thank you, Karen. As I was mentioning in my talk, I went through it kind of quickly. We're working really hard on that broader communication and telling our story. So we now have a cadre of writers. We used to have 2, now we've got 6 or 7 that are working with the teams, that are working with the leadership to craft those stories that can be broadly accessible. Set up a series of meetings with the PIs, one to educate me, but we had a writer attend all of those as well. And he's now working on writing up those blurbs in ways we think my mom would understand, right? And so, yes, we are really focused on trying to get that message out, because we do think it's an incredible story.
That's really good to hear. Wonderful. Thank you.
Bosco?
Yeah, I think people hit on almost all the things I wanted to make sure to raise, but again, I congratulate you, and I'm sorry we could not have helped make a smoother path for this transition. We certainly envisioned one that would be smoother than the one that's actually happened. So I'm a little sorry about that. I would also say that I'll also pick up on the issue of identifying some of the external impacts. So I think particularly of sort of the future evolution of people involved in the industry advisory committee and those connections, the broadening participation at a bigger scale that we talked about earlier. That also represented a significant change, and something we talked about in the transition report, and was one of the questions, which the international impact of these activities. I know you don't report to us in DOE talking about money with that, but I think that's an important aspect of the long-term legacy of the project. And so I don't know if there's anything to say about that now, or maybe that's the next time we talk about the report, but I am curious about your sense of that.
I can tell you, planning for post-ECP, that all three of the things you mentioned are important aspects of what we are going to do. The industry and agency collaborations, we intend to carry those forward and in fact, make them even deeper and richer. Make them, so that we can more quickly, we need to build trust, right? We need to build trust. A lot of these early meetings have been about building trust. First of all, getting understanding, common understanding, then building trust that maybe we can actually do things together. And we're now to the point where we're actually talking about and planning to do things together. I foresee as we go forward that will be coming even deeper, and it will just be a part of everyday life. The workforce aspects of it, Lori highlighted some really, really neat formats that we've been able to, in collaboration with many people, right, to bring new people into the field in ways that are absolutely essential. And we're going to keep that going. We're going to get better at that. And then the international collaborations, didn't highlight those here, but we have a number of them going forward. And people outside the US know what we're doing. Our collaborators internationally know what we're doing and see the value and see the possibility for partnerships.
Thank you.
Yeah. What's your comments? I just want to echo what others have said. I mean, this has been a Herculean effort, I know, politically, economically, and technically, and just huge congratulations for getting to the finish line with a few twists and turns along the way. I think we're all want to ensure that what has been created is preserved and not lost in this transition, and that's people, but it's also the spirit of collaboration and frankly the resources to maintain stuff too in the face of such a big technical transition that we're seeing ahead of us as well. So we'll keep fighting the good fight, but I think we all are united in both gratefulness, but also our shared concern about how we continue to do things together.
Thank you, Dan. I will say that I have heard over and over again that the ECP has been our team's favorite project that they've ever worked on. I hear that over and over again. I think it's the duration, the collaboration, all the things that you just mentioned have made it just a truly special project for the DOE.
Yeah, very true.
Well, those are the things people remember. If you ask people and they talk about the defining experience of their lives, then you've been successful. All right, we're going to shift on. We're a little bit behind, but not much, to energy exascale Earth system models and a project update. And so the floor is yours to pick up with slides and go forward.
Okay, thank you, Dan. Okay, let me see. I share my screen.
I'm sorry, Dan, we flipped the agenda. Tony was supposed to
Yep.
go next so that we could get a vote in. I'm very sorry, Shusheng.
No problem, no problem at all.
All right, this is the agenda I just literally downloaded from, so.
Sorry,
about that.
sorry, it must be cached. We wanted to get the vote in earlier.
That's right. Okay, Tony, then go for it.
Okay. I can find my talk. See if that should do it. Can everybody see that?
We can, it hasn't gone to single slide yet, but we can see them.
It says Zoom quit unexpectedly. Very helpful.
I can still hear you. And I can still see the slides. They're just stuck in the 4-slide format.
Still tells me I'm quitting, but okay.
Right. Okay. Hopefully Tony will be right back. Let me see if we can pull up his slides.
Tony, you're talking, but we can't hear you.
Yeah, sorry about that. Can you see that now?
Yes.
Good. Okay. So this can, I think, be very brief because I gave a much. I've got a Zoom quit unexpectedly message, which is going to crash me in a moment. So why don't you show the slides? You have them.
Or did we lose Tony? Or he's coming back? Well, we have a blank screen of Tony.
I'm going to share his slides, but we do need him to talk. So, but he did give a much more detailed version of his talk at the last ASCAC meeting. So hopefully it will be quick when he does come back. I need to figure out how to share slides. Got it. Okay, can you all see the slides that I'm showing?
Yes.
Okay. I will pinch hit for Tony and until he comes back. That we all saw the charge at the last meeting. And we all remember who the members were. If any of the members who are here, Rick or Susan or Martin, want to take over at any time, please feel free. The original name of this collaboration was JADAX4C. We now just call it the NCI-DOE collaboration. There were originally 3 pilots, and there was a cross-cutting project under ECP called Candle. This year's review, they did a face-to-face meeting at the Frederick Lab right before our last ASCAC meeting. And then they divided and conquered, and they had 2 subcommittee members lead the review and also the writing of the report. And their names are here. The executive summary version is that the Mosaic project is a mature project, and it has been very impactful. It has been working with 16 SEER registries, and they are also working with the VA. And the subcommittee was pleased to see the exploration of the foundational models to SEER data. That's another approach to the privacy concerns about the SEER data. Has everyone who's ever had cancer ends up in a SEER database somewhere. And so the privacy concerns are an important part of this project. And it has been able to leverage the Citadel capability at the Oak Ridge Leadership Computing Facility, which has just been ported to Frontier. So I'm very pleased to be able to share that. But another approach that they're looking at is through federated learning. The Admiral project is a very ambitious use of our multi-scale models, but also incorporating machine learning to inform the handoffs between the different scales of the model. It is focused on RAS-RAF. It is part of NCI's RAF initiative. They have made very good progress this year on introducing a more powerful AI-enhanced modeling capabilities. There's very good feedback loops with the experimental work that happens at Frederick National Lab, and they felt that the results that they shared were impressive. This team is also getting ready to run on Frontier, so they either Mosaic or Admiral will be one of the first other agency exascale applications, hopefully. The Improve project was a new project when we shifted from pilots to projects, and it's only its second year, but the committee found that it has made significant progress toward creating a community-based framework for a cross comparison of AI models used to validate cancer drug response. The code-based documentations are available on GitHub with data and curated models. So this is a bring your model comparison effort, and there's also an effort that's they're going to be adding, which is generating data that is specific for model improvement rather than training. So that's the executive summary. And again, if the subcommittee members want to jump in, they're welcome to. They also did a freebie review of the Candle project. It is reviewed as part of the ECP. It's one of the KPPs that have been achieved and is going through its reviews. But the goal was to deliver a viable exascale optimized software framework for deep learning. They've got benchmarks. These benchmarks are very helpful for the facilities as well and to the NCI projects. All of their milestones have been delivered, and they also shifted to looking at COVID and proving that the framework works on other aspects, other diseases. And they did receive a Gordon Bell Special Prize last year for that work. There's also some exciting stretch goals coming out of the Candle project on DOE transformers. They also joined forces with ExaLearn. The foundation models that they're training are getting ready to run on Frontier and Aurora, and they're sort of leveraging the ChatGPT infrastructure. The town halls for AI for science and security that met in 2022 identified other opportunities to use these foundational models for science, and they are developing international consortium to develop a trillion parameter model using NVIDIA's Megatron and Microsoft's deep. I can't quite see the end of that slide. But the Microsoft code base for training. And I don't think he intended to go through the detailed project reviews because they're exactly the same as they were in June. So I'm going to stop sharing. And is Tony back? Still no Tony. Okay. I think that's the report. The report was distributed to the committee and posted on the website, I think last week. So does anyone have any questions that I could try to point to someone on the committee? Go ahead, Jill.
Jill does.
Yeah, I had this question when Tony presented last time also, and I still have this question because I think that there's not enough communication to the NCI funded community that are working on these predictive models for the model evaluation. I know a large percentage of the people that are working in this area, including myself and other colleagues of mine, and there's really not much that's been done in terms of outreach to exactly the community that we would want to be using the platform and the framework, especially because you want that done sort of early on before everything gets hard baked. So I'm wondering if this communication, or I hate to call it marketing, but that's really what it is. I mean, is it just that it's hidden? Is it really happening? How can we make suggestions to have them improve that?
Yes, we did hear your comment on that. And I know that's been discussed between DOE and NCI. One of the problems is, of course, our people tend to publish in our journals and go to our conferences, and they're not the same. And I know the Improve project has done a lot more. They've got a hackathon scheduled, and they've been much more engaged in different workshops in the NCI space.
But somehow hackathons are not the right place to do it. The right place to do it are things like ISMB, to get in touch with the people who run the ITCR program, to do it at an ITCR, either annual meeting, or the PIs meet every month. And we often have outside speakers at those. There are at AACR, you know, there are lots of opportunities in exactly the space where you want people to know about that work. And I know that from the beginning of the DOE NIH collaboration, even before I was on this committee, we talked about the fact that this is going to have to really involve the community in an important and quintessential way. And the RAS-RAF project, I think, has been working really well over the number of years that it's been going on, because it started with the RAS-RAF community, really, with Fred McCormick, right? And so you had exactly the right community involved. So I just think this is, you know, I'm not arguing about the quality of the work. I'm just arguing about how we're going to get the uptake and how it's going to have an impact on exactly the community you want it to have an impact on. Broken record, I guess.
Right. No, I hear you. And we are working with NCI. We have been at AACR, and we have done talks on all of the projects, I think, now to the Cancer Moonshot community, those virtual talks they've been doing. But I will mention it to Emily, and and I'm sure we will discuss it at the executive committee meeting will be coming up in the winter. So we will definitely take it to heart. But that's more of an NCI challenge than Oscar, because it's not our community, so we don't always know where the right places are.
But you can give them the feedback.
Definitely. And I see Martin has his hand up.
Yeah, I was just going to say that there's a good points that Jill makes, and you know, but the RAS-RAF one for sure, but also, you know, Mosaic has also been looking at the working very well with the community. I mean, it's based on, you know, there's interaction with all the local centers. They interact, for instance, with our local Huntsman Cancer Center here in Utah, and so on. And with regard to the sort of Argonne effort, you know, Candle is one of the main mechanisms for sort of those interactions, and Candle, we heard, has been downloaded many times and used. It might be useful to have a more formal tracking mechanism for the use of Candle, and to understand how it's being used and where it's being used. We didn't see that at the last review, but it would be a good way of addressing the points that Jill raises about how the community is interacting, and for sure it's very important to have those interactions. As I say, the Oak Ridge, I think, have done a really good job in terms of working with the cancer community, and indeed they have to do. They can't do what they're trying to do otherwise. And as I say, the intention, you know, Candle, the software has been out there a lot, and so I think there's probably more going on than might be visible, but it's a good idea for sure to make it visible.
Tony, I see you're back. Please jump in.
I am back. Yeah. Have you shown? I'm going to show 8 slides.
I showed your slides. I went through them. Sorry for the technical difficulties.
No, that's fine. No, I hear the discussion, and you've got, you know, Rick and Martin there, who can actually, who were at the meeting and can talk about their projects because they reported on them. No, I think in the thing I added to the report from the review that I presented in June, it was an executive summary, which was very brief, pointing out that actually each project has a strength and they're doing really well. And I think that DOE actually has a success on the hands where the supercomputers are really being used to assist the NCI and the cancer community. So I think it's interesting set of projects, and Candle has supported it very well. For example, in the Improve project, makes use of a hyperparameter optimization service, which was launched by Candle in March 23. So I think really it was very successful. And I should have said Candle won the R&D 100 award this year also. And I was going to say something about the stretch goal for a large language model, but I think if you've shown the slides, that's just fine. I'm sorry I missed Jill's question. I apologize to Jill for not being there.
That's okay, Tony. I just, I'm like a broken record. I just raised the issue again about, getting it out there that the framework for evaluating predictive models exists and having people use it and kick the tires before it's fait accompli and hardened. And it's the same comment I think I made when you presented in June. So.
Yeah, no, so that's right. But I was impressed that the Improved project has looked at 16 AI models and actually got some uniformity and some methodology. So I think they've made great progress. And with Candle, that's been, I think, quite a success. And the other two projects are very different. Mosaic is very mature and is used by essentially all, a large percentage of the SEER registries and the VA. So I think really you have a success on your hand. And then the Admiral modeling project is a very ambitious project and is supported by some very innovative experimentation. So I think they're great projects. And I hope the report emphasizes that.
Any other questions or comments? All right, then the item that follows is to ask if there would be a motion to vote to approve the report.
I'm happy to move such a motion.
Okay. Second.
I second.
All right, any discussion? All right, those of you on the committee, all in favor, say aye.
Aye.
Opposed?
Aye.
No? Any abstains?
Aye.
All right, done. Okay, thanks, Tony, and thanks, Christine, for stepping in and doing a quick presentation on behalf of Tony while he was fighting a non-Microsoft technology.
Well, actually, this was working just fine. It was when I started sharing screens that it went screwed up. Otherwise, I've had perfect reception all morning. Okay, thank you very much.
All right, thanks, Tony. All right, as usual, I apologize. We will now go back to you for the Earth system model presentation. My bad earlier.
No problem. Thank you, Dan. And I hope I will not have any issues so Christian has give my talk too. So let me share my screen. Let's see. Oh, do you see it? Do you see my screen or hear me?
Yes, you can see it, but it's not in presentation mode.
Let me try again. How about now?
Yes, perfect.
Okay. So yeah, it's my great pleasure to be here today. So I'm Susan Davis, Program Manager of the Earth System Model Development Program Area, or ESMD, within BER Program Office, with the main goal to support the development of DOE's Energy as a Scale Earth System Model, or ESRSM. And within this scope, I'm also a BER Program Manager for the SciDAC partnership with ASCAC and also ALCC. Today, I will tag team with Dr. Luca Battagna, who is a computational scientist from Sandia National Laboratories. He is a critical member of ESRSM, simple cloud resolving ESRSM atmosphere model or SCREAM, as Jeremy mentioned earlier. Also, he is one major author for the recent ESRSM Golden Bell Prize paper submission. So I will focus on the DOE program perspective and also overall project update. Simply about ESMD. ESMD is one of the three program areas of the Earth and Environmental Systems Modeling Program, or EESM, within the Earth and Environmental Systems Sciences Division, or EESD, within Biological and Environmental Research, or BR Program Office. Within our division, all the program activities are guided by and support the division strategic plan addressing 5 grand challenges: the integrated water cycle, biogeochemistry, high-latitude processes, drivers and responses, and observation model integration. And there is close collaboration between BR and ASCAC, mainly through the SciDAC partnership, with focus on the Earth system model development activities. ESRSM, simply speaking, is a DOE model on DOE machine for DOE mission. And the goal of the ESMD is to support the ESRSM development to address the grand challenge of action predictions of Earth system variability and change, with emphasis on the most important scientific questions relevant to DOE mission. The development strategies include to drive model development with scientific questions centering around the water cycle, biogeochemistry, and corrective processes. And we aim to develop an integrated Earth system model, including all Earth system components: atmosphere, ocean, land, river, CS, land ice, also human component, across different temporal and spatial scales. We do this by pushing high resolution frontier, by bridging gaps in skills and processes, and by quantifying uncertainties through large ensemble simulations. At DOE, ESRSM leverages the department's world-leading HPC capability from ASCAC for computational advances and scientific leadership. In addition, ESRSM also integrates the innovative mathematical, computational methods, tools, and algorithms to model development, mainly through the SciDAC partnership. Within the ESMD portfolio, ESRSM project has more than 60% of total budget, is a central driver for ESRSM development. The project is tasked by DOE to deliver major versions of the model within every 3 to 4 years, with significant advancements from its previous version. Therefore, ESRSM project is on a rigorous model development cycle. It has very focused scientific questions over long term and each phase, with well-defined timeframes, well-designed goals and strategies. Other projects within the ESMD contribute to ESRSM development in different ways on different timeframes. For example, the SciDAC projects from the second largest portion of the ESMD portfolio are to support deep, necessary collaboration and integration between earth science scientists from BR side and the computational mathematical scientists from ASCAC side to tackle modeling challenges, also to prepare the ESRSM model code for future computational architecture advancements. ESMD also supports other lab projects to address modeling challenges or to address ongoing DOE priorities. ESMD also supports the Office Science-wide Early Career Awards, and also to entrain fresh talent from the university community through funding opportunity announcements. Also, with a relatively small budget but very important research activity, ESMD supports the interagency and international collaborations. One good example is the SATS consortium with DOE as a main sponsor, and with the participation of other agencies in US and in Poland, Finland, and also Canada. Right now, SATS is the most widely used CS model in the CMAP modeling community. So ESRSM is a ESMD ecosystem. In addition, it's also part of a larger DOE ecosystem, mainly the ESID programs and also some projects from ASCAC. In this, ESRSM provides modeling capability for others to address DOE relevant questions, and also integrates the knowledge gained from others, including the observation data, the new propositions, or diagnostic tools to inform future development. In addition to SciDAC partnership with ASCAC, ESRSM also benefits greatly from the ASCAC's ASCAle Computing project, or ECP, which also mentioned more later. So the ESRSM project team has more than 100 scientists from 8 DOE national labs and multiple universities. So ESRSM is really a cross-laboratory initiative in Earth system modeling. And this is such an amazing team that we have. The ESRSM leadership team also reflects such nature. In my mind, such an effort like ESRSM is only possible at the DOE by bringing together the uniquely talented scientists covering a wide range of model development expertise and also the world-class facilities and capabilities at our lab. Here is a snapshot of ESRSM's status, major timelines, and achievements. The project started in 2014. ESRSM version 1 was released in 2018. After that, ESRSM became an open development project. ESRSM version 2 was released in 2021. Compared to version 1, version 2 is a better and faster model with regional refined modeling capability, or RRM, in all its components. Currently, ESRSM version 3 is under testing and is on track to be released by the end of the year. We are expecting exciting advancements, especially in the atmosphere component with much improved physics. ESRSM version 4, planned to be released in 2026, is envisioned to be a GPU-enabled, fully coupled ESRSM, providing foundation for digital twins of the Earth system regionally and globally. In past January, ESRSM project started its phase 3. And in February, the project started realizing the Exascale vision the project set at the very beginning, almost 10 years ago, by developing the first benchmark of its kind through running 3-kilometer global simulation of SCREAM on Frontier, the first and fastest Exascale computer of DOE, with record-setting performance of more than 1 simulated year per day. This result has earned ESRSM spot as one of the 3 finalists for this year's Golden Bell Prize competition, the first year for the climate modeling category. So this is really exciting. And here I want to acknowledge ECP for enabling the early access to Frontier for ESRSM to make this happen. In addition to this Exascale readiness, ESRSM is also unique in its RRM capability, in the sense that it is the first Earth system model running fully coupled global simulations with RRM in all components except real world that has completed climate production simulations. Furthermore, ESRSM is also unique in its capability, including coupled Earth-human feedback components. So we are very proud of all these major achievements. And this result of not only last few years, but also almost a decade of effort. So here I want to use the opportunity to acknowledge other fellow program officers. Dorothy Koch, who initiated the ESRSM project and also led the team through very foundational, challenging first few years. Sally McFarlane, who was the interim ESMD program manager, I worked with her very closely at the beginning upon my arrival. She brought me up to speed to the program activities very strategically and in a very well organized way. And also Randall Levitt and Lily Chatterjee, who has a very many years of experience and also wisdom, whom I am very fortunate to have opportunity to work with. So just about the ESRSM, the GPU readiness, right now the project in phase 3. And in this phase, many of our major simulation campaigns will be still using the Fortran code running on CPUs, but we do have a few new GPU capabilities, including in the atmosphere component, the SCREAM version 1 cloud resolving simulations, and the multi-scale modeling framework, MMF, thanks to the ECP contribution, and also high resolution land simulations, and also the ice sheet component, mainly simulations of the entire Antarctic ice sheet using the RRM configuration. And the plan is to have a fully coupled ESRSM on GPU in phase 4. ESRSM has been in the spotlight recently. On September 12th, the ESRSM scientist Peter Caldwell was invited to give the first webinar for the WCRP Digital Earth Lighthouse Activity webinar series. And the ESRSM Golden Bell family status had gained a lot of recognition and exposure for the media. So here, there's a UK media article citing the ESRSM SCREAM as the American's next top model. So we are very proud of all these achievements, and we must acknowledge that this will not be possible without DOE's strong support, including BER and ASCAC, starting with the SciDAC partnership. I have to say that each component, each version of the ESRSM have benefited greatly from SIDAC investment, including various decals, trace transport schemes, and biogeochemical capabilities in almost each component. Actually, SIDAC has contributed to Earth system modeling community very substantially and broadly, even before ESRSM started. The ASCAC modeling effort is a great example in this perspective. Starting with the first project called ASCAC in 2009, then Pixies, Prospect, and Fancy, DOE Lab had been able to develop a world-class ASCAC modeling capability from scratch with SIDAC investment. Currently, we have 3 new ASCAC models that are being coupled to world-class Earth system models: NCAR's CSM, DOE's ESRSM, and also Hartley Center's coupled model version 3. The SIDAC investment also led to improved performance, algorithm, physics, and accuracy of ESRSM. The ECP project had led to a new configuration of the ESRSM called the ESRSM MMF. With that, right now, ESRSM has a configuration with a high resolution atmosphere and ideal result ocean coupled together, running on Frontier right now with more than 5 simulated year per day performance. In addition, the ECP also contributes to ESRSM in other multiple perspectives, including performance improvements, IO improvements, also different porting possibilities for ESRSM different components. So with the ESRSM's open model development practice and also broad collaboration and coordination, ESRSM really contribute to national and global endeavor in advancing Earth system predictability. To assert and maintain an international scientific leadership position in the development of Earth system models while addressing DOE mission, we must face a lot of challenges, also to advantage of many opportunities we have. For example, where we enhance ESRSM capabilities, we must address the fundamental model biases to ensure the model's fidelity and credibility. Over the next few years, ESRSM model code will be transitioning from Fortran to C++. Potentially, that there can be multiple hurdles and challenges. And also, there have been continued challenge to retain the valuable team members within the DOE system. So how to make sure we have a well-balanced and continued team of scientists covering all range of the model development expertise. Yeah, so we need to continue to work on our strategy. Going forward, ESMD will continue to strengthen the core by working closely within BR programs, including the SIDAC partnership with ASCAC, and to enhance the integration with other DOE programs, including ASCAC's ECP, IRI, and upcoming Earthshot project if they are relevant. And we will keep thinking better ways to coordinate and collaborate with other climate modeling centers in US and internationally. And we talk a lot today about the emerging technologies and the concept initiatives, such as machine learning approach, the digital twin technology, the recent new initiative in European countries, Destination Earth Virtualization Engine, and also the new WCRP core activity called Earth System Model and Observation. So how ESRSM will navigate ourselves to make sure that into the future, we still can maintain our leadership position in certain areas. Also, can we even identify new space to be successful and even take a lead. So basically, what's ESRSM like in 10 years in 2033? One thing I'm certain is that ASCAC will be essential in shaping the future ESRSM. And it's very special time for ESRSM project as we enter the 10th year. So in December, the American Geophysical Union meeting, we have a town hall titled ESRSM, a decade of Earth system modeling effort as a Department of Energy. And the project is tasked to develop a new strategic vision over the next decade, setting future vision and path. And also next fall, we are planning to have a 10-year celebration to demonstrate DOE's Earth system modeling capabilities and to inform more broader society in Earth system science, probably computational science, to what ESRSM can offer for our code and model output and other diagnostic package, etc. And also to initiate new collaboration and coordination. So with that, I want to use this opportunity to thank ASCAC for your contribution and strong support of ESRSM through the SciTech partnership, ASCAC Computing project, HPC user facilities, and ALCC. Of course, this will not be possible with the strong support from BER, the leadership, and also fellow program managers. And also, if any ASCAC scientists online, I want to also use the opportunity to thank you for you bringing your ASCAC expertise to advance ESRSM, advance BER science, and also contribute to the broad Earth system modeling science community. I will list the resources here for you. Also, I can put it in the chat box. So next, I will hand over to Luca to introduce in detail the Golden Bell Prize mission results. Thank you.
Can you guys hear me?
All right, thank you very much. Questions or comments?
Dan, Luca's going to give the other half of the talk.
Okay, that's what
and
I
Luca,
thought.
I could hear you briefly. There, now I can see you.
Can you
Yeah,
hear
because
me now?
I can see or hear him. Yeah, we can see and hear you now.
Okay, let me just get share the screen. How does that look? Can you see it?
Great.
Yep, that's good.
All right. Thank you, everyone. My name is Luca Bertagna. I'm from Sandia National Labs, and I'm going to talk to you today about the E3SM C++ atmosphere model and our journey to Exascale. I was actually hired at Sandia when this journey just started about 7 years ago. So that's what brought me to Sandia, and I was able to see the story unfold pretty much from the beginning. So I'm the person talking, but there's a lot of people involved in this journey. I listed all the people that I could remember. They come from a lot of institutions, as Sujin pointed out. It's a big project. So you already saw what E3SM is, so I'm not going to get into detail. Big model, lots of components, but a big variety of time and space scales. E3SM is mostly written in Fortran, and the snippets of code were written across several decades, which makes maintaining and port this kind of code a little complicated. But I'm not going to focus on the whole E3SM. I'm focusing on the atmosphere model of E3SM. So the E3SM atmosphere model, or EAM, is broadly speaking divided in two parts, dynamics and physics. Dynamics is what solves the Navier-Stokes equation in a rotating framework. And also the transport of traces in the atmosphere, and it's handled by the home package, which decouples vertical and horizontal operators, uses spectral element in the horizontal direction and Eulerian or Lagrangian in the vertical direction, and a semi-Lagrangian method for traces transport. Physics is in charge of approximating those processes that are not resolved at the scale of the dynamics grid. But still contribute some forcing terms in the dynamics equation. Examples include microphysics, which is water phase changes and precipitation, macrophysics, which is subgrid, cloud, and turbulent processes, radiation, aerosols, and there can be more depending on the resolution and the kind of model you want to solve. As I said, like most of E3SM, EAM was originally written in Fortran, and it was a very high-performant code on CPU-based architecture. That was the result of decades of optimizations and research. Typical production runs for E3SM that use EAM will run at a horizontal resolution of about 100 kilometers and 72 vertical layers, and I will explain in a second what those are. But I wanted to point out what the scales of typical current production runs were. So the discretization for EAM can be either done through what we call the cube sphere or the regionally refined model, but I'm just going to focus on the cube sphere because that's what we used in our Golden Bell submission. So for the cube sphere, you basically take a cube, you draw a quadrilateral mesh, a uniform quadrilateral mesh on the surface of the cube, and then you inflate the cube until it reaches the shape of a sphere. And the number that is important in this context is we refer to as NE, is the number of elements along each edge of the cube. So once you created this quadrilateral 2D mesh, you extrude each quadrilateral vertically for a certain number of layers. So in the top right, I'm depicting this process, and I'm showing like a quadrilateral element with the spectral element degrees of freedom inside, extruded vertically for a certain number of elements. We refer to a column as each individual degrees of freedom extruded vertically for a certain number of vertical levels. So this is what the grid that dynamics uses. Physics parametrization can run on a different grid. On the bottom right, I depicted what it is. So there's the quadrilateral you can see with in green the dynamics, degrees of freedom, but physics is resolved using finite volume approximation, finite volume schemes inside each of these 4 quadrilaterals for physics. So there can be a difference in grids for dynamics and physics. So these are the computational grids that we use. In our journey in the last 7 years, we've pushed towards a kilometer scale resolution. And why we did that, there's a few reasons. One is that decision makers need prediction with reduced and quantified uncertainty. And increasing resolutions can help in this regard because when the resolution is large enough, you can do away with certain subgrid approximations, which are a big source of uncertainty. Another reason is that at fine resolution, you can capture more extreme weather events, which are a leading source of impact from climate change. And finally, improvements in HPC architecture in the last decade have made exascale simulation possible. I want to point out that in our Gordon Bell submission, we used a horizontal resolution of 3.25 kilometers. That's achieved with NE equal 1024 in the cube sphere that I showed before, with extruded for 128 vertical levels, and that's around 7 billion degrees of freedom per variable, with 6 state variables and 10 tracers. So it's around 100 billion degrees of freedom in our simulation. Here I'm showing just to give you an idea of what it means to be at a 100-kilometer scale versus a kilometer scale. These plots are just the surface height near the Bay Area in California, and you can appreciate the amount of details that you can capture in a model when you're able to get down to kilometer level resolutions. So in our path to exascale, a crucial concept was performance portability, which you've heard already a lot, and you already know a lot about. But what we mean by that is basically the ability of a code to run efficiently across a variety of architectures. And efficiently, what efficiently means, it depends. There are general metrics, but in the realm of climate science, what's usually considered is the simulated years per day metric, which basically means if you let your code run for a day, how many years of your model you're able to simulate. So to achieve performance portability, there are mainly 3 approaches, either via compiler directives, so you hint or force the compiler to generate an optimal code for the backend. OpenMP and OpenACC are example of this. General purpose libraries, in this case, you delegate all these architecture-specific optimizations and choices and implementation details to a third-party library. Cocos, Raja, Okka are examples of this approach. And then there are domain-specific libraries. In this last approach, you basically write your code in a higher-level language, and then an intermediate compilation step generates standard source code like Fortran or C, and this intermediate compilation produces optimal source code for the given architecture. Cyclone, grid tools, and other examples in the climate realm exist. And it's important to notice that with a variety of architectures that we have to support, we cannot maintain multiple versions of E3SM. Performance portability is really a must in the path to exascale. So we chose the second option in the list before. In particular, we decided to use Cocos. It's a C++ library for node parallelism. It provides abstractions around the concept of parallel execution as well as multidimensional arrays. through concepts like execution space, execution policy, memory space, data type, and so on. It supports several backends, including the most common one in HPC clusters now, OpenMP, CUDA, HIP, SQL. It's a very reliable library. It has a large pool of world-class developers. It's heavily tested, lots of downstream apps, which indirectly still test COCOS itself, and most importantly, it follows closely new HPC architecture, which can help to reduce disruption when a new architecture arises in the HPC world. We refer also to our portable atmospheric code as EAM-XX. When we ported EAM to EAM-XX, our guiding principle were mainly three. The first is expose as much parallelism as possible. We did that using teams of threads in COCOS. Then we wanted to maximize vectorization, because even though GPUs are the leading architecture in the exascale era, we still have lots of important clusters that are CPU-based that we still want to use efficiently for climate simulations. And so vectorization is the best way to achieve performance in terms of flops per watt on conventional CPU architectures. And finally, we wanted to minimize memory movement, which means we didn't just use the GPUs as accelerator, but we just kept everything on device as much as possible. So we went back to us basically just for I/O or for coupling with components of Ethereum that only run on host. And then, of course, we want to minimize also like the size of scratch memory and reuse it and be smart about it. Also, one thing that I want to point out, although I'm not going into detail, rewriting the code in C++ was a great chance to also promote a maintainable, extensible, and robust code, and also a culture of strong testing and verification. There was no unit testing in EAM. EAM-XX has lots of unit tests, but I'm not going to get into details for the sake of time. I'm going to move on. Our journey from EAM to EAM-XX, roughly speaking, went through three phases. The first was during the CMDB program. The second was during E3SM phase 2, and then now in E3SM phase 3. So in the first phase, what we did was we demonstrated that COCOS can be used as a performance portability approach in the dynamics part of EAM, most importantly, only in the hydrostatic component. In particular, what we did in this phase, we refactored the hydrostatic code. We've written in C++ with COCOS, and we were able to achieve better than parity performance with the original Fortran code on conventional CPUs, which was a great success. We were ready to settle for a little loss on conventional CPUs, but achieving performance portability, but we were actually able to do slightly better also on CPUs. And then we also did an in-depth comparison through several architecture on a single node case, and we looked at performance as we increase or decrease the workload that we throw at the machine. And that's depicted in the bottom right figure. There's a variety of architecture. The one in red that goes much higher than everybody else, and higher is better here. That was a V100 GPU, and it shows the classical behavior that you need to throw enough work to a GPU in order to get performance out of it. So that was our first phase. In our second phase, in E3SM phase 2, we ported the non-hydrostatic die core, which also includes some nonlinear solvers inside, and we started also the porting of physics. We were able to run the whole the die core non-hydrostatic version at scale on the full Summit system, both on CPUs and GPUs. And the takeaway here from the picture on the right is that when we use the GPUs on the full Summit system, we were able to gain at scale a speed up of roughly 10x compared to the CPU only. We also ran this simulation with n equals 1024, so that's a little slightly more than 3-kilometer resolution. But we also ran n equals 3096, and that's 1-kilometer resolution. And I want to point out that that's roughly 1 trillion degrees of freedom. And what we were able to achieve at 1024 was a 1 simulated year per day, 0.97, on the full Summit supercomputer. And this is just for dynamics. But what I'm really want to talk to you today about is like the last part of our journey, which is when we ported the full atmosphere model, including physics. And what I really want to show you is the plot on the right, and that's what sums up our journey. So we ran the full E3SM atmosphere model written in C++ with Cocos at scale on Frontier. I'm also showing our results on Summit as a comparison. The red curve is Summit, the other two are Frontier. The blue one is some ad hoc optimization for GPU, but even without those, we were able to cross the 1 simulated year per day barrier, and we're the first global cloud resolving model to do so when running a cloud resolving resolution. We're the first global cloud resolving model to run on an exascale computer at exascale scale, and also we can run on both AMD and NVIDIA GPUs, as well as conventional CPUs, and we're also our current experiments are also doing well on Intel GPUs, although we haven't been able, of course, to run on a full system at scale yet. And this work, of course, led to a Gordon Bell submission for the special prize in climate modeling, and we achieved the finals, and we feel very confident about our chance to actually be the winner. One quick consideration about power consumption. I'm not going to talk a lot about all this stuff in this slide. I just want to point out one thing, which is summed up in the last 2 bullet points. On Perlmutter, when we ran on GPU, we're roughly on a GPU node, we're roughly 5.8 times faster than when we run on a CPU with the same number of nodes. But we monitored the power consumption, and we used roughly 70% more power on GPU than CPU. So if you do the math, we're using a GPU, we're roughly 3.5 times faster per watt. So we're not just using GPUs because we have to make the machine shine. It's also because using a GPU is convenient also in terms of an energy efficiency. So how is EMXX used for science? So we have lots of simulations that are either ongoing, completed, or imminent. All of these, you can read details, but they're very important for the climate community in terms to understand better certain aspects of the climate and to face the challenges that come with climate change. I'm showing here a picture, just an eye candy to show you the level of details that we're able to capture with a simple cloud resolving model. So on the left, for instance, you can see at the top the result of the simulation. At the bottom, you see satellite images for shortwave cloud radiative flux, and you can appreciate the amount of details that you can capture with kilometer scale models. Sujin already mentioned that collaboration with other ASCAC projects. There's several pieces of EMXX that were developed by computational scientists from other projects. Scorpio, the IO library, semi-Lagrangian transport, RTMGP, non-hydrostatic, regionally refined meshes. Even though I didn't show them here, we do support regionally refined meshes in EMXX. So collaboration with ASCAC is, of course, of the utmost importance. So to conclude, so with EMXX, we finally kept faith to the exascale part of the E3SM name. And with our submission with the Gordon Bell Prize, with our results, I think EMXX established itself as a reference point for other atmosphere code bases when it comes to exascale. Every other atmosphere model that will claim to run at exascale, a cloud resolving resolution will have to compare with E3SM. The initial study for performance portability was a little time consuming, but the lesson learned considerably sped up subsequent work. Porting the code to run on GPUs for NVIDIA GPUs took a while, but thanks to Cocos, the amount of work needed to run on AMD GPUs was orders of magnitude smaller than the initial effort. So Cocos is efficient to map to architecture, but also efficient as a strategy to reduce disruption from future architectures. The downside is that C++ syntax is much heavier than Fortran, of course. This can be a barrier for some scientists. So we need good software design, separate concerns as much as possible to make code more maintainable and increase productivity. And finally, I'll point out that we're not the only effort that uses C++ with some performance portable layer. Mali, which is a CIDA project, also runs on GPUs through the Trilinos library, which relies on Cocos. And then the next generation Ocean component Omega also will have a portable layer and will be written in C++. And with that, we'll be happy to answer any questions.
All right, thank you, Luca. Questions? So I'll ask one. I mean, this is an impressive achievement to be able to do simulated days, but am I correct that we're still a long way from being able to do large scale parametric studies? Even at this scale, we need even more performance?
Yeah, that's a more. I mean, like I have like inverse problems or optimization or sensitivity with respect to parameters and that kind of stuff. Yeah, of course, that entails like a lot of study also like by UQ group and like efficient sampling strategies. I don't think we'll have like a lot more performance that we'll be able to squeeze out. So we can expect, of course, some performance improvement, but it's not going to be orders of magnitude. Like we saw 10x going on GPU, but I doubt we're going to have a 10x. So it will have to be algorithmic improvements probably going forward to like do efficient parametric studies.
Well, and probably next generation architectures too. So
hopefully, but you never know what you get.
Yeah, so Dan, if I understand you correctly, so you're right, we cannot run like, for example, like many decades or 100 years old high resolution simulation kilometer. But I think right now with the speed we have and the DOE computer we have, we can run like up to a decade. That's in the ESRSM's roadmap. So by 2025, we will run the 3 kilometer global decade-long simulation.
Okay, thank you. Other questions or comments?
There is one in the chat from the public.
Yeah, and so the question is, what's the status and strategy for integrating all the subgrid physics into a C++ model?
Well, we already, I mean, our parameterizations for subgrid, for Scream is Shock, which does the turbulent subgrid parameterization. That's already working in C++, unit tested and efficient. There are other parameterization that you need to include if you want to run at lower resolution. That's part of our to-do list. To include more parameterization that are needed depending on the modeling choices. As usual, the issue is staffing, time to do that. But all the physics that was included in this round, which is radiation, macrophysics, microphysics, and aerosols, all of that is already done in C++ on device. So it's a big chunk already of the work. And the thing is, like, using what's been done already as a template, porting a new parameterization to C++ and to run on device is not as hard as the first one that you do. You can use templates and recognize patterns to increase the speed at which you can do this porting.
Great, thanks. Any questions from anyone at this point? Seeing none, thank you both. Terrific work.
Thank you.
Thank you.
And so next up, we have an update on the Chips and Science R&D office from Eric. As we know, Chips and Science, the authorization, there's still a big air gap between authorization and appropriation, and that's an ongoing topic of conversation, but there is money there to do some good things, and I know Eric's going to tell us about that.
Hello, everyone. Can you hear me okay?
Yes.
Okay, wonderful. Thanks so much for having me here. I know you've had a long day, a lot of material, so I'll try to keep my talking to a minimum and really open to hearing any questions or feedback that you may have around the Chips for America Act. I think, Christine, you have the slides. Can you help me with that?
Okay. Yeah, just give me a second.
Okay, sure thing, no problem. So my plan is really to just outline just the basic approach that we have in the CHIPS R&D program, to go through the components to just give an idea of what they look like, what's coming up next, how we see them to be proceeding, and then try to leave as much time as possible for questions specific to your community and how the CHIPS R&D program can support that. Before we get to the slides, just want to just make sure I note that Chips for America is predominantly in the Department of Commerce. It encompasses the two major programs, which are the incentives program, the manufacturing incentives program, that is $39 billion in size. And that is focused on the near-term onshoring of domestic fab capability into the United States as a national security and economic security imperative. The R&D program, which I'll be going through in more detail, is $11 billion, also in commerce, also at NIST. And we are complementing the incentives program in that our mission is to ensure that the foundational technologies for semiconductor manufacturing into the future is developed here and is supported so that the investment in the short term on onshoring fabrication and manufacturing is sustained. And so there are plenty of places where we are working together to try to achieve the best outcome for the country. The last thing I'll note is on this front as an introduction is that we are working very closely across the government. It is a whole of government effort with these funds, including 200 million NSF for workforce development and 2 billion for the microelectronics commons from the DoD that was with their initial awards just announced last week. We're in regular communications to try to pull together all aspects of the government in service to these top line goals that have been set out for Chips for America. Okay, so with that, thank you so much. If you go to the next slide. So if I just stick to the R&D program and our specific R&D goals, they can be distilled to these three. The first one is US technology leadership. And so continuing that theme is that we need to ensure that the United States invents, develops, and deploys the foundational semiconductor technology of the future. The US does lead and has led in much of the development of the current state of technology. And we want to be sure that those next waves of innovation are supported and nurtured here in the United States so they can be deployed here. The second goal is to accelerate ideas to market. Not a new idea, definitely an imperative with this program. And what our target is to develop a thriving ecosystem that is focused on getting the best ideas to commercial scale as quickly and cost effectively as possible. Especially for a technology that's so critical to so many other technologies like semiconductors and chips, is that, and also the complexity of the technology is so high that we really need an ecosystem that can match that level of complexity because there's so much dependency between one innovation in one part of the process to another, all the way from design into the final packaging of the product. And so our goal was to make sure that the research and this technology transition ecosystem can match that level of complexity enough so that the best ideas have this chance to get to the market. By going quickly and cost effectively, there's a number of barriers and gaps that have been identified by the industry, by the community overall. And so we have been designing approaches for the R&D program, largely leveraging a lot of the existing efforts across the country and to catalyze new ideas to try to address those barriers specifically. The third goal is a robust workforce. There's no shortage of awareness of just the shortage of STEM workers overall, and then workers specifically for the semiconductor industry. And so our goal in the R&D program is to take the long view and to help build a workforce development ecosystem around semiconductors and its workforce to have a new generation of skilled workers, inventors, designers, researchers, technicians, and others that can take these ideas and sustain them into the future. Just as a quick note, we're taking a look at workforce from the R&D perspective of not just filling vacancies and jobs or just filling gaps in training for those vacancies. Certainly those are very important, but we really want to take an individual person-focused point of view in that there should be an ecosystem where someone could enter the industry, perhaps as a reskilled person or someone just entering it from another field, and to be able to find ways to thrive within the industry by being able to find other additional jobs and knowing how progression in a career pathway may work within the semiconductor industry as opposed to counting jobs and seeing how many people can be filling them. So taken together, you'll see these 3 goals woven through the programs all through CHIPS R&D and are shared across the government as well. Okay, next slide. Okay, so for the CHIPS R&D program, sorry, I'm repeating for those of you who know in detail, but I'll just cover it for those who may not be following along as much as detail as we move along. We have 4 major programs in CHIPS R&D. The National Semiconductor Technology Center, that is the flagship program of the R&D efforts here in Commerce, and I'll describe what that is in more detail. To the right, we have the National Advanced Packaging Manufacturing Program. This is in the legislation that is focused on using R&D tools to build a US domestic ecosystem for advanced packaging. And advanced packaging, for this audience, does include heterogeneous integration and chiplets technology, of which is, some of the areas in which HPC are making advances through that part. So this is a specific program to support a domestic ecosystem in advanced packaging. To the left is the metrology program, largely centered here at NIST. It leans into our core mission here at NIST on measurement science and standards. And we are augmenting our program to identify what we have done is, I'll touch upon in more detail later on, are some grand challenges from the industry point of view. The measurement sciences, specifically the ones that will accelerate semiconductor technology into the future. And so we are designing that program to build upon our strengths, but also to connect with these other 3 programs so that from an industry sector point of view, that it is all harmonious and built together. At the bottom, we have in the legislation to add up to 3 Manufacturing USA institutes to add to the Manufacturing USA network. And I think the big idea here is to connect the CHIPS R&D ecosystem with the Manufacturing USA network, and which can be very synergistic and powerful for taking ideas from one set of approaches within Manufacturing USA and connecting it with a specific important sector like the semiconductors industry. So as we take these programs together, one thing that we have been very mindful about, both for the requirement because of how integrated the industry is, but also to achieve the goals of strengthening and advancing US leadership for semiconductor manufacturing technology as a whole, is that we really need to pay attention to how these different programs fit together, going into what we've been calling more integration as opposed to collaboration or coordination. Those still didn't quite capture the essence of having to be thinking intentionally about, say, how an output from one program would become an input to the other. Or if there's a participant within one program, would it be a frictionless experience to participate in another program if that is what the resources needed to get a technology to commercial scale? So this is not, all of you here are very well aware that this is not an easy task, but since we are doing it from the ground up, that this is imperative to get right in order to have the best chances for complex ideas to reach the end. The last 2 points about the design of the project at a high level is that we are taking a very strategic view about the infrastructure that's needed to accomplish these goals, and also paying attention to the participant value proposition for those who would join these programs or be funded by those programs or make use of resources that we make available. And so that would go all the way from academic institutions to national lab personnel and staff and programs to companies large and small. A lot of our thinking and work has been informed by the Industrial Advisory Committee, which was stood up a little more than actually just about a year ago. And this is 24 individuals who represent a broad swath of the industry, and they have been working extremely hard over the past year, really helping us think through some very complicated issues about the design of these programs. And so we've taken a lot of their input, as well as those from RFIs and from the PCAST report, and quite a few number of community thoughts about how to construct these programs, and we've synthesized it into what we'll be executing, that we have been executing over the last year or so. Okay, we go to the next one. Okay, just to give you a sense of how the programs are being rolled out. So the legislation passed a little more than a year ago. And during that time, we've been working 24/7 to outline the strategies and moving into more direct implementation. So if I go program by program, I'll just give a sense of what we've put out so far and what the next steps will be. And then we'll go into what they are in a little bit more detail. So for the NSTC, the National Semiconductor Technology Center, our vision strategy paper, which was done in partnership with other agencies, of a lot of collaboration into into that vision and strategy, was released this past spring. And inside that vision strategy paper, we outlined a number of component programs that I'll go into more detail. One key part is that this is under legislation meant to be a public-private consortium to be established and to be run as with a nonprofit operator. And so we're in the process of standing up a purpose-built organization to be the operator of the NSTC consortium, and that these may not make sense right now, but those steps in being able to announce a board of trustees for that nonprofit, we expect to be any time soon, but certainly within the next couple of weeks. And then through the rest of the calendar year, we'll be working to stand up the NSTC with that organization. For the advanced packaging program, we announced the director of this program earlier this week. It is Professor Subbu Iyer from UCLA. So he started Monday, and we're really excited to have him. And we will be releasing a vision and strategy paper for the packaging program in the coming weeks. For Manufacturing USA, we've had a lot of community input, and also in the same time frame this fall, we are planning to announce the topics that have been selected and to begin the proposal and engagement process for how to build the Manufacturing USA Institute. We have legislation to support of up to 3 new institutes. The metrology programs are well underway with grand challenges projects, and we have the reports of the directions we're going on our chips.gov website. And you'll be hearing more about how that engages with the community and with industry in also the next coming months. Okay, so with that said, let me go into each of the programs. I'll just give you a sense of what they're about and how they're constructed. And then hopefully that would have left enough time for questions. Okay, we can go to the next one. Okay, the first one is and one more is good, is the NSTC. And the vision for the NSTC is that by the decade's end, the NSTC should be viewed throughout the world as an essential resource within the broad semiconductor ecosystem. We envision it to have a network of respected scientists and engineers, facilities, effective programs, and technical achievements. One way to think about the NSTC that we've tried to articulate is that the NSTC is essentially a platform organization where we want to convene the community as a public-private consortium with membership and those that participate. And it's where key ideas and new ideas are both ideated and pursued in a collective fashion, but also is supported by a network of facilities, expertise, and other resources, so that those that have an idea have resources that they can draw upon to give the best chance of those commercial successes that we are aiming to have. Okay, so we can go to the next slide. Okay, so there's 3 basic types of programs that we envision within the NSTC, and they're described in one category of technology leadership, community assets, and then workforce. Okay, we can go to the next one. Okay, I think we can go back one more, then I think I'll just talk through what these are, and I can go into more specifics are in the vision and strategy paper. So for technology leadership, these are programs that are looking for input and to synthesize with the nonprofit organization and from the membership itself about what are grand challenges or very important leapfrog technologies that will take collective effort. And so we imagine programs that would be funded around those type of topics and to be able to drive towards those final pieces. And so there'll be a number of projects that we envision across different types of technology areas where there'll certainly be more than one grand challenge to be pursued, but it would be meant to try to drive and organize the community towards those large scale leapfrog ahead ideas. In the second category for community assets, These are both physical infrastructure, such as a prototyping facility that is often identified as a gap within semiconductor manufacturing technology, of somewhere between the early stage type of prototyping you would do in a national lab or a university fab environment, to the final scale up to high volume manufacturing that is largely performed by the foundries and the IDMs of the world. And there's a stage in the middle, which there is a shortage of that pathway finding to high volume manufacturing that has been an identified need for the community to be able to fill in and to be able to accelerate that stage of the technology development process. We also imagine that we want to build a digital enablement gateway, which is a repository and resources of lower cost access to electronic design tools, coupled with the data that you need and a bank of silicon proven IP, which are resources that a small to medium-sized company often have difficulty finding a resource to gain access to, or losing time in order to license them appropriately. And so by building out this library in a shared environment, that we hope to reduce that barrier for a number of companies before getting them onto track for other more traditional pathways for scaling up. So you can see ideas like that throughout the paper, which is around what are the types of tools that would be necessary to lower the barriers of access and accelerate the transitions into commercial scale. On the workforce side, we are envisioning that the NSTC, as a community convener across the whole range of the semiconductors technology overall, is also, we're recognizing that these ideas and the energy to perform and execute on new technology is performed by people. And so we want to center people within the programs and provide resources that amplify and help people find the best ideas in developing workshop within a collective center of excellence on semiconductor workforce. This center of excellence would need to take an industry sector point of view, not just a point of view of an educational or training institution, for example. There's already a tremendous amount of activity that's been invested across the country in terms of educational infrastructure and those that are closer to fabrication sites that have been announced. What we need are things like, how do we know, can we measure the effectiveness of a training program from an industry point of view? Can we collect and build competency models that augment what curricula are being offered within educational institutions so that those credentials can be transferable across a career set, for example? How can we reach underrepresented communities who may not know anything about the industry? What types of approaches are effective? So within a collective center of excellence, drawing upon and bringing all those ideas together, we hope the NSTC can couple this technology development along with the workforce development. Okay, we can go to the next slide. So I don't think you'll be surprised that we imagine that this nonprofit consortium will have membership across the full range of institutions that would have interest and contributions for what we're trying to do. Okay, next one. Okay, maybe I did do this. Okay, so this is just an example set of what could be seen as physical facilities that would be part of the NSTC network, and it goes from a baseline CMOS process all the way to more specialized areas like memory, photonics, or power, for example. Okay, we can go to the next slide. Okay, we can go to the next one. I think I already covered a bunch of this. Okay. So if I go to the next program, advanced packaging, manufacturing, the mandate is to use R&D tools to build a domestic ecosystem in advanced packaging. The best way to think about this program is as a traditional funding program, that we are using the funds and the mandate to make investments to achieve this goal. So what that means is that we will be leveraging public-private partnerships and a range of tools that can help us with that, including using the NSTC to build out the capabilities, especially those in advanced packaging that need to be very closely aligned with how leading edge production is being done. Now, within advanced packaging is certainly seen as the space where a lot of performance improvements can be made within semiconductor technology. And I'm sure all of you are familiar with these concepts of heterogeneous integration, tooling and automation substrates for a broader range of application space, chiplet technology, for example, all different kinds of pieces that are are where a lot of the performance enhancements are being developed at this moment. We can go to the next slide. And so, in thinking about the space, we have basically one context point is that advanced packaging done inside the United States is currently under 5%. So trying to solve that gap from 5% to a viable percentage in the United States is basically the main choice, the main strategy we need to pursue is what is the next phase of advanced packaging and to skip the current business model into what is coming. And to do that, we're looking at it through two different lenses. The first one is technology innovation. And those are the breakthrough technologies for how advanced packaging will be practiced into the future. And that would be something like heterogeneous integration with co-design. And then the second part would be ecosystem support, which is we see as investments to bolster the growth of domestic capacity for those foundational pieces of the ecosystem. And examples of that would be something like materials and substrate, which are basic essentials, but are not available in the United States, to tooling and automation, which are approaches to replace the labor cost differential as one example between where packaging is done today versus what may be done in the United States with a competitive advantage. So here's a couple of other examples of programs that we imagine. We'll have more details in the vision and strategy paper that we will be releasing in the next month or so, very shortly. And that is be funding people directly towards against those targets in those programs. Okay, next slide. We also see a recognition for building pilot packaging facilities. We tend to connect this closely with the NSTC and the facilities there, so it'd be a single managed network of resources for the community to be able to use. Okay, so you can see some of the details here. I won't go into them at the moment. Can we go to the next slide? Okay, halfway there, just two more. So the metrology program is really centered around measurement science and standards. These are foundational, very pre-competitive types of topics that will be tackling. And what we are planning to do is to really change and focus our programs around large grand challenges that the industry shares, as opposed to a more traditional approach where we are doing it domain by domain or like a specific project by project. We're gathering projects together to be able to tackle larger grand challenges in the measurement science space. Okay, go to the next slide. What we are saying here is that metrology has connecting points to all of the other programs and it's being designed with that purpose. So within packaging, there are a number of measurement science challenges that are across the industry that we'll be addressing. And then the same with the NSTC and the technology areas that would be focused on. We are also being mindful that the measurement technologies also need to reach commercial scale. So whether they're online in a fab facility, or they're in a failure analysis laboratory somewhere, or in the testing of the performance of a new chip architecture, all of that needs to be incorporated and needs to also reach commercial scale to accelerate the development across the spectrum of the industry. Okay, next slide. We had some workshops last year. We had more than almost 1,000 industry participants to help us identify these key strategic opportunities and turn them into grand challenges. You can read the report and the outcome at chips.gov, or we'll have these slides for you. You can use the QR code to do so. And so it covers a number of different areas like this, from the measurement science of new materials and packaging, all the way to computation, data, visualization, and automation. Okay, if we go to the next one. We summarize them in these 7 grand challenges. I don't think they'll be of any surprise, but these different topics have a lot of specific details for why these different challenges are so important and how they can accelerate the development of new manufacturing technology. And so our intention is already to start to build upon the different grand challenges. The dark blue ones are the ones we've started so far. And then to go into the spirit of how we intend to engage with industry and the community is that we see these becoming communities of practice around the measurement science around these core areas. And within these communities of practice, to be able to provide the resources, the intellectual energy, and an environment where that type of the ideas and solutions that are developed can really come forward. Okay, next slide. Okay, Manufacturing USA. Okay, next slide. For those of you who are not as familiar with Manufacturing USA is a program focused on advanced manufacturing of many different types. In this chart, you can see there are 17 institutes that cover a range of different advanced manufacturing technologies, ranging from biomanufacturing on the right side of the logo diagram chart, all the way to the left side, which are pretty closely connected with semiconductors like AIM Photonics or NextFlex. A unique component of Manufacturing USA is that each one of these is a public-private partnership. Each one requires an industry or member cost match for its program, and they're intensely focused on getting across the valley of death for these specific advanced manufacturing technologies. And so for CHIPS for America, the concept is to take now the types of facilities and public-private partnerships in the NSTC, and there'll be a network of expertise and facilities and resources. And now we want to connect these two networks together intentionally so that interesting ideas from one can flow to the other and vice versa. And we'll be adding an institute or 2 or 3 to this network specifically focused on semiconductor manufacturing. Okay, next slide. We did issue an RFI to the community for ideas about what are the best places for investment, the technology areas for Manufacturing USA, and other factors for the design of the new institutes. So we published this report in the spring. You can see a range of respondents. All of them were very informative and helpful. We go to the next slide. There was a lot of consensus about things like make sure you're coordinated with the other CHIPS initiatives, make sure it's connected to the other Manufacturing USA institutes. There's consensus on trying to ensure long-term sustainability of the institute. Where there was not consensus is on what topics would make the most sense for the Manufacturing USA institutes. And so we are going through, excuse me, a review, our own internal review process to take that input and to identify the topics we think would fit best, not only for the industry, but also within the overall portfolio of the CHIPS R&D efforts. So we'll be announcing that in the fall as well. Okay, we go to the next one. Here's an example of just some of the ideas from the RFI, from cross-cutting technology topics like smart manufacturing automation, advanced materials, co-design digital twins, or a very focused topics such as substrates for advanced packaging or MEMS, for example. So the full range of these ideas was exciting to read about, even though there wasn't a consensus. Okay, I think I have one more. Okay, thank you. So, well, when I put in the slides, the R&D Standards Summit, which is one of our big events, it actually concluded yesterday, so I'm sorry it's a little bit out of date. But it gathered all the standards organizations in semiconductors together to think about where standards could be an accelerator for this core idea of leading to technology leadership. Almost 1,000 people registered for this summit, which I never saw for a standards-focused summit. And a lot of exciting ideas came through it to highlight and emphasize the themes I've been describing for our programs. For more details about chips.gov, the R&D program, and the incentives program, you can find it all at chips.gov. All of our reports are there. There's a ton of information. Also, you're welcome to reach out to me or others within the office or through your colleagues here at DOE, and we'll certainly be open to answering and engaging with you however we can. I will say, just to close, is that I think it's pretty clear how this ecosystem can be contributing to high performance computing overall. I led with an example of chiplets being critical to reaching exascale computing, for example. And so can we imagine what other types of performance, market, and usage drivers can help inform where the technology needs to go and what kind of challenges need to be reached? I think if we are successful, that we'll be able to have a full range ecosystem that can go from design all the way into the manufacture of hardware that can really accelerate the breadth of types of specializations that might go beyond what NVIDIA and others can do today, or what a design shop or like an Apple designing their own chip? Can there be even more ideas for architectures and technologies to draw upon to reach the next levels of computing power that has its own accelerating technology component into where the US can still remain in the lead? I would be remiss to also just point out that, you know, if the more computing power you have, then the more quickly you can design all these complex processes. I don't know if chip manufacturing is quite as complex as the atmosphere and climate at the moment, but they're both pretty complex and require, you know, capabilities to be able to really be able to address the problems that both those areas bring up. Okay, with that, I hope that was useful and not too much a review, and I'm happy to answer any questions that you have.
Thanks so much, Eric. Question or comments from members of the committee? Martin.
Hi, thanks very much. Great presentation. Could you didn't really, I mean, unless I missed it, I mean, you didn't really say too much about what you sort of plan to do in the area of photolithography, but this seems to be the key technology. And it seems to be something of a one-horse race at the moment. And it also seems to be a sort of horse that's been trained for about a decade or more, you know, taking a very long-term view, which sometimes isn't easy for industry to take given shareholder pressure. So how do you sort of compete against that one horse, or at least make sure you've got a backup horse? Let's just put it like that. You know, I'm thinking about, you know, whether that technology sort of, to my understanding, probably goes down to about 1 nanometer in terms of, you know, the latest machines. And then the question is, what's next, and what should, so, you know, how would the chips activity kind of play in that space, and where would it lead us, do you think?
Sure. It's complicated question to answer, but I take your point for exactly the situation as you described. My research career was in lithography, and so it's very interesting to see how that technology developed and how EUV even got to where it is today, and still using the same fundamental resist chemistry that was still developed in the 80s that is still present today. So to answer your question, the first thing we've realized in this program is that the business model market drivers for how they adopt technology is essential to take into account. It's almost as much of a business economic driver for why lithography finished where it was, even more so than any technology component. And so once you know that, then the researchers who want to find that next technology need to take that into account. And so although I don't know the answer for what that will look like, is certainly, we're fortunate that that one horse race is in an allied country for the purposes of this program. But certainly whatever solution has to come has to also meet all those market drivers as well as the technological ones. That being said, you know, the entire process flow is you know, several dozen operating units, unit operations, and each one repeated maybe 10 times, so there's thousands of steps. There is a lot of room for improvements across that stack for what is to come. And then when you get to heterogeneous integration, you're complicating that into even more complicated 3D structures. So the range of places to make a difference, either by margin or to improve yield, or any number of those type of areas, is pretty open. And so it's not just about the lithography, even though that's one clear bottleneck, but there's so many other areas that are dependent upon those pieces that would be equally as valuable, which we don't actually know. We want to set the conditions for what comes out best by matching the science technology along with just the business economics. It's less about business economics, it's more like business physics. Like there are some rules that just can't be broken in terms of just being viable.
Thank you, great answer.
Mark, then Karen.
Yes, I noticed that you're going to invest in simulations and some other things, but I didn't see anything specific that I could pull out from in the area of tools and in the area of the integration of AI to support things like automated testing or things like that.
Semiconductor industry is fully in the mainstream of trying to adopt AI for everything they can think of to use it, including those areas, especially for, yield and process optimization. Those components are definitely woven throughout all the programs in terms of access to supporting modeling, primarily through access to data and to modeling tools or design tools. So for example, I kind of overlaid, I didn't really talk about it, but in the metrology program, one of the key ideas is what we're calling METIS, which is a one-stop shop for access to core reference material information, fundamental constants, test structures that you can calibrate and work against. And so it'll be a rich environment that'll be accessible to those who want to optimize metrology and what it can tell. So if you want to do something like testing and assembly, then you do need some basic validated data to be able to validate any machine learning or AI model that you'd be using. And so a ground truth purpose will be served by this shared digital resource. Within the NSTC, we have the digital enablement gateway that covers a lot of pieces from IP to licensing to lower access design, cost access to design tools. But it is also intended to be a platform to be able to share data across pre-competitive research projects and across all the facilities that we imagined in the NSTC. Now, I know for this group, you appreciate the challenge of having a common data management structure or schema about sharing rules and protocols in order to gain the advantage of everyone sharing without losing your competitive edge. We believe there's enough energy in this community to see the value of pulling that data to getting to the types of tools you're describing. So even though those tools are not the focus of what we're doing, the foundation for making those tools successful is certainly woven throughout all the different programs that we have. It will depend on people participating and agreeing to do these. So we need to make sure the value of contributing is far lower than the benefit of what you get when it all puts together. So I hope you can find those themes across there, and if it's not clear enough, you can give us that feedback and we can try to amplify what that looks like for you.
Karen?
Thank you. Thank you for the update. Really appreciate it. My question is a bit more looking at things from a DOE ASCAC perspective. So in the context of leadership computing, high performance systems, and that, is there any thought about opportunity? So as we're getting beyond exascale and beyond, the systems are getting complex, very complex, and from a kind of a hardware side and software side, but hardware side primarily, which is more the focus of the CHIPS Act. There's almost like research that needs to be done in terms of bringing up these very complex systems. It's not like a turn on and off you go anymore. So as we are developing future technologies, particularly heterogeneous integration and heterogeneous computing is clearly going to be part of our future. Is there an opportunity within this kind of global consortia of institutes and funding to have? I saw the prototyping, which is wonderful. But what I'm asking is there an opportunity to sort of have like test bed type of systems? So a little bit more than just kind of a component, and a little higher up, on the system level. I think it's something that if it's not been considered, it may be something that'd be worthwhile, thinking about, because I think the future of computing is going to depend very heavily on that.
Sure. I mean, as you can tell, we haven't really named exactly where those areas would be within the NSTC. What you've described is very much in mind, because it's not only the performance aspect, but it's also those are market drivers in the context of why Chips for America was passed. So there's certainly room and space for that. We have those technical centers and resources. We do imagine to be more of a test bed concept, right? It's not just a service to prototyping for anyone who thinks they can get the commercial scale. They're meant to be prototyping / test beds in order to be demonstrators for now the capital from the private sector can be de-risked enough to do it that way where it should happen, right? So I think we could use and would value, certainly with DOE here, of course, they've been very active in the conversations about how to best utilize the assets within the DOE system and how to get all the components can fit together. Even like the easy one of just like, we have some of the world's best high performance computing. Why wouldn't we use that to help us be better at making computing, right? That makes no sense at a very basic level for that. You know, the trend of like there's more diversification and specialization of different, right? Like in this program in DOE, you've had to do that, right? They're starting to differentiate into different kinds of high performance computing. Maybe that should continue. Then we really do need a space to be able to prototype and test which ones can be adopted for which purpose. Chiplets, if we can standardize that technology, we can start to mix and match even further and turn that crank even faster. It would be better if we could be guided, that could be guided by clear directions of opportunity. And I think what you've described here and how this committee and this part of DOE operates would be an important contributor to what that could look like. I think that'd be a very powerful example of how one part of this case, the US is leading in the design and production of the world's fastest and highest performance computing platforms over a range of different approaches. And can we now marry that to what comes next? Because now we have a powerful R&D ecosystem for the hardware and manufacturer side that is now ready and present that can be harmonized if we find the right pieces to put together. So yeah, I think that'd be pretty, so yes, the answer is yes. And I think that's kind of how it might come together.
Yeah, I was going to ask a version of that same thing, because we certainly know the decisions that drove offshoring of semiconductor supply chains and led so many US vendors to focus on fabless design. But we're also at this inflection point about what the future, to Karen's point, of computing itself should look like. And some of the needs that the country has, it's not clear that the answer will emerge purely driven by economic forces, which is a subtle way of saying it's not clear money can be made for some of the things the country needs. After all, we build submarines and aircraft carriers. There's not a vibrant commercial market for those things, but they're very much of need for the country. And whether it be science and engineering or national security, that other side of the ecosystem, which does depend on a vibrant economic model underneath it, but nevertheless needs some government help to drive things forward, I think is what we're all in this committee kind of struggling a little bit with, because it's clear the path we've gone down, there are some forks in the road, and you touched on some examples of what those are, but any thoughts on how we marry those two together? I'm basically asking Karen's question a different kind of way.
Well, first easy one is please join the NSTC. Tell Hal and the other DOE folks what's most important. That there's definitely spaces for those conversations to take place. You're correct in that and Secretary Raimondo and the NIST Director Laura Lacoste are pretty clear in that the mandate for this program is also clear, and that is not the current economic drivers that drive what we need to invest in. The first imperative is national security and economic security as a couple pair, just restating what you said. So I think the main thing is to be able to make that case, right? So if there is a case for why this is now a leap ahead national security point of view, because it gives us some capability or capacity that would meet those targets, then framing it that way is very powerful and be very helpful. So sometimes when we talk to academic researchers, for example, I would say, they say, that sounds like you're not going to fund research. Like, we're absolutely going to fund research. How do you think this is going to happen? There's going to be a lot more research overall. It's just that in this program, as you can hear how it came about and what is being asked, the success of that research is not whether or not you published it. The success isn't even if it was very high quality. The success is, does it meet our national and economic security objectives? Personally, they're usually coupled. I mean, honestly, But I'm just saying, like, that's the framework of which we're operating under as the imperative. And so I think if you take that same mindset about why, and you already do in this committee, right? I mean, like, well, why do we need this kind of exascale computing or this capacity or what's coming next? Then framing it in those terms makes it clear in terms of a prioritization decision point about how to best support that. And then it is a whole of government effort to be able to articulate where that should go. So within the interagency, we will be and have been having conversations about, well, where should that investment be made in the national interest? It is not in the commercial interest. We ask, is it commercially viable so it could be sustained, but it's not a commercial interest that drives it. So those are difficult, but also challenging and fun, but we take a lot of input for how to do that. So if you're also aligned in that type of language and mindset that's been set from the very top across the bipartisan way across what's been happening, and that DOE is also very, very good at, then that just makes it stronger and tighter to help us articulate the justifications, reasonings, and motivations for whichever direction we need to go.
Thank you, Eric. Any other questions? I'm looking to see. Very much appreciate you making time for us today, Erica. I know I speak on behalf of the rest of the committee. We're committed to collaborate in any way to support these shared agendas. I've spent more than my share of shoe leather advocating for chips and science on the Hill. So it's good to see some things off the ground.
Well, thank you so much. We all appreciate it and know how precious an opportunity this has been from all of your efforts. So thank you very much. I really appreciate it. Please reach out to us, sign up for our newsletter, chips.gov. There'll be a lot to come in the next few months.
All right, thank you. I want to ask if there are any public comments from anyone who's hung in here, and then I want to turn to the committee and see if they have any final thoughts on strategy or other issues. But any other comments from participants that people would like to share?
Yes, they'll have to type them into the chat, and perhaps I can let you know if there are any as you guys have your conversation.
All right, thanks, Christine. I just wanted briefly to circle back to, and it's really a continuation of what we were just querying Eric about. You know, any thoughts on the best way that you think we as ASCAC can try to help shape what are in collaboration, obviously with DOE, ways that we look forward from the successes, but also frankly the uncertain future we have in terms of which directions we go to support national needs in the infrastructure and the research associated with it. So any thoughts on that before we adjourn? Or is that too big a question to contemplate after a day of meetings? Well, this is a quiet group today.
Yeah, this is Roscoe. I think the questions you raise are very important. It's just the answers are not very easy. I think, you know, we certainly have had the experience of suggesting ideas and so on, and they're not propagating far enough up the chain or in the right way to have the impact we would have liked. I mean, of course, I'm thinking of the transition report and things that, you know, that nobody said there was anything wrong with it. It's just we didn't lead to action. And so improving that pathway is something that might help, and also seeing if there are other pathways that those of us who have much of other lives can do to have an impact. But I appreciate the question, but don't have an answer.
Jaron, I don't want to put you on the spot, but you know, as the new kid on the block, so to speak, in this role, what can, from your perspective, what can we most do to help?
Well, I think it's a very loaded question, and again, certainly, we had the transitioning the ECP report, but and given the recent advances in AI too, I think that's something that we should consider as a community if we need an update and give us more of a actionable items maybe in terms of timeline, right? So I think that's something that we should consider as a community.
Okay. Any other thoughts? I don't want to hold people. Martin.
Yeah, I mean, I think psychologically what we respond best to, or what everybody seems to respond best to, is a threat. You know, there has to be some idea that, I mean, and right now things are looking good. You know, we've got these exascale machines, you know, 2 of them are here, one's coming, everything looks great. But my sense is that, you know, if you start looking about 3 or 4 years down the road, it doesn't look so great anymore, especially if some of the advances that are being made in China with the phones and chip technology lead through into machines that people are not really too concerned about the power consumption of. And all of a sudden things should look very different. And so the real question is, you know, is there enough understanding of what's going on elsewhere to sort of understand what the challenges and threats are to the position we've got at the moment? And I'm not sure. I mean, I just don't know. I mean, you probably know better than I do. And that seems to be one of the drivers in some sense. Certainly, you know, there are some real challenges there in terms of what's being done in some of these other places and the kind of work that's being done. And it would be foolish to ignore those, but I'm not sure that we're also taking them into account enough, or maybe I'm wrong and we are. So, you know, please correct me if I've, you know, got the wrong end of the stick.
Krista?
Well, just Martin's comments spurred me to think a bit more as we're closing out the Exascale computing project and thinking forward for the, you know, towards those challenges. Where might those risks be in the next few years? You know, of course, one risk is quantum computing, and we also mentioned AI. So I think there is an opportunity for this group to really advise and look further in terms of what is the ECP 2.0 that brings together you know, exascale compute or high performance compute, AI, and quantum computing, and how are we helping you know, make sure that we're accelerating to quantum safe, for example, but also then looking at the applications of quantum computing, which is the opportunity, right? So there's both the threat and the opportunity. But I think also, how do we bring HPC and AI together, right? Even in advance of the quantum side. You know, there's just so many, just listening to the presentations today, right? You have materials discovery and you're understanding climate and right. And these AI models are, of course, becoming more and more advanced, which is phenomenal. But there's a real opportunity for us to, I think, help shape the direction of those investments in the coming 2 to 3 years.
Well, I'll throw out one other thing and maybe let people go and encourage us all to think about it. One of the things that I was discussing in another context was how rapidly some aspects of this world are moving, right? 3 months in the AI world is forever. And that's not the time scale in which government, whether it be the lab side of government or academia or government itself, tends to think and move. And that was a conversation I had at OSTP last week is, you know, can we move thoughtfully, but with enough alacrity to be able to embrace the opportunities and the challenges as they evolve? Well, maybe on that note, I'll leave that as food for thought. Thank you all. And let's hope we have a government on Monday. But whatever happens, we will persevere. And so thanks for your participation. Thanks for the thoughtful comments and for the presentations. And whatever time zone you're in, have a great rest of your day.
Thank you.
Thank you. Bye.